Request our esteemed guests to please take their seats in the hall. Okay. Okay. Good morning, everyone, and I'd like to welcome one and all to this opening session of this 8th conference of India Radar Meteorology, iRAD 2026 at Guwahati University. The India Radar Meteorology iRAD conference, as you all know, is a flagship scientific forum initiated by the Ministry of Earth Sciences, Government of India, to advance research in radar meteorology. Since its inception in 2017 at IIT Kharagpur, iRAD has evolved into a vibrant platform that convenes leading scientists, technologists, and professionals across the world to share insights, breakthroughs, and emerging trends in radar-based atmospheric observation, extreme weather forecasting, and climate analysis. In continuation of this iRAD series, this time the 8th edition of iRAD has been hosted by Gauhati University. And to mark this occasion, we have with us a host of dignitaries. We have with us our keynote speaker, the Chief Guest Professor P. Chandrasekhar, Colorado State University. We will be soon joined by Professor Nonigopal Mohanto, Honorable Vice Chancellor, Guwahati University. We have with us Professor Utpal Sharma, Registrar, Guwahati University. We have with us Dr. S.P. Agarwal, Director, NESAC. Will soon be joined by Sri P.L.N. Raju, Director, ASSAC. We have with us Professor S.S. Kakatkar, Program Director, SAMEER. We welcome you, sir. And now may I request the convener, Professor Dhrubajyoti Sahoria, sir, to please escort our guest to the dais. And we have also with us Professor B.N. Goswami, P.N. Professor, Guwahati University. May I request everyone to please take their seat on the dais. Sir, please. We begin the proceedings of the inaugural session with the Guwahati University anthem. May I request all to please rise in respect.
Gauhati
Thank you, everyone. We now move on to the felicitation of the dignitaries. May I request our colleague, Dr. Navajit Kumar Das and Dr. Jyotisman Tai to first felicitate our chief guest, Professor P. Chandrasekhar, with a Fulam Gamusa and a memento from Guwahati University. We are pleased to inform you all that we have been graced by the presence of Professor Noni Gopal Mohanto, Honorable Vice Chancellor, Guwahati University. Welcome, sir. May I now request our colleagues to please felicitate our distinguished guest, Sri P.L.N. Raju. I think he's soon joining us. Now, may I request our colleagues to please felicitate Dr. S.P. Agarwal, Director, NESEC, with a Fulam Gamusa and a memento. Thank you so much. Now may I request our colleagues to please felicitate Dr. S.S. Kakatkar, Program Director, SAMWR. Thank you so much. Now, may I request our colleagues to please felicitate Professor B.N. Goswami, PM Professor, Guwahati University. Thank you so much. So now, may I request our colleagues to please felicitate our Honorable Vice Chancellor, Guwahati University, Professor Noni Gopal Mohanto, sir, with a Gamusa, Fulam Gamusa and a memento. Thank you so much. Now may I request our colleagues to please felicitate Professor Utpal Sharma, Registrar, Guwahati University, with a Fulam Gamusa and a memento, please. Thank you so much. We have with us two distinguished guests in the audience. May I request our colleagues to please felicitate Mr. Gautam Kumar Mishra, Member Secretary, Assam Pollution Control Board, with Fulam Gamusa. And a memento from Guwahati University. Thank you, Professor Ruboti Sohoria, sir, for the felicitation. And we are glad to inform you all that we have with us Professor Meenakshi Devi, former professor, Department of Physics, Guwahati University, who was instrumental in setting up the ST radar in Guwahati University. May I request Professor Ruboti Sohoria, sir, to please felicitate ma'am with Fulam Gamusa and a memento. Thank you so much for the felicitation. Thank you so much. And the ceremonial lamp has already been lit, and we are good to begin with the further proceedings of the inaugural session. May I now request Professor B.N. Goswami, the PM Professor, Guwahati University, to please deliver the welcome address.
Good morning to all of you. Honorable Vice Chancellor of Guwahati University, Professor Nanigopal Mohanta. Chief guest of our today's function, Professor V. Chandrasekhar, who is a distinguished professor at Colorado State University, USA, and one among the top radar scientists in the world. Professor S.P. Agarwal, Director of NESAC, dignitaries at the dais, the guest of honor, Professor Mr. Raju, who is currently not here, Director of Assam State Space Application Center, Dr. Joydeep Borua is also not here right now, Dr. Soma Sen Roy, who is Scientist Z and head of Radar at IMD and nominee of DZ IMD, Dr. S.S. Kakatkar, Program Director Samir, all distinguished invited speakers, amongst whom we hope we are happy to see Professor Z.S. Bhatt. Is he around? He is probably not yet here. And all the leading atmospheric scientists in the country which attending this conference, and the members of the invited, all the invited speakers, the members of the organizing committee, the members of the National Steering Committee, and members of the local organizing committee has done a great job, because many of them are not associated. The radar group here is very small, but many of them have no association with radar, but they have put in a lot of work, and their hard work has made this possible. So I welcome them here. Also, of course, we are thankful for the steering committee for hosting this conference at Radar Gauhati University. We welcome them here. Many of them are here. And of course, locally, our registrar, Utpal Sharma, without his support, I think this conference would have been there here. And the members of the press and ladies and gentlemen, it is my great privilege and honor to welcome you to this iRAD 2026. With all the limitations in this state university, and we are going to try to make as your stay here as comfortable as possible, as stimulating and scientifically fruitful as possible. So when the local organizing committee asked me to give the welcome address, I was a little bit concerned, because many times when because they said that you are the senior most person working faculty in this university, so you should give the welcome address. But when people like me start talking, then we start giving gyan. So maybe it will be, and if we start giving that gyan, so don't just attribute to my advancing ages. So the iRAD, I think, this iRAD conference is very significant, especially in the northeast region, because it has this very complex terrain, and understanding and getting observations to understand the processes is very important. So therefore, the organization of this conference here is very important. And I think here, I must tell you a little story. And this conference, and the iRAD conference, has been towards the direction of capacity building in the country for radar technology as well as radar science. And we recognized this for quite some time back, when I just joined IITM, and at that time the Ministry of Earth Science has been formed, and IMD was planning a lot of radars even at that time. So, but it was recognized that the radar expertise, both in technology and science, was very little in the country. And so therefore there is a need to build capacity in this. And that was very much recognized. And we discussed on it, MOES and IMD. IITM actually started a radar meteorology program as a part of our cloud physics program, and we set up this cloud physics laboratory at Mahabaleshwar, and we purchased 2 radars to start capacity building, doing research in both science and technology of radar. So that was the beginning, and that was started with Professor Chandrasekhar's help, because we did not have really good experts, and so I invited him to come to India and spend several weeks in IITM several times. He gave lectures, and then so we started building capacity. Many of our scientists had gone to Colorado University and actually had interaction with him and got training. So through like that, we built up, and I think the radar iRAD is a follow-up of that. So that. But over the last 10, 15 years now, now this thing is trying to build capacity. And but I think this it should unfortunately it should not remain sort of. We have to assess what kind of capacity we are able to build in the country over the years. And I think the iRAD should now sort of introspect and see what we are, where we are going, and what we have are missing, or what we need to do. So one of the things that I see is of course that the training of the people in actually technology is very little in the country, and there are not many people who are actually understand the technology. But more importantly, how understand the technology, how to convert that into actually meteorological signals is a very, very important research problem, and there even we are missing much more. So I think these are the areas how we can improve them, and sort of, I think in this iRAD conference should not simply become a annual affair for meeting everybody and going back and no follow-up action and things like that. I think we should sort of think about that seriously in our discussions in this area. Other thing that I think is that there is a big plan under MOES and IMD to increase number of radars in the next few years to 150 odd in the country. I think this is mind-boggling, and this is great news. And I think, but the biggest problem is the technology itself is not going to help improve our predictions. Ultimately, what do we need? Why do we need these radars? We need to understand the fine scale, temporal, spatial scales of the monsoon precipitation processes, and how to use that knowledge to improve forecast. Ultimately, we need to improve forecast, and this observing system has to improve forecast. And so, unless we can convert the data that we get from this into a research quality data that can lead to a better understanding of these processes and finally improve better parameterization, otherwise there is no really benefit for this, right? Simply getting the data out of the 150 radars, data will be enormous, data will be coming. So we need to train people to how to convert this data into research quality products. And I think there is a great lacking in this area in this country, and we need to build that. Without that, the crores of hundreds of crores of rupees of investment will be futile. So I think that will be waste of public money. So I need to, the iRAD should provide sort of guidance into how this can be done, and so some resolutions you should do. Other thing is that the important thing is that iRAD, of course, is essentially started with understanding. We have a lot of lack of knowledge in the microphysical processes, and therefore focus of iRAD is in the microphysics. But microphysics alone is not going to help us improve prediction. What is most important is how microphysics affects the large scale and how small scale and the large scale interact. And with 150 radars, I think we have a great opportunity to understand how small scale and the large scale will interact, because now it will cover such large areas. But we need to put those radars in a way and also have programs so that this interaction between large scale and the small scale has quantitatively understood, and that is lacking. And so that is, I think, something. And even in the Northeast, we need to do that. We put these radars in a way so that it will be part of a program which will help us to understand this process studies, like interaction between small scale and large scale. Understanding of that leads to parameterizations, improvement of parameters, and improvement of parameterization leads to improvement of forecast. So I think that is where the biggest focus is required. So I think during these deliberations we should think seriously how effectively we can do. But of course, this will all need certain amount of policies with respect to the government, from MOE especially, that the capacity building will not happen unless we invest on capacity building. We are investing on infrastructure, but we are not investing on capacity building. Capacity building means we have to create jobs for which trained people can get placed. PhDs in radar meteorology must get placed. Where is the place in PhDs getting radar meteorology in the country? Not even one. So then, if the PhDs are not there, they will not innovate. And then who will innovate anything new that is required? We should be able to produce many in this country. We should think big, and we should be able to produce many Chandrasekhars in our country. But we are not able to produce, even the last 15 years, one Chandrasekhar. So I think this is where our big problem, where government has to invest. They have to have a program where radar meteorologists will be employed, and they create research which will then feed back into this capacity building. So otherwise it will not happen simply. So that focus has to be there from IMD as well as from Ministry of Earth Sciences. So I hope we can make some recommendation, and hopefully policymakers will follow up that. So without taking too much time, you are all our guests, and in the Northeast, we are very hospitable people, but we have our own limitation. Financially, we are not very resourceful, and unfortunately, this year the most probable, most potential funder ditched us in the last minute. So financially, we are still in a sort of difficult situation, but we'll do our best to make your stay here as comfortable as possible, and so this Northeast is a sort of a very unique place. It is like a mini India. So there is unity in diversity. We have a lot of diverse ethnic cultures, traditions, and practices, and all these live in harmony. And of course, it is a beautiful natural place where we have bountiful rain, and bountiful rain has fertile land, but it also brings disasters, erosions, and there are challenges. So the science and the radar thing can help us understand these processes, and hopefully we can provide better service, meteorological service to this community. I think the service provided to this community in this region is very poor and very neglected, I must say. I'm not sure, you may not agree, but I must tell you that I think I'm very disappointed about the service, the meteorological service, the data, the network that is here is very poor compared to many parts of India, and so we need to improve that. But in any case, if there is any commission, I take responsibility, and we'll try to try to make them as correct as much as possible. And I hope that you will not keep that in mind when you leave Guwahati. But we hope that as much as possible, we'll try to make your stay here as comfortable as possible and as scientifically stimulating as possible. So enjoy take some time off and see Assam not just in Guwahati. Guwahati is not representative of Northeast. Okay, this is a very urban, new urban growing area, and you go out and see the nature and the people of Assam outside Guwahati. And there are many things many places and cultures and people to meet and see. So find time and enjoy yourself, and hope that you will have a great time. Thank you very much, and welcome to Guwahati.
Thank you, Professor B.N. Goswami, sir, for your welcome address and for also outlining the preamble of this conference. Thank you, sir. Now we have with us Professor Noni Gopal Mohanto, Honorable Vice Chancellor, Guwahati University. May I now request, sir, to please deliver the inaugural speech.
Namaskar and good morning to all of you. Professor Honorable B.N. Goswami Dangoria, Guest of Honor Dr. S.P. Agarwala Dangoria, Honorable Director from NESAC, Honorable Dr. S.S. Kakatkar, Program Director, Samir, esteemed distinguished guest, Sri P.L.N. Raju, Director, ASSAC, Honorable Chief Guest of today's program, V. Chandrasekhar Dangoria from Colorado State University, my distinguished participants from various parts of the country and abroad, my distinguished colleague, our registrar, and other colleagues from our Guwahati University. Well, as being the Vice Chancellor of Guwahati University, I do have the honor and privilege to welcome all of you to this 8th conference on India Radar Meteorology Conference, iRAD 2026, being organized by Guwahati University in association with various stakeholders. And today, I am very delighted to see a galaxy of scientists and distinguished participants from various parts of India and abroad. And we welcome you to Guwahati University, the oldest university in the region, which was established way back in 1948. And this conference holds immense significance, precisely because, as we all of us aware of the fact that this is the age of technology. And we have seen only a few days back how America, the United States of America, in a very arrogant and fascist manner, have airlifted one of the presidents of Venezuela, of this country called Venezuela. But nevertheless, however fascist and dictatorial this move may be, this reflects the importance of technology, whether the capturing of Osama bin Laden in Abbottabad, or whether India's Operation Sindoor. All these things reflect the precision and disruptive technology that's going to play a very instrumental role in the days to come. And northeastern region in general and Assam in particular, we have been witnessing extreme air condition and weather climatic condition. Whether be it heat condition or whether it is the occurrence of winter. For example, this time the occurrence of winter is relatively bigger and larger than the last time. And when it comes to humidity and rise of temperature, our northeastern region and Assam, we have witnessed very extreme weather condition. And of course, the monsoon, for example, we are dependent on monsoon. We are a agriculture-driven economy, but the occurrence of monsoon with its erratic nature has caused a lot of problems with occurrence of flood. Flood is a problem that leads to immense suffering among the common people. So this kind of phenomenon like flood, extreme weather condition, this causes a lot of misery and a lot of problematic situation for the entire region. So I believe what Professor G.N. Goswami sir has talked about capacity building, and he has very pragmatically talked about the progressive role of government in terms of more research funding in such conferences and in such infrastructure so that we can address this kind of extreme climatic condition, including the meteorological understanding and predictions. Well, I am not an expert on that. I just wanted to flag off certain issue. Once again, as being the Vice Chancellor, I welcome all of you to this conference, and I crave for the indulgence of your forgiveness in the event of any omission and commission. With these words, I declare this program being inaugurated. Thank you.
Our sincere thanks to Professor Nonigopal Mohanto sir for your encouragement and constant inspiration. We have with us Dr. S.P. Agarwal, Director, NESAC. Professor Agarwal has taken important initiatives towards the effective utilization of space science and technology for various developmental activities of NER, such as natural resource management, infrastructure planning, disaster risk management, weather forecasting, satellite communication applications, ICT-based and governance-related applications, etc. We are indeed privileged to have you with us, and now may I request you to please deliver your address. Over to you, sir.
Thank you, and very good morning to everyone. Sorry, my throat is not proper. Namaskar, Suprabhat. Good morning. It is a deep honor to stand before you at this important gathering of minds dedicated to radar meteorology and to speak especially about the vital partnership between radar and satellite meteorology. In fact, since I am from the Space Application Center of Northeastern region, I thought I should discuss that marriage between the satellite meteorology and radar. So I will touch upon that. First of all, my heartfelt thanks to the organizers for convening this conference and for creating a space where operational meteorologists, instrument engineers, algorithm developers, modelers, and end users can meet, debate, and build collaborations that deliver real benefit. So, most respected Honorable Vice Chancellor of this great university, Guwahati University, Professor Mahanta, our chief guest, Professor Chandrasekhar from a very reputed university of US, distinguished guest of honors sitting on the dais, researcher, scientist, professors, and dear student. We meet at a time when atmospheric extreme, that is heavy rainfall, intense convective storms, coastal cyclones, and rapid urban flooding present pressing risk to lives, livelihoods, and infrastructure. Dear colleagues, this is the time that we have to think of all together and how to overcome these disasters. As you are aware that climate change is happening now. In 90s we used to call there will be a climate change, but now this is the fact. We are living in the era of the climate change, and because of that lot of extreme events are happening. And you may be aware that if you look at the entire country, and there is a report and it says that northeast region is going to affect most because of the climate change. So this is the right time that we are organizing this conference, which is the Radar Meteorology Conference in Northeast region, especially in Guwahati University. Let me discuss something on the radar and the satellite together. So radar meteorology, as you are aware, it gives us high resolution, near real-time views of precipitation structure and dynamics. Doppler capability reveals wind patterns and rotations. Dual polarization improves hydrometeor identification. Dense radar networks enable localized nowcast that are indispensable for flood and severe weather warning. You are aware that Assam is always having flood problems. And you can imagine in future, if there will be climate change, more extreme event will be there. Our two colleagues are here. Dr. Prasad, he is the director of NCM-RWF of Ministry of Earth Science, and Professor Narayanan from NARL, and they are working on it. So, when climate change is happening, it means temperature is increasing. When temperature increases in the atmosphere, what does it mean? It means it is having more water holding capacity. Now, atmosphere will have more water holding capacity. And that is the reason why we will have more thunderstorm, more extreme weather, more floods, more lightning. So, this is the, radar technology plays a very crucial role. Nevertheless, satellite plays a very important role, and there is a need of the hour that satellites and field-based radar should marry. So, what is that? Satellite meteorology provides continuous, wide area coverage, including in the oceans, mountains, remote region where radar coverage is sparse. Satellite sensors offer multispectral information on cloud microphysics, water vapor, surface temperature, and large-scale circulation pattern of the atmospheric wind and vapor. They are essential for synoptic context, early detection of developing system, and climate scale monitoring. Now look at the northeastern region. We have a mountain regions of Sikkim and Arunachal Pradesh. We have a hilly region of Nagaland, Manipur, Mizoram, part of Tripura. We have a plateau of Meghalaya, and of course we have a plains of Assam. See, all kind of geography is there. Meteorology is totally different from place to place. If you want to predict what kind of weather will be there, the algorithm in Sikkim will be different than algorithm in Assam. The algorithm in Meghalaya will be different than algorithm in the Tripura. So, there is a need to discuss this very important topic. What kind of algorithm is going to develop, we have to develop so that we can forecast. How many radars are required in northeastern region? I am well aware that IMD is having many radars, but are they sufficient? Whether we have to think of it. Probably after this conference, we can give the recommendation that how many more radars we need for northeast region for such type of climate change scenario. So now, when fused intelligently, radar and satellite data give us the best of both worlds. The spatial and temporal richness of the radar with the geographic completeness and spectral details of the satellite. So what will happen? Once we will have this, for a country with a long coastline, as you are aware, complex topography, space, I have already told you, for the northeast region, it is valid for entire country, and a monsoon-driven agriculture economy. Remember, very, very important thing. You are an atmospheric scientist, weather scientist, but whatever you are doing, it is really helping for two very important securities of our country. First is the food security, and second is the water security. So, a monsoon-driven agriculture economy we have. Rain-fed areas are there. Radar satellite partnership is, it will really benefit the society. Better integrated observation mean for earlier and more accurate cyclone and storm track detection. Second, improved quantitative precipitation estimation. It will help us in flash flood and urban drainage forecasting. As you are aware, and some of you are, many of you are from Guwahati, you know this time we have a very bad, flood, urban flood, especially in Guwahati. Many people had a trouble during that time. Everybody is aware, those who are sitting and those who are from Guwahati. So this improved quantitative precipitation estimation with the marriage of two, radar and the satellite, will help in this. Second, enhance input to high resolution numerical weather prediction and hydrological model. Professor Prasad is there, he understands very well that how improved instrumentation and the satellite technology will help us in better for weather forecasting. And support for agriculture, water management, aviation safety and renewable energy operation through dependable, impact-oriented forecast. Now, there are few more technical things which I want to dwell upon it today. So, several areas deserve special attention as we plan the next decade of capability. One, data fusion and assimilation. Seamless algorithm that ingest radar reflectivity, polarimetric moments, satellite radiance and derived products into model will rapidly improve forecast skill at both short and medium range. We need both short range and medium range. Now another technology which everybody is talking about it, that is machine learning and AI. It's a need of the hour. From eco-classification to probabilistic nowcasting, AI can accelerate feature extraction and translate observation into actionable guidance. I always talk, we are very good in prediction. Even professor from the USA, Professor Chandrasekhar, he understands. We are very good in prediction. Now this is the high time that we have to think for not only prediction, but prescription. Yes, this is the prediction. Then what should be the prescription for betterment of the society? So this is the high time. And AI is going to help a lot in that. Higher temporal and spectral remote sensing is the need of the hour. The new generation of geostationary satellite, polar satellite, combined with phased array and rapid scan radar system will offer denser, faster observation. Okay? But only one thing you remember, they demand smarter processing pipeline and more computing power. And for that, we need really very high-end HPCs. Those who are working in atmosphere, they understand the importance of HPCs. And of course, interoperability and standards, open data formats, quality control protocols, and share validation framework are essential to scale multi-sensor product across agencies. So some of these points I thought I should dwell upon it to tell you this conference is so important, and outcome of this conference could be, one of the outcome could be in these directions. Already Professor B.N. Goswami has touched upon various aspects of capacity building. So this need, there is a need of capacity building in this region itself, I should tell you. We are having good human resources here, but there is a need of capacity building. Our professors, our scientists, our researchers, especially our young minds, those are sitting backside, they need capacity building. And this is the duty of the great university like Guwahati University, that we build the capacity in this region, sir. Honorable Vice Chancellor, I request, there is a need of capacity building of these young minds in the atmospheric science, in weather forecasting. Collaboration is another other important point. I always feel every scientist work in silos. I hope our dignitaries must agree with me. This is the big problem, and this is the time we have to work not in silos, but in collaboration. So, and especially in weather, tracking weather-related risk requires partnership between national meteorological services, space agencies, universities, industries, between hydrologists and meteorologists, between neighboring countries that share airspace and river basin, etc. Conferences like this catalyze those partnerships. Let us leave here with concrete plans for joint experiment, data share arrangements, and training exchange. Finally, I urge all of you, researchers, scientists, professors, even operators, to remember that ultimate metric of success is not your paper, research paper. Ultimate success is what your research is impacting the society of the region. That should be in your mind. How many more lives we can save? How much economic loss we can avoid? How much better are our farmer decisions because of improved forecast? So this is what I want to tell. Concluding, radar and satellite meteorology together form the observation backbone of modern weather and climate service. There is no second thought about it. The science and technology we develop here will determine how resilient our communities are to the future extremes. At the end, again, I congratulate the organizers and I wish you productive sessions of this conference will really save the future of this region. Thank you very much. Jai Hind.
Thank you, sir, for your address and for contextualizing the importance of radar technology in Northeast India. Thank you so much, sir. We have with us Dr. S.S. Kakatkar, Program Director Samir. Dr. Kakatkar is a prominent scientist in India specializing in microwave technology. He is currently a Program Director for Industrial Solution at the Society for Applied Microwave Electronics Engineering and Research, that is Samir, Mumbai, under the Ministry of Electronics and Information Technology, Government of India. May I now request Dr. Kakatkar sir to make a brief address to the audience.
Thank you, sir. Respected members on the dais, participants of this conference, friends, a very warm and good morning to all of you, and a very happy New Year 2026 to all of you. May this year be full of scientific discoveries and innovations. I feel honored to be a guest of honor here. Perhaps, I don't know, DG Samir should have been here. Samir being one of the sponsoring organizations for this conference. But as Professor Goswami said, perhaps he thought that I am one of the senior most, oldest member associated with ST radar that was installed in Guwahati University and still serving in Samir. So maybe suggested my name, and thank Guwahati University and organizers also for accepting its suggestion. I also feel that I am representing here all the other stalwarts who worked in ST radar. Most notable among them, they are either superannuated or not working in Samir, like Dr. K.P. Ray, who was the chief investigator for this project, did most of the work, Dr. Agarwal, then Abbengar sir, and all our other colleagues who either contributed in maybe antenna or RF side, signal processing, or installation, testing. Even the contract staff and all were recruited here. I remember that it was during such times, only December, January, that we did the phase calibration for the radar, and that too at night, because we wanted to avoid working in the morning to avoid the phase variation in the morning. So in the night, we did all the phase calibration. Of course, I was in one of the control rooms, but these our young junior colleagues and these contract staff, they were in the field doing phase streaming or like that. Sometimes we also used to go and discuss with Professor Meenakshi Devi or Barbara sir. I even had the opportunity to meet former vice chancellors, Dr. Mrunal Hazarika, then Handik sir. So, I mean, water under the bridge, but just remembered after coming here all those things. So, okay, let me wish the conference a great success. and hope that the papers presented in this conference inspire other researchers in the field, leading to maybe prediction and prescriptions, as Dr. Agarwal said, and remedy social impact. Thank you.
Thank you, Dr. Kakatkar, sir. We now move on to the inauguration of the Book of Abstracts. May I request the guest of honor, Dr. S.P. Agarwal, to do the honors, and may I request our colleagues to please assist, and may I also invite Professor Trubos de Sohoria, sir, the convener, to please join our dignitaries on the dais. So may I now request our guest of honor, Dr. S.P. Agarwal, to please inaugurate the Book of Abstracts. Thank you so much. We now move on to the keynote address. We have with us Professor B. Chandrasekhar from Colorado State University as the keynote speaker. Now may I request Navajit Kumar Das from the Department of Anthropology, Guwahati University, to please introduce our keynote speaker.
Professor V. Chandrasekhar is a renowned radar meteorologist and distinguished professor of Colorado State University, USA. Professor V. Chandrasekhar is internationally renowned for his pioneering work in polarimetric radar observations of the atmosphere, with deep expertise in radar system design, radar network development, DSP design, RF communication system. He has significantly advanced weather radar technology and its application atmospheric science. His research spans image processing, neural network application, and large-scale system simulation. And he has organized and participated in 6 major multi-agency national level experiments involving radar, aircraft, and ground instrumentation. As an active experimentalist, he conducts specialized experiments to collect in situ data for validating new techniques. He is also co-author of 2 most popular textbooks, namely Polarimetric and Doppler Weather Radar and Probability and Random Processes. He has served as PI or co-PI on major national programs including NASA, TRM, and GPM missions, the ACTS program at Colorado State University, and the DARPA NGI program. So now I request Professor V. Chandrasekhar sir to kindly deliver his keynote address.
As Professor Chandrasekhar sir is getting ready, I have the honor to inform you all that the Book of Abstracts, they are available at the registration desk. Our esteemed participants may accordingly go and collect them. Thank you so much. Laptop to connect. Sir, your laptop. I will use this. You'll be able to use this? Yeah. All right. So you have a flash drive, sir? Yeah. Pen drive पर लगा लो. It will be visible here, I guess. It will be visible here. It will be visible here, I guess. Okay. Sure, sir.
Can you go to Google search? Google search.
You want Google?
No, Google search. Yeah, open that.
See.
Can you open? How do you find the book announcement? Can you? I wanted to show it.
Okay, is this connected to internet?
Yeah, one second.
It is not connected to the internet.
Oh, it's not connected. Okay, then don't worry. I just sent you a message.
Oh. You can't connect.
it's here. Bukawara. Oh, not this. Yeah, yeah. It's not on. Hello? Hello, can you hear me? Okay. It's okay. Yeah, yeah. Okay. First of all, it's a great honor and privilege to be giving a talk in this conference, and especially about complex terrain. And it turns out that this is one of the active area I'm working on that is very relevant to Guwahati and this region. So, you know, I didn't realize that I was, there is some, once I tell you, it'll be obvious. I was walking around yesterday, and then I was very pleased to run into a specific location. So I will start this conference with a very simple statement, which as soon as I say, you will all understand. At least local people will understand, you know what I'm talking about. Oh, here. Okay, can you hear me? Then I will start with Ami ek jajabo. So that was I am actually a fan of Bhupen Hazarika, and I was very pleased, and I didn't realize I will run into the to that memorial place here yesterday. I spent time, and then so that that's almost that song's meaning. It's like I am a traveler. I am missing my home, but at the same time, I am also feeling like I'm everywhere, and so on and so forth. And then he connects Ganga and Mississippi. So it's so well connected. So for those of you who are not from here and visiting, so just at the end of the University Road, there is this Bhupen Hazarika Museum. So please go visit. So it was very nice. Thank you. So that's why I wanted to start this whole talk with Ami ek jajabo. Okay, now let's get back to radar. Let's get serious. So complex terrain it's like a big challenge for radar. And why are radars, like the previous speaker talked about satellite and radar. So sometimes when we wanted to build a satellite network and radar network in the US and especially X-band radar network, somebody asked, we have satellite looking down, so why do we need radar? Satellite is able to see everywhere. Why do we need radar? So among the young people in the audience, anybody knows the answer to this question? If satellites are looking everywhere from above, why do we need radar? Somebody just there's no wrong answer, please. Okay. 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 Any other answer? Yeah. Yeah. There was one other answer in the back. Can you speak up? Okay. Okay. So essentially, oh, you want to answer too? Go ahead. See, all these answers have already filled the question of radar meteorology, because most of these answers are correct. So all of them had one part of the answer. There are two big issues. One is satellites. Most of them are what do you call, not active instruments. There are few instruments where the radar type of beam can go right through. Most of them are Viz and IR, so they just see mostly from the top the net effect of what is going on, and that's the first thing. Though there are radars on satellite, but those radars are all on low Earth orbits, which means they are constantly going around. And you come back to that same place once in a few months, or sometimes a month, sometimes few weeks. So that's why you get just snapshots. Whereas radar is sitting here continuously watching the storms as it's coming to you. So this is like, one is like a spy camera, another one is you're building a fort, and then you're just looking through the telescope who's coming to, the big storm is coming to attack you, and so on and so forth. And the resolution and all that stuff is there. I'm glad that we are all in the zone trying to understand. But in spite of that, if you have complex terrain, right in front of you, there is a huge mountain. No matter what, you can build the biggest radar you want, it is not going to penetrate through the complex terrain. So there is what do you call, there is the truth, inconvenient truth. That's the first thing. And also when you go very far away from the radar, there is another inconvenient truth called Earth's curvature. So coming back, so all these things was happening. In US, a very textbook definition of complex terrain location is the San Francisco Bay. So there is mountains on both sides, and in the bay is a beautiful place. It's just like here. But the problem is that's also a highly populated place, very high value real estate. All this Facebook and Google and everything else is there. And so it's very important to critically monitor that region. And so that's why we started this big project with a collaboration with NOAA, State of California, and the US government and everybody else. It's a very collaborative project. So what's the motivation? And weather radars, I mean, this is like the map of where all the weather radars are located. There are about 150 radars in the US. But if you think about it one way, and everybody has talked about India is going to deploy about 150 radars, and then the area of US is 3 times the area of India, which means India will have 3 times more dense weather radars than what US has. That's one way to slice the problem. And the thing is, a lot of the US, I mean, this is Colorado. The whole state of Colorado is about, because 3 are in the border, it's got about 2-3 radars. That's not much. And the state goes about 400 miles north-south and 600 miles east-west. It's a huge state. So not every place has coverage. And this is the Bay Area, and I will talk about that. So due to deployment location, the existing National Weather Service radars look too high in the atmosphere. And then radars suffer beam blockage due to complex terrain. So, but they could deploy the radars only where we could deploy. Okay. So in spite of everything you have, this formula of one radar, one type of radar will blanket cover the nation, that concept doesn't work. So we need to augment with other types of radars to fill the gap. So we had a huge research project called CASA to evaluate this problem and then develop technology for smaller and more compact radars, which we did quite a while ago. But another important thing is, over the past several decades, weather radar research has produced a rich toolkit for processing both single and dual polarization radar observations. It's moved from research to operations. And then all sorts of progress have been done, but translating these advances to sustained operational use is not straightforward, because, as they say, research is like washing clothes with hand. Operations is you're using a washing machine. So you want to put clothes in the washing machine, push some buttons, and you want it to work. You don't care what happens. Whereas when you wash with clothes with hand, you can be careful, you can use delicates nicely, and it will naturally come to you. So the real-world deployments must contend with the diverse meteorological regimes, various hardware configurations, and practical limitations, such that you may be putting the radar right at the foothills, which means you can see only one hemisphere. The other side you go, you just stare into the mountains. So you need to deal with all these issues. And so we need to take care of all this. That's one part of the story. Second part of the story is most of the precipitation comes for California comes through what is called as atmospheric rivers. Those of you in the back, if you cannot hear me, you can come forward. Way in the back, there is a lot of room in the front. Please come forward. You can come in the front. Yeah. There are people sitting extremely in the back. So the atmospheric rivers have this problem of, you see, it just lifts precipitation, and then the complex terrain, yesterday when the radar school I talked about it, the complex terrain produces intense, the microphysics at collision coalitions actually increases the rainfall as you get close to the mountains, and that produces a rush of rainfall. And I talked about this and then showed this. And this is the valley. This is the long-range radars. I have shown cartoon of a couple of two long-range radars sitting here. One long-range radar will just look over the mountains. Another long-range radar will look way up, and most of the times it looks at ice. Or if it's shallow precipitation, it will look above the precipitation, and the valley rain will not be measured accurately. These are all problems. So we need to improve the situation, and then what we have done is we've gotten a combined set of radars, small radars deployed in the valley, while they work with the big radars and produce a composite product. And so I wanted to show you very specifically what these radars are. KDAX is one of the Weather Service radars. And then KMUX is another Weather Service radar, KBBX. And these form these big white circles. These are the big S-band radars. Then this is the coast. This is Sonoma County, and then there is San Francisco. Imagine if you have a radar, and if you have to deploy a radar in San Francisco, it's not easy. You cannot find a spot to put a radar in the city of San Francisco. It's next to impossible. So you have to put radar where you can put the radar, and then just work with the configuration. So that radar is not shown here because we deployed it just a few months ago. And then there is this is the bay, and this tip is San Francisco. This area is San Francisco Airport. This is East Bay. There is a radar in East Bay. This is Santa Clara. That's where San Jose is, and this is Santa Cruz. So This is very highly populated area. That's the Silicon Valley, which is high-value real estate, and that's where we have deployed this AQPI system. Now, what you see here is the terrain, and then this is the height in mean sea level in meters. So now let's go further. Did something change? Something changed here. Oh yeah, these are the three NextRad radars, KBBX, KDAX, and KMAX. And then there are these X-band radars, and these things are being put together. Now, IITM is working on a similar problem. They are putting a network of 4 X-band radars. When I said it's very hard to put a radar in San Francisco, and I think they have civil the same thing. Oh, you think it's a problem in San Francisco, it's a problem in Bombay too. Right? It's very hard to find a place because nobody wants radar in. The problem is, okay, then you make a deal with somebody to put a radar on a tall building. You just wait another 2 months, somebody else will build a tall building taller than this next to you. Then one side there will be complete blockage. So you need to worry about all these issues, which has got nothing to do with radar meteorology. Okay, I think it's starting to. So when you start putting these things, these radars are not all on the ground. They're all in a 3D structure. So Santa Rosa is 40 meters above the ground, and then East Bay radar is 600 meters above the ground, and Santa Clara is 138 meters. And then there is a new C-band radar that we have put to provide an umbrella as well as coverage over the ocean to watch the atmospheric rivers coming in. That's about 450 meters. So that C-band radar has just been installed. Okay. This is you take the radar, and then how do you quantify the complex terrain? So you have this KBBX radar that's in Sacramento, and its altitude is only 67 meters. But you see this is the height above MSL of the lowest elevation free of orographic blocking. So if you are close by, then when you have green, there is less blocking. But if you go further away, then the lowest elevation you see is starting to get into numbers like 4 and 5 kilometers. So the lowest radar observation you see is 4 to 5 kilometers, which means, and all these areas with complex terrain, like I told you, it's about like this region are the Uttarakhand floods. There is a lot of variation in precipitation in the lowest 2 kilometers. And you need to observe that to get the rainfall right. Here is KDAX, that is, and then you see this, that at a height of 43 meters. And as you go farther away, because of the blockage at different regions in the valley, you don't see low elevation precipitation at all. Let's keep going. This is KMAX. KMAX is a very interesting situation. The height of the radar itself is at 1 kilometer. And many times when you have warm rain coming, the whole rain layer is only 5 kilometers. Many times you just look over the rain as you go far away. Here you can see, because the radar itself is very high, most of the region doesn't, the coverage is much higher. This is the statement of the problem in complex terrain. So how do you take all this and put it together? So combining the best coverage from KBBX, KDAX, and KMAX, then you can get some sort of a picture like this. And you can see, you see less of these brown colors and more of these blue colors, which means you're seeing closer to the ground. That's the first thing. Okay, now let's look at the rainfall process in the San Francisco Bay Area. I used this cartoon yesterday to talk about this. Essentially, at low elevation, you have this predominance of collision coalescence process, and you go above that, you have aggregation and rhyming. Okay? Essentially, we need low-level observations to get insight into microphysical processes to improve rainfall estimation. So there are essentially two types of rainfall that's prevalent in this region. One is cold stratiform rain, which is bright band. You can actually observe the bright band, like you see here. And then the ice process is governed by this Bergeron process. And then ice crystals are formed in cold regions, and then they melt and fall, essentially fall, and then as rain. And then this warm orographic rain driven by collision coalescence, and this is facilitated by orographic enhancement. So on the top you see this is Doppler velocity, and this is reflectivity. This is stratiform rain, and then you see that the clean bright band. And then here the ice crystals, suddenly they will melt, and then you see a lot of increase in velocity, whereas orographic warm region, that is the velocity distribution is very different. Okay, now we put this gap-filling X-band radars, that's what they call here. You put these gap-filling radars, suddenly the coverage diagram has become much better. You see a lot of these, there is hardly any brown in this, except when you go deep into the ocean in the San Francisco Bay region. So this is, we are basically going through a design problem of deploying radars in complex terrain. So one quick example is, and this region is Sonoma County radar, which is Santa Rosa, and this is KDAX. So if you look at it through a cross section here, and then plot the complex terrain of mountains and hills, and you see here, you put a radar that is Santa Clara radar, and then it looks well in the basin, whereas the NextRad radar, by the time it looks in this region, the minimum beam is about almost 2 kilometers high. So it doesn't see the rain properly. So this is the cross section looking in this direction. So what are the advantages of these radars? They can see closer to the ground, and then higher resolution. Why is it higher resolution? Because we don't do this full scan of radar, the scans that the National Weather Service does. And I think anybody from IMD here can tell me what is the scan cycle of Weather Service radar here. It's about 10 minutes. Sorry? 12 minutes. There VCP 12, when the presence of precip is like 6 minutes, whereas our next X-band radars actually provide continuous update every 2 minutes. And 6 minutes, I don't even know why somebody is doing 12 minutes, that's a different question. Even 6 minutes, I bitterly complain. If you want to know how long 6 minutes is, when you have a flood, when you have water running, at that time you want to see when is the next update coming from the radar. And then you tell somebody, oh, the next update will come after 6 minutes. That's a long time. You want to know how long is 6 minutes? I told you this perhaps before. Many of you have microwave oven, right? You want to heat something in the microwave. You open the thing and put it inside and put heating for 1 minute, and you just stand next to it. That's a long 1 minute if you're just waiting for it. So if you're waiting for an update, 6 minutes is a long time, especially when there is floods. So 2 minutes is the number I have formed over a period of time, and that you need to get update every 2 minutes. In fact, it's even better if it's less than that. Anyway, so we check on updates more frequently, and I will show you what's the story of that. Okay, What you see here is a narrow cold frontal rain band seen by the Sonoma County radar. And then it's simultaneously seen by the NextRad from KDAX. Narrow cold frontal rain band is how the intense collision coalescence rainfall forms on the ground, and then the rainfall is focused, and there is extreme rainfall here. But I'm going to play this again. What's the update time on the left side and the right side? Oop. It's not playing. Did you see the animation in that before? What's the animation on the left side and right side? I guess it doesn't. There's something missing here. Let's go play. Did you see that thing move first time? You see how frequent the update is on the left picture and how frequent is on the right side. So that's because this is 6-minute update, this is 2-minute update. And also, you cannot see the high intensity rainfall on the right side. This is the problem with weather service radars. Okay? Okay. So this is, okay, we can skip this. This is, oops. Okay, it has a mind of its own. It's running. So composite visibility, when the X bands are considered here, this whole region, XSCW, that is Santa Clara Valley, that's called as the Napa Valley. And have you heard of Napa Valley? That's the wine country. It is very rich real estate producing wine, so they are very weather sensitive. And this side is Santa Cruz and Santa Clara. The other end is Silicon Valley. So all the way from high quality wine production to Silicon Valley, everything is being covered by these radars. So, and with this, we have reduced the things. So when you finally deploy all this, we make a hybrid network of radars and X-band that operate at different frequency bands, range extent, sampling geometry, everything. And AQPI X-band has higher spatial resolution than, I have no idea who that is, and a spatial resolution than NextRad, and they have different sampling volume, and they are not synchronous. They don't operate in a very synchronous way. So you have to take all these and then merge the data together in a meaningful way. What are the challenges? Basic science and physical considerations, there is beam blockage, range resolution, sampling cadence, okay? And then asynchronous scans and radar calibration. I don't know how to shut this off. And then the other one is physics. DSD variability, attenuation correction, and vertical profile. Vertical profile in complex terrain is one of the most important things. This is all science. This is engineering. So when we deploy radars in complex terrain, science and engineering are equally important. You can't just solve the science and then say, I have figured out the warm rain processes, I know the raindrop size distribution areas, and then you can just bring it to the front. Whereas the engineering considerations is how you sample. You don't sample synchronously because I mean, these radars are being run by 2 different organizations. You'll be very lucky if these 2 radars are even synced to the same clock. So you have to be very careful so when you do all these things together. Finally, we produce a composite products which is 250 meter by 250 meters with a 2-minute update. Okay? That's the product we produce. So the hybrid network needs to be integrated. Long time ago, I wrote a paper, how to network radars. I think the title of the paper is Theory of Weather Radar Network or something, in which I made a nice model that you can put it in triangular and rectangular, hexagonal deployment paradigm and all that stuff. That's just an idea, okay? But none of that theory fits here exactly. But nevertheless, the theory was a way to understand. And then these here, in this theory of radar network, all radars were identical. Nowhere close to identical is these radars. So we need to deal with all this. Okay, let me see if he can do the same magic here. Here is a hybrid network. There is a lot of, as you say, masala mixing that has happened here. And this is a composite produced every 2 minutes between 18 to 24 UTC. And this is an operational product that works like clockwork, or that's how you say, like washing machine. This is data from all radars. If you are not careful, before we reach this stage, one radar will turn like this, another radar will turn like that. It will never look so smooth. And you can see a nice line that is seen as a composite from all the radars. And this is basically a composite with 2-minute update time. And it is made with all the NextRads. So the main thing is NextRad volume scans are repeated every 6 minutes. X-band is every 2 minutes. Attenuation correction has to work. If attenuation correction is not perfect, and then you try to merge it with the S-band, you will come like this will come like this, suddenly there will be a step. It is like a building from 2 different sides, and then if you are not paying attention, the pavement is not leveled. You will deal with all sorts of issues. Those pavement is not being leveled. You don't need to be a scientist. Anybody can look at the picture and, hey, something is wrong with this. So it will be very embarrassing. So that type of processing technology is important. Okay, a lot of the times when you deal with this, and then let's say you go to IMD, first thing they will say, hey, IMD radars are able to see the same thing. Why do you need these radars? Okay, so this is Weather Service radars only. You made a composite with this. Because of all the blockage and everything, there is no timer here. How much time I have left? So I have to finish now. Okay. Let me fast forward. Whereas this is the value of having this radar. This area is completely missed by Weather Service radars. And then I can show many examples like this. And in these radars, and then this is low resolution, and then this is beam overshooting. All these things can be seen. So this is like very routine now, very operational. Okay, the next important thing is, this is Sonoma County radar, and you can see with time, the vertical profile here. The vertical profile is going with increasing reflectivity with ground. That's collision coalescence. Whereas you see the same with NextRad radar, you see reflectivity decreasing. That looks like you are having evaporation. This is the problem of not observing close to the ground. Even the physics is not being captured properly. So the bottom line is essentially you get much better rainfall. Since I have to finish, I'm going to run to the end. And we produce the best rainfall rate with the lowest error with this composite system. And then there is one more thing. Nobody will believe if you said that we saw a tornado in California. Normally tornadoes are supposed to happen somewhere in the middle plains, like Mississippi, Kansas, and so on. This is Santa Cruz, and this is X-band radar at 2136, 2138. You can see every 2 minutes. And then this is X-band Doppler. This is NextRad. You can see a beautiful hook echo. Can you see that? That's a tornado. A lot of people saw it on the ground, and then they said, no, tornadoes don't happen in California. I think you are dreaming. You are smoking something wrong. That's what people said. But then it just disappears. You see, the whole cycle of this is 4 minutes. Whereas NextRad, they don't even have observations, and this is how NextRad sees. And this is, everybody talked about high resolution. This is the high resolution picture with the X-band radars, and you don't see that. So like this, you can keep on showing a lot of examples of why you need this gap-filling X-band radars. So summarize, so the AQPI network, we have actually figured out a methodology when you have disparate radars. How do you actually combine these things together? It is not as simple as take reflectivity from here, take reflectivity here, and just put it together and press it with some istri and it'll all work out. It doesn't work like that. You need to account for the engineering problems and the physics. And then, so the operational integration of short-range X-band radars with the weather service radars, how do you do that to produce operational products is demonstrated. And the X-band radars are used not only to serve gap filling, but they actually improve the rainfall estimates. And the transfer of local microphysics information from X-band at low level benefits the whole network. Because you see that, and then you transfer it to the whole network where the low level thing is not seen. And so overall this, because a lot of the times, people thought that how do you show that it is useful operationally? That's the main purpose of this project. And thank you. Do we have Q&A or we have to kill? Question? Anybody wants to ask a question? Yes, please. I think he needs a mic. Yes. He's coming.
Yes, thank you for giving very elaborate explanation how you can mix that X-band radar and NextRad, probably S-band radars. In India, we have a very big problem of the cloud burst or heavy rainfall intensity, rainfall for a shorter duration, for a shorter area. It happens in Uttarakhand, it happens in Himachal Pradesh. They are the two most affected. Now, IMD as well as other agencies, they are working on it, what kind of radar we need. So what is your opinion, whether we should go for, of course, three-dimensional radar system we should develop, that is fine, that I understood from your lecture. But do you feel still we need NextRad and X-band combination, or only X-band will do? Thank you.
Okay, that's a very loaded question, but it's a very good question. You know the meaning of a loaded question, the very heavy question. So first thing is, you need radar. Let me rewind even back. I'm not joking when I make these statements. You need radars that work. Seriously. I've seen a lot of radars that are procured, but based on promise of tender, and they don't work. And then we are stuck with the process. So if we are buying, let's say, placing, and process is it's available in the US also. If we are going to buy 50 radars or something, I would just look for delivery of 1 or 2 systems and test them out. So in that environment, that radar might have worked in Delhi, but if you put it in this Uttarakhand environment, and sometimes power failure happens frequently, it may never come up again. And do we have that type of other infrastructure other than radar? I deal with this all the time. The biggest problem I deal with this my radars is not about the radars, it's the power failure. Because if the quality of the power is bad, and then if the radar fails, what it takes to bring the radar back up, that's the one thing. That's even engineering and this thing, it's economics. Then the next thing is you get X-band radar. We need to do a study of the terrain using digital elevation model. This is all that terrain picture I have done with digital elevation model. Digital elevation model, and then map the place depending on the distance. If you have a lot of clearance, then if it's more than 50, 60 kilometers, you can even put 1 C-band and get away with it. So I did a design study like that. But if it's closer than 40, 50 kilometers, it's better to put 2 to 3 X-band radars in strategic locations. But what will happen is if you put it inside the valley, these radars won't be able to look at what is coming in. So only to help with that, we need these big, long S or C-band radars. You would have them outside the valley. Then you need a combination of the two things. That's what would help in the Uttarakhand area. It's not just X-band, it's a combination hybrid. That's why we put a C-band radar, because you need to see what's coming. And then to do this cloud burst, this 12 minutes will never work. I am telling today to IMD, even weather service 6-minute cycle update will never work. Maximum you can allow is 2-minute update time. That's very important. Well, you call it as cloud burst. We call it as collision coalescence. That's like the cool name for it. So that collision coalescence has to be observed. The lowest vertical profile has to be observed. I showed an example that you use the long-range radars. They show different vertical profiles. So that increase in reflectivity with ground, that is the cloud burst. Suddenly the light close to the mountain, yesterday I was showing it in my class, the rainfall rate will increase by a factor of 10 to 100. That we like to call it as cloud burst. Very good question, thank you. Yeah. Once
Wrap up the inaugural. Sincerest apologies, sir, because we have a lot of sessions coming up. We only wish that we had more time for this deliberation. So a sincerest thanks and gratitude to Professor B. Chandrasekhar for your insightful deliberations, sir. And we hope to have your feedback, your observations throughout the day as we go ahead with the sessions. Thank you so much, sir. And may we now request you to please take your seat with the audience. And extremely sorry for not having further questions to this session. Thank you so much. So may I now request Professor Utpal Sharma, Registrar, Guwahati University, to please propose the vote of thanks.
Good morning. Honorable Professor B.N. Goswami sir, Honorable Vice Chancellor will left the program. The guest of honor, Dr. S.P. Agarwal, Director NESEC, Dr. S.S. Kakatkar, Program Director Samir, who is associated with ST Radar, and we have a lot of conversation during last couple of years regarding the upliftment of the ST radar. Then the exciting talk delivered by V. Chandrasekhar from Colorado State University. First and foremost, I express our deep gratitude to Professor B.N. Goswami sir for his warm and inspiring welcome address, which set the tone for today's proceedings, and also his mentorship for conducting such a big event. We are sincerely thankful to Honorable Vice Chancellor Guwahati University for his inaugural speech, whose words are always encouragement for, and which reaffirmed the Guwahati University's commitment in advancing scientific research and innovation. Our special appreciation goes to our guest of honor, Dr. S.P. Agarwal, Director ANISEC, for his gracious presence and for inaugurating the book of abstracts, and also the other kind of support from ANISEC Meghalaya. Dr. S.S. Kakatkar, Program Director Samir, for his insightful remarks, and keynote address by Professor V. Chandrasekhar, Colorado State University. We would like to thank Mr. Gautam Kumar Mishra, respected Member Secretary of Assam Pollution Control Board, for his gracious presence today, and also the support for our abstract volume. The present abstract volume is published with the gracious support from APCB, Assam Pollution Control Board. We also express our deep appreciation for the presence of Professor Meenakshi Devi, former Professor, Department of Physics, and also the leader in establishing the ST radar facility in Guwahati University. I also wish to acknowledge the sponsors and partners who made this conference possible. In particular, we extend our gratitude to Ministry of Art Science, Indian Institute of Tropical Meteorology, Pune, State Bank of India, Astra Microwave, Samir, Assam Pollution Control Board, ANISAC, STI-GON Radons, Farm Technology, Numeric, Praya Infotech, Cybernet Solution, SCI-COM. Professor Takasaki and Professor Oshio from Japan have just arrived at the airport. We also thank them for their presence in the conference. I also like to thank Secretary MUES, Dr. M. Ravichandran and Soma Sen Roy, Head IMD Radar Division, who has joined us yesterday for the inauguration of the Radar School. I thank all the delegates, researchers, and students who have joined us from across India and abroad. Your participation enriches this platform and strengthens the collaborative spirit and which defines the iRAD. I also extend my appreciation to the organizing team at Guwahati University, whose tireless effort have brought this event to a success. Finally, the media people present here, all the members of the Works Department of Guwahati University works day and night tirelessly to make this event successful. The security staff, the cleaning staff, all the LOC members, actually in my vote of thanks I have not mentioned their names, but it is there in the abstract book. So the list of the abstract book where the LOC members' names are there. So I appreciate your tireless effort for making this event successful. The director and staff of Guwahati University Press for making a lot of printing activities for this conference, working day and night. The technical persons for controlling the audio visual for this conference. I express our deep concern, deep appreciation for their support. With these words, I once again thank each one of you for your presence and contribution. Thank you.
Sincere thanks to Professor Utpal Sharma sir, Registrar Guwahati University, for proposing the vote of thanks. This brings us to the close of the inaugural session, but before we break for tea, we have a few announcements. First, we will have a group photo. So before we disperse for tea, we'll assemble here for a group photo. Then secondly, those who have not collected their ID cards are requested to please do so from the registration desk. And you are also requested, those who have not yet collected, to please collect your food coupons from the registration. And some of the participants have to go to the new academic building for the parallel session. May please note that there's a bus waiting outside. Our volunteers will accordingly guide you to that venue in the new academic building. And the high tea for us is being served in the food court. But before we disperse, we all congregate for a group photo. Please. Sir. May I request all our dignitaries to come to the dais? So. Please, sir. So. Thank you, everyone. And may I now request everyone to please join us for high tea, which is being served at the food court. And may I request everyone to please come back to the auditorium in about 10 minutes' time, as we need to move on to the first technical session. With these words, thank you, everyone, for your participation. Thank you so much.
Hello, hello.
May I request all participant friends to please settle down. We are just about to start the first technical session of the day. Yes. Yeah. This is for information of all concerned that the poster and interactive session, the hall has already been inaugurated, just adjacent to this particular auditorium. So those who are intending to present their posters may please go and put them accordingly in the hall, in the slots provided. The hall has already been inaugurated. You may please go and display your posters. Thank you. So, welcome back after the tea break. We are now set forth to begin the first session of the day one of this conference. The session is on wind profiling radars. And for this session, we have a host of papers preceded by the lead talk by Dr. T. Narayana Rao. The chairpersons for this session is Dr. Sanjay O'Neill Shaw and Dr. V.S. Prasad. May I now request Professor Chandana Sharma ma'am to please escort our chairpersons and the speaker to the dais. Our chairpersons, Dr. Sanjay O'Neill Shaw is the director of the Regional Meteorological Center, Guwahati. Our co-chair, Dr. V.S. Prasad, is a prominent figure in India meteorology, serving as the head of the National Center for Medium Range Weather Forecasting, NCMRWF, under the Ministry of Earth Sciences, MOES. Our speaker here today, the lead speaker, is Dr. T. Narayana Rao. May I request Dr. Navajit Kumar Das, our colleague from the Department of Anthropology, Guwahati University, to felicitate our dignitaries. May I request him to please felicitate them with a gamusa and a memento. Thank you so much. May I request our colleague Dr. Navajit Kumar Das to please also felicitate our chairpersons for this session. Dr. Sanjay O'Neill Shaw with a gamusa and Dr. V.S. Prasad with a gamusa and a memento from Guwahati University. Many thanks, Dr. Das. And now may I request Dr. Das to please do the honors of introducing our lead speaker, Dr. T. Narayana Rao.
T. Narayana Rao received master degree in physics with distinction from Andhra University, Visakhapatnam. Later, MPhil and PhD degree in atmospheric physics from Sri Venkateswaram University, Tirupati. Dr. Rao co-authored more than 150 research journal articles of international repute and mentored 15 students leading to their PhD. He serving as a convener and several committee of national interest, and also as core member in SERV and PM member in Ministry of Art and Sciences. Presently, he is serving as an associate editor for Journal of Art System Science and Journal of Atmospheric and Oceanic Technology. He is serving as an associate, he is a fellow of prestigious Indian Academy of Science, Bangalore, and Indian National Science Academy, New Delhi, and also recipient of ISRO Team Excellence Award and ISPS Fellowship. Thank you.
Thank you, Dr. Navajit Das. Now, may I request our chairpersons, Dr. Shaw and Dr. Prasad, to please conduct the proceedings of the session. Over to you, sirs.
So it is a great time for us that we have Dr. T. Narayana Rao for delivering his lead talk. So may I request sir to please deliver his talk.
Yeah, on only. Okay. Yeah, okay. Okay, no problem. Okay. Okay, good afternoon. First of all, thank you for having me here. And then initially this year, actually, I have been giving so many these talks in all iRAD conferences. So this time I wanted to skip. But in the last moment, they told me to give a talk on wind profiler, so there's no one. So I immediately agreed. But then I have already given 2-3 talks on wind profilers on different aspects, on the radar meteorology, and then also one more talk on the topside distribution retrieval and microphysical parameter retrievals and other things. So this time, that's why I changed my presentation. Then today I'm going to talk about atmospheric turbulence. And this is more like, this is not really a scientific presentation, it's more like a technical presentation. So this is how we can use wind profilers to measure the atmospheric turbulence. I will, at a later stage, I will not only confine to the wind profiler, but I also talk about the Doppler weather radars. So this is the slide. Actually, normally I show to start the presentation. Normally in atmospheric radars, we can divide into broadly three classes. One is the, you call what, operating at VHF and UHF band. So we call wind profilers. And then the basic, the scattering mechanism is the Bragg scatter. And then when you're talking about VHF, there are other scattering mechanisms also, like Fresnel reflection and Fresnel scattering. And then, and also these radars also get echo from the rain particles and then ice particles. So through Bragg scattering. So these radars actually you get all sorts of scattering. And then if another class of radars actually are called Doppler weather radars, they operate either S band or C band and X band. depending on the requirement and then other things, then they choose the frequency. And then another class of radars, actually the high frequency, these radars, they operate at K and W band. They're all for the cloud profiling. These are the basic scattering mechanisms. That's what I told. Then these three scattering mechanisms are relevant for wind profilers, and these scattering mechanisms are relevant for the Doppler weather radars and then the cloud radars. So the basic thing is actually these radars operate during the clear air conditions also. So the basic thing is actually they get the echo from the changes in the refractive index. The small changes in the refractive index will scatter, and then the scattered signal you will use to retrieve the parameters. So broadly, these kind of MST radars, they are useful. Because they get echoes from the troposphere and then lower part of the stratosphere, and then some regions of mesosphere and then ionospheric region. So a lot of studies people have done in the upper atmosphere to study the E region and the quasi-periodic echoes, 150 kilometer echoes, and then to see the spread of the plasma bubbles and other things. And then the middle atmosphere also, people have done a lot of studies on the mesospheric echoes, winds, waves, dynamics, because these radars are basically for understanding the atmospheric dynamics. So there are a lot of people have done a lot of studies on that. And in the lower atmosphere, people have done some the exchange between the troposphere and then the stratosphere. Some studies focused mostly on the variations of the tropopause and then the exchange between the troposphere and stratosphere. I think this region is actually is a very good region to study these exchanges, because there is a lot of intrusion, stratospheric intrusions comes in the extratropics. So those things can be studied with this the radar, whatever situated here. And then the wave dynamics, and then several meteorological processes people have studied. And then this is also atmospheric turbulence. This is what I'm going to talk. So when you talk about the atmospheric turbulence, we use actually these atmospheric turbulence in several domains of atmospheric studies. Starting from the weather and climate studies, because some sort of knowledge and quantification is required, quantification of turbulence is required, basically to understand this exchange of heat, moisture, and momentum, particularly in the lower part of the atmosphere. And then, of course, this also influences the boundary layer evolution, and then, of course, parameterization in all numerical models. Boundary layer parameters plays a very important role, and then. The another important application is the aviation safety. And then I just Googled it last time. Sometime back I read actually in the news that nearly some 5,000 to 6,000 these turbulence related serious discomforts happens in aviation in every year. And then there are tens of thousands small incidents happens because of the atmospheric turbulence, but then the severe accidents happens because of the atmospheric turbulence. Then for air quality and pollution dispersion also, this turbulence information is very, very crucial in those kind of studies. And then turbulence is the one actually initiates in the initial phases of the cloud drop growth. The turbulence plays a major role in enhancing the collisions and then thereby contributing a lot to the drop growth. And then optical radio wave communication, upper atmosphere. So in several domains of atmospheric research, some information about the turbulence is required. So there are some instruments, several instruments to measure the atmospheric turbulence, like sonic anemometers. They will provide high resolution wind measurements, and then from there, either you take the variance and then calculate the turbulence, or construct the spectra, and then from the Kolmogorov theory you can calculate the turbulent kinetic energy. And MST radar and wind profiler, that I'll come little later. And then weather radar also we can use to estimate the turbulence. Then Doppler radar measurements using the velocity variance, they get the high resolution measurements, and from their velocity variance they can calculate atmospheric turbulence. So in different regions, different instruments people use to measure the atmospheric turbulence. And there are some indirect methods also, like radio sounds. They use using the Thorpe method to get the atmospheric turbulence. But these are all point measurements. For example, sonic anemometer or aircraft measurement or radio sound, you see these are all point measurements, whereas the radars provide a kind of a volume integrated value. So this more robust value it provides. See, yesterday also we have seen the Doppler spectra. So typically at one height, if you take the Doppler spectra, will look like this. I think yesterday, I think most of the students have gone to the Doppler weather radar, the 200 megahertz radar site here, and they have seen the Doppler spectra. At one height, it looks like this. So there is a, from the zero, how much it is deviated, that gives the Doppler velocity, and the spread gives the actually information about the atmospheric turbulence. If the spectra is broadened, then the turbulence is more. If it is narrow, then its turbulence is less qualitatively. So by estimating the broadening of the spectra, we can calculate the intensity of the atmospheric turbulence. So why this broadens and how we are relating it to the atmospheric turbulence? See, assume that the wind, you have a beam, radar volume is, in the radar volume, you have a lot of turbulence. So in general, they are all moving with the background wind. But then there are these irregularities that sometimes they are opposite to the background wind, and sometimes they are in the direction of the background wind. So because of that, there will be a small changes in the background wind. So that because of those changes, you see a broadening in the spectra. Okay, so that's why the broadening of the spectra directly gives information of the atmospheric turbulence. But there are some problems because there are some other contributors which broaden the spectra. So we need to remove those things to actually estimate the turbulence intensity. For example, beam broadening, they call beam broadening, shear broadening, and other effects. So it's intensity, it's not visible. Hey, you can change the battery, I think. Okay. Battery you can change. Okay, if you have a wide beam, then the targets which are actually at this edge of the beam will encounter a difference of a velocity, and then similarly these targets here also encounter a different type of velocity. Because of the different velocities also your beam can broaden. So we need to remove, so what happens is actually the broader the beam, you have more problems. So you have to use a very narrow beam to get rid of the beam broadening. And then also it depends on the background velocity, because the background velocity component is actually going inside. So ideally you need a very narrow beam, and also the wind should be small to get rid of the beam broadening. And then the shear broadening within the pulse actually the target, there is a strong shear. For example, if the wind is increasing with altitude, let us say, then the targets actually which are at the lower edge of your volume will encounter a smaller wind, and whereas here they will move with the larger wind, and then because of that also you see a kind of a broadening there. And so these is called shear broadening. So these broadenings we have to remove to accurately calculate the turbulence. Okay. So MST radar was, Indian MST radar for example was installed in 1993. People, we have been studying about the atmospheric turbulence from those days. The first paper came in 95. For example, the turbulence is large at lower heights and then decreases with height. So this is what we know from the initial results. Then there are different methods people use to calculate the atmospheric turbulence, because the backscatter, whatever we are getting, is basically due to the turbulent irregularities. So using the backscattered power, also we can calculate the atmospheric turbulence in addition to the spectral width. So people have compared those different methods to see whether they are agreeing or not. So and then finally they found they are actually within some error. They normally match at some heights where turbulence is a major factor for the backscatter. And then we have studied actually what is the seasonal variability, and normally during the monsoon time it will be large compared to the winter time. And there are some local enhancements where the tropical easterly jet and other jet streams are there in the shear zones. Normally you see a local enhancement of the turbulence. So these are some results actually people have done, people have published, and then sometimes we have launched the radio sound in those days. Now actually of course we have a regular radio sound descent, but in those days actually we have in a campaign mode, we have launched radio sounds and then used different techniques and then compared these things. Like that, several studies we have done. But these are all theoretically we are removing these contributions. But how far they are accurate? Okay, so they are published somewhere, and then we have taken those formulae, and then we are using it theoretical formulations to remove these beam broadening contributions, shear broadening contribution, and other things, just to check whether these formulations are correct or not. What we did is we conducted an experiment some time back. Then we used different antenna sizes. Okay, full antenna, half of the antenna, 1/4, and 1/8 of the antenna, and then we tried to see that whether we are getting, after correction, we are getting the same value. If the formulation is wrong, anything is wrong, then we should not get that, because if it is because of the error, something else we should get. To see that, if we use it different antenna sizes, so VM also will be changing accordingly. And then finally what we found is actually after correcting all these things, then they all converge. So giving the confidence on this technique that it is working well. So similarly, we did that during the clear air, and during rain time also we have studied the turbulence, what is the turbulence intensity. And then normally what we found is actually the turbulence intensity is nearly an order of magnitude higher in the cloud. In cloud turbulence is one order of magnitude higher compared to the clear air. Then when it comes to the Doppler weather radar, people have used Doppler weather radar, X-band Doppler dual polarization radars for studying the microphysics and other things. But many people have not used the weather radars actually for that study of the turbulence. Only qualitatively they say that if the spectral width is large, then they say turbulence is very high, and then if it is narrow, then they say turbulence is weak. And then the one problem is because this Doppler weather radar is getting echoes from the raindrops. So mostly the broadening is due to the fall velocity of the hydrometeors. So we need to remove the contribution, then only we will be able to do. Otherwise we have to ignore. So generally the people take at lower elevations, so they can ignore that, because if almost lower elevation means the fall velocity is perpendicular to that this component is almost negligible. So we can neglect that. But if you want to get the complete profile, the total system, how the turbulence is behaving. So if you want to know, then you have to go to the higher elevations. But then higher elevation people have not tested. So what we thought is actually we have an MST radar sitting there, which is giving very accurate turbulence measurements. So whether if you have a common volume, with MST radar, then whether if the turbulence intensity, how it compares with the turbulence intensity. So then we can use actually Doppler weather radar at higher elevations also, so that we can get a complete structure of the vertical structure of the turbulence, and then we can also track the advantage with the Doppler weather radar is you can track. So when the system evolves, then we can see that how the turbulence structure is changing in an evolving system. So that is the advantage with a Doppler weather radar, whereas with MST radar only is a vertically pointing system. So system has to pass over the radar, then only we'll be able to study. Whereas the advantage here is you can track it. Okay, so that's with that intention what we did is we did several experiments to have a common volume. I'll skip some of these things. Okay. Don't worry about all these things, because I told that with MST radar you have three problems which broadens the spectra. One is actually the beam. Due to the finite beam we have a problem, and then because of the shear, wind shear also you will have a problem. But in case of the when it comes to the Doppler weather radar, you have other problems also, because the antenna is not steady, it is also rotating. So because of the rotation of the antenna, then you will have a broadening. And also there are other factors, because with the beam shear, all sorts of shear broadening comes here. It's not only the vertical, and then also because of the oscillations also some broadening occurs. And then, but the major contributor is actually due to the fall velocity of the hydrometeors. So these are the additional contributions which broadens the spectra. So we need to remove all these things, then only you will get the turbulence. You can use the spectral width for the turbulence estimation. In the case of MST radar, you have only two factors, but whereas with the Doppler weather radar, you have several factors which will broaden the spectrum. So we need to remove all these things. And of course, we have done that. Then earlier some reported, some studies are there, few studies, they have used actually the climatological to remove this contribution, contribution due to the fall velocity. To remove that, then people have used some kind of a climatological values, whereas if you have a polarimetric radar, you can get the actual DSD, and then we can use this DSD to remove the hydrometer fall velocity. So we did all these things, and then finally what we got this experiment, what we have done is, what we tilted the MST radar for 10 degree towards east, and then Doppler weather radar here is around 600 meters from the MST radar, and then we pointed exactly in the same volume, and then we had a common volume of with the MST radar as well as the Doppler weather radar, and then we quantified the turbulence within the common volume. So we have taken, I'm showing two case studies here during the two cyclones. We have Feng and Michong, and during that time, this is the PPI image. This is a convective system here sitting there, and then this is a stratiform rain. During in different precipitating systems, normally how the turbulence behaves. This is with the MST radar. Of course, you see very high rainfall rate of nearly 30 millimeter per hour, and velocities are also of the order of 5 to 6 meter per second. And during the stratiform rain, you don't see those kind of things. The rainfall rate is also very weak. So these are the two case studies we have taken, and this is what we see. This is the spectral width. That's what you get with this is the observed spectral width with MST radar, and this is with one is with MST radar and one is with Doppler weather radar. And in other case is the convective case with MST and then you can see actually in this case with the MST radar, the beam broadening, because the MST radar beam is around 2.2 degree. So the beam broadening is the main contributor, which is giving nearly 8% of the, is contributing to the 8% of the broadening. Whereas in case of a Doppler weather radar, this, the beam broadening is not the major factor, because the beam is very, very narrow here in this case. And this here in this case, actually the fall velocity of the hydrometer contributes more, nearly to the 15% to the broadening. And then after removing all these things, and then after calculating, you see in a common volume, they are more or less actually matching both X-band radar as well as the MST radar. You see broadly they are matching. Okay, so this gives confidence on the Doppler weather radar. We can use Doppler weather radar to calculate the turbulence if you properly account for all those non-turbulent contributions. And then of course we have taken several cases, and then to see whether, and then one good thing is actually you see the both MST radar as well as the Doppler weather radar, the range of turbulence values, intensities, actually they are all more or less matching. And also you can see a 1-to-1 correlation also. It's a reasonable correlation you are getting. So it gives confidence that you can use the Doppler weather radar to estimate to quantify the intensity of the turbulence. Okay. So this is what, so these radars, of course, MST radar they are proven tools to obtain vertical profiles of both clear air and in-cloud turbulence. Whereas now with this comparison, what we found is actually now we can use Doppler weather radar also at higher elevations to calculate the turbulence if you are properly accounting for the fall velocity. And then what we found is actually the turbulence intensity is an order of magnitude higher in precipitation than clear air. This is what we have seen when we compared with our whatever values we got here with those earlier studies. Then we found that this is an order of magnitude higher. And even in stratiform and convective rain also, we found that there is a stratiform, the turbulence in convective rain is actually an order of magnitude higher than in stratiform rain. Okay, and then, but it's not always true. But even in stratiform rain also, we have 1 or 2 occasions we found strong turbulence. Normally in stratiform rain, we expect the turbulence to be weak. But in stratiform rain also, we have seen in 1 or 2 times actually the large turbulence, and then we saw that what is the reason. Then we found that actually there is a strong shear is there. So that shear, because of shear, actually you are getting higher turbulence in those cases. So of course this, sorry. So the scanning capability of DWRs actually it allow It allows us to understand the turbulence structure in an evolving system. This is the advantage actually, because now DWRs also we can use if you are properly accounting for the other contributions. So this is what actually I wanted to tell. Thank you very much.
Any questions to Dr. Narayan Rao? Mainly from young students, any?
Yes. Should be. S-band actually you can use, sometimes S-band you can use, you will get even the Bragg scatter also. So you can directly use that Bragg scattered signal also to calculate the turbulence. Or also, otherwise, if you know if you can account for all other things, then you can use the Rayleigh scattered component also to calculate the atmospheric turbulence.
Yeah, good presentation, sir. Just as a follow-up question to what he asked, both the methods work when or during the absence of precipitation also?
Doppler weather radar actually gets echo from the precipitation particles only. This is what I am telling. These two radars operate at different frequencies. They have different sensitivities. They have different scattering mechanisms. MST radar gets echo from the Bragg scattering, whereas Doppler weather radar gets from the Rayleigh scatter, basically from the precipitating particles. Okay. Even then, when you properly remove other contributions, they are matching. Okay. So that is the message.
Okay, thank you.
Any other? If not, I have one question.
You have one
question. Is it possible to automatically identify the turbulence regions in radar image, and so that it can?
Yeah, people are doing it qualitatively by looking at the spectral width plots. But then if you really want to use these actual numbers either in the models or they wanted to quantify properly, then they are simply neglecting. Only the lower elevations they use, the lower elevation angles they will use the PPI images and see wherever spectral widths are large, then they say that this is the turbulent region. So like that they are qualitatively identifying, but then really quantitatively nobody is really looking at that. But then it can be used to quantify the turbulence. So the parameters can be directly, we can use it in the models and other things.
Like lightning, other things, there is automatically audio
yes.
signals are putting that one. It identifies, tell that where the lightning going to occurring.
Lightning is
especially the DWR image.
Lightning is another issue, but what I am telling is the strong turbulent layers can be identified, in-cloud turbulence layers can be identified with the Doppler weather radar. MST radar is actually, we can use MST radar to see to know the clear air turbulence. These two are two different things. One is clear air turbulence, the other one is the in-cloud turbulence. But still, if you properly do, then it will match. The atmospheric, the background turbulence we can derive.
Thank you, Dr. Narayan. Wonderful presentation. Now,
we will start with this paper ID 08 by Mr. Javed Akhtar.
May I start? Okay. Respected chairpersons, respected keynote speaker, and all the other dignitaries, a very good morning to all. I am Dr. Javed Akhtar from Department of Atmospheric Science, University of Calcutta, and this work has been done in collaboration with Professor Ashik Pal from Institute of Radiophysics and Electronics of University of Calcutta. Today I am going to talk on characteristics of atmospheric turbulence that obtained through the CU-ST radar over Havingata in West Bengal. So atmospheric turbulence, it plays a crucial role in momentum transfer, energy dissipation, mixing process in troposphere as well as in the lower stratosphere. The ST radars, that's the stratosphere, troposphere radars, they operate in the VHF band, which is from 30 to 300 megahertz. They can detect the atmospheric echoes over a wide altitude range, and they are highly sensitive to the small scale fluctuations in the radio refracting index, which is associated with the turbulence. So we can use the SNR, which is obtained from the backscatter radar signal, to estimate the refractive index structure parameter, or CN square, which is a key quantitative measure of the turbulence. Here at Calcutta University, ST radar, it provides a high resolution wind observation as well as the SNR observation, which help us to estimate turbulence at different heights. And this is the location of the ST radar. It is in the eastern part of India. It is located at Havingata of West Bengal, and this is an active phased array radar operating at 53 megahertz, and this is the aerial view of this radar. So it is located strategically in a location which is a transition zone between tropical and subtropical climate zone. Also it is located near to the equatorial ionization anomaly zone, and it is a part of IGP, Indo-Gangetic Plain, as well. It is it is located in the proximity of Bay of Bengal as well, and it is prone to very high damage weeks, like it faces nor'westers in the pre-monsoon and thunderstorm during monsoon, and also frequent tropical cyclones. So, okay. It is a 53 megahertz radar and bandwidth of 3 megahertz, and it can steer the beams up to 30 degree, and its height coverage is up to 24 kilometer presently, and its resolution is 50 meter up to 3 kilometer. After 3 kilometer, the resolution is 150 meter. And how the data is processed from power spectrum, that is, we got the binary data, which is called .d5. Then we convert that in ASCII format, which is .mmt5. From that, we estimate the moments parameter like total power, mean Doppler, Doppler width. And then we also compute the wind components like UVW components using the Doppler beam swinging technique, DBS. And signal to noise ratio is estimated using this formula, which uses the total power, number of 50 points, and noise level. And there are 5 beams used in this radar. One is zenith, one in the north and south at 10 degree, and another in the east and west. So in DBS technique, 3 non-coplanar beams, one zenith, one in the east-west beam, and another is north-south beam is used to compute the wind velocities. This is how turbulence is computed. As I mentioned earlier, CN square has been used to estimate the turbulence, which is related to the radar reflectivity by this equation, which is 0.38 cn square lambda to the power minus 3. Lambda is the wavelength of the radar. In our case, it is 5.66 meter. And this radar reflectivity is related to SNR through this formula. And there are various radar parameters which is given in this table, the values used in this experiment. Now coming to results, we have taken 4 dates, 4 distinct dates, 2 from winter, January and February, and 2 August date for the monsoon. So this is the zonal wind profiles, and we can see clear seasonal constants in the zonal wind structure. In winter, you can see there are strong westerly flow in the upper troposphere, while in the monsoon, there are negative values in the zonal velocity. So strong easterly flow in between the range of 12 to 18 kilometer, and this is associated with the tropical easterly jet, TEZ. This is the vertical velocity profile of the 26th January date. So here we can see the vertical velocity is quite weak, and there are very few updrafts and downdrafts. Similar can be found in the February. But in the monsoon, there are frequent updraft and downdraft, and vertical velocity is quite high in the monsoon situation. This is the wind shear profile. In the winter, the vertical velocity, the wind shear is greater below 5 kilometers, which is near to surface. But in the upper troposphere, it is more in the monsoon due to the presence of the TEZ. Now this is the estimated CN square, which we can see in both seasons. There is a decrease with height. The maximum values are found near the surface. And also there are seasonal modulation we can found. Yeah. So mainly in winter, the higher CN square values are confined to the lower troposphere due to the low-level wind shear, strong low-level wind shear, which I have shown earlier, and due to the mechanically generated turbulence. And during monsoon, CN square is enhanced due to the presence of that strong upper-level wind shear due to the TEZ, and also due to the convective activity as shown from the vertical velocity. This is a special case, the supercyclone Amphan. The vertical velocity increases during the landfall of the cyclone, and also we can see enhanced turbulence during the landfall. So I will now summarize. So CN square decrease with height in both seasons, but its magnitude and vertical extent vary, and enhanced turbulence found in the lower troposphere during winter, while it is higher in the higher troposphere during the monsoon. And the mechanism is low-level shear-driven mechanical turbulence causing in the winter, and in upper troposphere during the monsoon it is due to the presence of the tropical easterly jet and convective activity. And also during the cyclone we have found increasing vertical velocity and enhanced turbulence. And finally, I have to show one thing. It is the upcoming research opportunities at radar site. There is a project funded by MOES. Some positions are available, and a working interview on 28 January. If you are interested, you can contact me for further details. Thank you.
Requirements, constraints, we are reducing the speaker time to 8 minutes only from 10 minutes. So next speaker is Manoj MJ. Please. Please adjust the time to 8 minutes.
Warm good morning to one and all. I'm Manoj from Cochin University of Science and Technology. And what I am going to present is an overview of the research activities that was undertaken at Cochin University of Science and Technology. Actually, by this year end, we are about to finish or complete the 10 years of operation of 205 megahertz VHF radar at Cochin. So I have only 8 minutes to present the overview, so I will rush through it. Thanks to my collaborators and mentors. Unveiling the tropical atmospheric dynamics, a decade of scientific insights from the 205 megahertz VHF radar at Advanced Center for Atmospheric Radar Research. This is the ST radar at AccuSat, located at the brink of a coastal location near the Arabian Sea and sandwiched by the Western Ghats region. This is the configuration ST radar, which is already published. I will skip through this one. This is a kind of comparison with the radio zone observations. We are getting the lowest range bin right from 315 meters above the ground to somewhere around 20 kilometers. And this is the left side is the wind speed, and right is the wind direction. The black line represents the radio zone observations, whereas the other colors denote various baud rates. And this is the maximum height reached, even though there is a slight variation or reduction in height during the winter time, basically due to the reduction in humidity. Otherwise, we are able to cover up to 19 to 20 kilometers throughout the year. So this radar initially thought for deriving the winds for the troposphere and the stratosphere is now able to capture the signals of ionosphere also, which was not planned earlier. It is as a byproduct. So this radar is actually capable of probing the lower atmosphere, right from the boundary layer to the free troposphere and the lower stratosphere, and even to the E and F regions of the ionosphere. I will just cluster these research activities into different categories. One is the boundary layer evolution, and you can see the very good evaluation of boundary layer, morning boundary layer, and the convective growth, etc. Then we have derived a novel mechanism for identifying the boundary layer height from the vertical profiles of signal to noise ratio, wind variance, especially through wind direction and wind velocity, and making a combined product by summing up all the three and finding the exact top of the boundary layer and comparison with the radio zone. So here you can see that these three are from radio zone. This is the new method. It is known as the normalized standard deviation method, which is giving good value and a good estimate with the radio zone observation. So this radar derived new observation provides high temporal resolution mapping of boundary layer. This is the one you can see the evolution of boundary layer and comparison with other methods. Then this is a comparison for several clear sky days, just to remove the ambiguity with the cloud patches and other contaminants. We selected only cloudy sky, clear sky days, and the comparison black one represents radio zone and the magenta green color represents the radar. Now this is the seasonal diurnal evolution of all the seasons, winter, monsoon, pre-monsoon, post-monsoon, etc. Then we have several good observations of thunderstorms, both pre and post-monsoon observations. You can see how the atmosphere becomes turbulent prior to the thunderstorm event. Then the thunderstorm happens here, and finally the atmosphere comes back to a stable condition. Then there are this 205 megahertz as a unique facility or feature that it can separate out the signal due to background wind condition as well as the falling hydrometeors. So by utilizing this observation, we can estimate the background wind condition even during precipitation by adopting several technologies. I will show through that. And this is the investigation of the moist thermodynamical process of thunderstorms using radar and model. You can see how the radar is the model is accurately able to reproduce the vertical velocities at 1 kilometer resolutions. And here we can see the structure and thermodynamics of the atmospheric boundary layer in convection and thunderstorm initiation. We can see here you can see the I am unable to see here. Yeah. Oh, this one? Yeah, okay. Yeah, okay, very good. Yeah. So you can see how the thunderstorm evolves and how the pre-convective environment starts to develop from this one. And we have identified this bar represents the radar observations of boundary layer, and there is an enhancement of boundary layer at least 2 to 3 hours prior to the thunderstorm initiation. That means the pre-convective signature is already evident in the boundary layer, and the convective mass flux, how it is improving, that also you can see. Yeah. And one more thing is the difference between equivalent potential temperature and the potential temperature difference influencing the moisture difference, and the increase in the vertical velocity prior to thunderstorms also you can see here. Then because this is a observation of thermal internal boundary layer evolution, and here it is taking from model and radar. We are able to accurately pinpoint the observations, and this is the during the land sea breeze onset, how the vertical velocity variance before, during and after it is coming, and the slight baroclinicity over the coastal location is for the first time it is quantified using this baroclinic angle, and you can see the isobars and isopycnals cross at this theta angle. This is the evolution of theta. From this theta we have found out that something like 500 meters of ascending motion is solely given by baroclinic instability, which is driving the sea breeze circulation. And some waves and instabilities also. I'll just go through this one, won't explain this one. So we have identified the inertiogravity wave, presence of inertiogravity waves over these locations, and this is the characteristics and intrinsic periodicity of IGWs. Then ALS wind validation, it is a satellite by the European ESA, European Space Agency, and its validation is also done by our radar, which is conducted by Agil et al. Then application of AI and signal processing in clear air turbulence and clear air signals and precipitation echoes has been done. This is the observation of Kelvin-Helmholtz instability and Kelvin-Helmholtz billow over our region, which is published. And during the monsoon time, you can see low-level westerlies and upper-level easterlies, and the evolution of vertical wind. Then we have identified an empirical model decomposition method for identifying the background wind from the precipitation echoes. This is using the radar. We have developed a monsoon onset index which can predict the onset at least 2 to 3 weeks ahead, which is already published. And this is cold point estimation, cold point tropopause estimation from radar. Then application of AEML in radar signal processing is also done. And we have identified a new method that is nothing but the Gaussian mixture model for separating out the clear air echo from precipitation, which is already published. Here we use a combination of 2 Gaussian functions for identifying that one. And finally, the radar observations during ionospheric plasma irregularities. You can see that how a thunderstorm starting in the troposphere can send acoustic and gravity wave frequencies into the ionosphere and perturb the ionospheric total electron content over this location. So that is also published. Yes, finally. So then the recent Hungatonga volcanic eruption, its signature had sent gravity waves throughout the equatorial region, and its presence also could be detected with the radar. And Thanks for all your patience. Thank you.
Uma Khan. Kane, sorry.
Yeah, Uma.
Sorry for the try.
This one is pointer.
Yeah, that's pointer, and slide changing is the
This one is slide changer. Okay.
Hello. Hello? Yes. ठीक है? अब गिरना नहीं चाहिए. Yeah. So very good morning to one and all present. Good afternoon to one and all present over here. And yes, load the presentation. Yeah. Myself, Uma from Space Physics Laboratory, ISRO, and today I'll be talking about the convective storm differences during the wet and dry spells and active and break phases of the Indian monsoon. Due to short lack of time, I'll just proceed with the slides. And as we all know, this is the percentage of MCS, what do we see, and this is the rainfall fraction that is created by the MCS. And we all know like 70 to 80%, in fact 90% of the rainfall comes from the MCS. And convection play a major role in terms of its hydrological cycle, radiative balance, exchange processes, and it plays a major role in the global weather and the climate. So in terms of now, when it comes to convection and global weather and climate, monsoon plays a major role. As we all know, Indian monsoon, about 70% of the rainfall comes from the monsoon convective systems. So within that monsoon convective system, yes, the August audience must be knowing about the intra-seasonal oscillations that we have, the dry and the wet spaces, right? And in that also we have differences, and like regional wise also there are changes in this rainfall. So when we call an all India, like all India active and the break phase, we call about the central Indian region. So based upon that region, we define the active and the break phases of the monsoon. It means that when you calculate the rainfall anomaly, it should have plus or minus 1 sigma. If it goes above 1 sigma, we call it as an active phase, and if it comes below, we call it as a break phase. And the regional dependence, because every region, like for especially when you comes to the southeast India or the southern peninsular India, it does not follow the active and the break phases of the all India. So we need to go for the regional definitions, and that is why we go for the wet and the dry spell. And this is a typical rainfall map you can see. When this is wet, dry, and active and break, when the central Indian receives the active major rainfall, we don't receive much rainfall over here. And when there is a break phase, yes, of course we receive. This is a well-established feature. So this paper mainly focuses upon that, what kind of the convective storm characteristics exist between these 4 phases. That is the active, break, wet, and dry, how the storm properties changes. And we go here. And this is the typically we have used sorry to explain, we have used a C-band radar that is situated over the Tumba, the Stura location, and we have taken about 140 kilometers around in and around that region. You have the popular Western Ghats over here, and so we will be able to differentiate the characteristics of the convection with respect to this coastal, land, and the orography effects also. So this is the typical phase. We saw the wet, dry, active, and break. Active and break, I means the definition based upon the all India active and the break, and the wet and the dry is the regional classification. So you can see that this is number of the days is also given, and we all know the convection is very less during the dry phase, but you can see that the intensity of the convection is extremely high during the regional dry phase, and that is even prevalent during the break phase of the monsoon. And active and wet phase, we see overall a distribution of a convection over this region, and this is the maximum reflectivity. What do we see? The maximum reflectivity also, you see that over the coastal and near to the land regions, we see a strong convection during the dry phase of the monsoon, and that prevails even the break phase of the monsoon. So at a first stretch, it shows that the intensity of the convection is maximum during the dry and the break phase compared to the active and the wet phase. So we try to characterize what kind of convective storms basically exist. So we classified based upon the shallow, deep, and overshooting. Like shallow congestors, we basically classify well below 8 kilometer as standard definition. And then 8 to 15, we call it as a deep. And when the convective storm top goes beyond 15 kilometer, we call it as an overshooting convection. And that is the category that comes here. We see wet, dry, active, and break. We see mostly the congestors dominates. during the wet and the active phase. But when it comes to deep, you see the dry and break has more deep convection compared to active and the wet. And the overshooting convection percentage is very less because we don't, over that region, only on the leeward side of the Western Ghats, we get maximum overshooting convection, as the monsoon is basically dominated by the congested systems over this entire region. And coming to the next one, and then we try to do some statistical analysis with respect to the box chart, trying to see different properties of the storms with respect to the area, what will be its top, what will be duration and all. So overall, we could find that even though the area of the storm and the max Z is very high for this active and the wet, but we see that intense storms are fine in the dry and the break phase. Even the duration of the storm is more for the wet, but we see even the dry and the break exist for about 1 to 2 hours. Now coming to the rainfall, yes, we do see here the characteristics between the regional wet and dry and the active and the break. You can see that break also gets equally a good amount of the rainfall when the All India break is declared. We do see a significant amount of the rainfall over this region, and that is, even though the dry spell it's prevalent, the area of the storms and the precipitation flux as the larger area contributes to more precipitation flux during both the break and the dry phase. And then next comes the diurnal variability. What kind of diurnal variability of the convection exists over this region? We do find that wet, we do not see a significant diurnal variability like wet and the wet phase, but during dry phase we see a strong afternoon peak, and during the break phase also we see a strong afternoon peak. So that clearly shows that this afternoon peak, the dominance of the deep convection we do see during the afternoon time, and that contributes to the maximum to the overall percentage of the storms. And active also we see a small in the early morning, and this early morning basically comes from this where we are seeing that early morning peak that basically comes from the oceanic systems, because the oceanic system, when you see the overall diurnal variability, it starts propagating from the Arabian Sea, as our station is very close to the Arabian Sea, and it propagates and then enters the inland, and you have the orographical effect, and once it crosses the leeward side you get a very deep and the overshooting convection, and that is what this classification also shows. And then yes, and I'm coming to the last slide. I think I could complete. And then so when you talk about this kind of a differences between these storms over all these phases, what kind of background meteorological condition should be responsible? Because within a short region itself, we do see the differences in the nature of the convective storms that is over this location. And so what did we find? This is the background convective available potential energy, and this is the specific humidity, and this is the temperature anomaly, and this is the vertical velocity. So what do we see? Basically the dry phase, where do we see the intense storms, is basically more dominated by the positive anomaly of the Cape. Means the Cape guides more the convective storms during the dry spell, but on the other it is only basically the moisture and vertical velocity that drives during the wet and the active phase, which we do not see in the dry phase. Especially you do not see a very strong updrafts, or you do not see any kind of strong humidity during the dry phase, but only the Cape and the warm temperature anomaly drives during the dry phase of the convection. So when you see overall the wet and the dry and break, in a conclusion, the dry and the break phase has more intense storm, and that is driven by the Cape, and during the wet and the active it is the moisture and the advection of the low level jet that drives mostly the convection over this location. With that, I thank you. I could finish in time. I can take questions if it is permitted.
So now I invite Mr. Nawadun Poddar.
Good afternoon, everybody. So I am Navarun Poddar from Space Physics Laboratory, Vikram Sarabhai Space Center. I am a senior research scholar. I am going to present on the characteristics of vertical air motion near the vicinity of monsoon jet stream using the direct radar measurements using the Cochin stratosphere troposphere radar. So as we know, that vertical motion of air is a very key driver in the atmospheric processes across different scales. It is the establishment of this radiative convective balance that actually causes this motion right from the troposphere, that is the lowest layer of the atmosphere. And it is very important in facilitating the mass and momentum exchange in the troposphere to stratosphere and vice versa. So generally we can delineate vertical motion of air across two different scales. So first is the very short-term and spontaneous motion that is generally triggered by a particular set of local atmospheric combination of atmospheric conditions that are mostly dominated by processes such as strong convection, extreme weather events such as cyclones, so on, and by spontaneous stratospheric intrusions that occur from stratosphere to troposphere. Now, generally the scale of this motion, this vertical air motion, is of the order of meter per second. That is generally comparable to the order of the horizontal winds that are extant over a region. But then there is the clear air and the long-term mean motion of air in the vertical direction that is actually much lower in magnitude. And it is like the one that is more responsible for having larger amount of climatic implications. That is the transport processes across the stratosphere, troposphere region. So this is what I wanted to study. Now, it is very difficult because you cannot measure it so easily because of its very small magnitude as compared to the other component of air. But thankfully, it can be measured directly and very precisely using stratosphere, troposphere, and mesosphere, stratosphere, troposphere radars. Now, to get the background and motivation, we know that the Asian summer monsoon region, as shown here, is one such region that has a very complicated dynamical setup. And this region encompasses everything: strong wind systems, cyclonic and anticyclonic circulation on a very large scale, which are very important to understand the climatic implication of vertical motion in this region. Now, already some work has been done owing to the presence of some other ST and MST radars. Gauhati is where famously it has been done for a long time, and it is established. And recently it has also been done over Nainital. But these two locations are in totally different orographic and different regimes in this region. And it is not as same as the gateway of the Indian summer monsoon, that is the southern part of India in the state of Kerala. Specifically, we are working here with the stratosphere troposphere radar, as already explained by Dr. Manoj in Cochin. That is a 205 megahertz stratosphere troposphere radar. And we see that in Cochin, we see these two jet structures in the zonal direction during monsoon. So now to understand how this affects the total vertical motion, we have done this study. So to come to the radar, I will just go straight through it. This is the specification as has already been shown. This is a typical clear air echo from this radar in the multiple directions when the beam has been inclined, we see. This is in the absence of any convection or any precipitation. Now to see the data availability, we are here working with a long-term data set. That is, the radar has been operational for almost 10 years now, as has been already been told. Now we are using the data that has been observed between 2018 and 2024 here, and we see the heat map operation. That is, more than 20 days of radar have been operated in most of the time, and we have more than 100 hours of operation per month. And this is the time distribution of the data. We see from this that from around 10 IST till 19 IST is the time where the radar has been operated intensely across all the seasons. So this is the period that we have taken for an analysis. So now to go to the data processing, we start right from the raw signals, and we obtain spectrum and the moments using the well-established adaptive method to get the Doppler moments from there. This is a comparison of the vertical velocity that has been carried out using the different well-established techniques, and we see that they're more or less aligning. Although we will be going forward with the direct measurements, that is the direct zenith observation. Now the profiles have to be filtered of any convective disturbances to make it very uniform, just not to get any bias in it, so that because we are characterizing long-term data. So what we have done is we have filtered out any convective or precipitative data by totally eliminating frames by using a plus minus 1 meter per second bound of the Doppler velocity. And this is the what we are left out, the solid lines in each month across all the years from the this dotted line that shows all the profiles that what we are working on. And the coverage we are getting, combining two modes of the radar operation, we are getting almost 450 meters to 20 kilometers. So to get the monthly mean characteristics, these are the contoured frequency altitude diagrams of the probability of occurrence of vertical velocity that has taken place across all the months. We see that in all these things that the spread of this distribution is actually showing the extent of higher vertical velocities, where like anything more than white is actually showing more than 1% of distribution. 99% of the distribution in all the months lie actually inside 0.8 meter per second in the filtered data set. And it is also evident that the spread increases in the month of monsoon, and we see there is a very big expansion in this distribution at around 15-16 kilometers, which also corresponds to the tropical easterly jet that is present at the location during this time. Now coming to the monthly mean vertical velocity characteristics, we see that seasonally when we divide this across the 4 seasons, we see that there are variabilities, but during this summer monsoon months of June, July, August, and maybe May here and September here, centered around this region, we see a very clear structure where we see downdrafts in the lower troposphere that is actually crossing over to consistent updrafts in the upper troposphere and lower stratosphere region. So this is a very interesting feature because this will, I'll come to it, this is a feature that is like a 2-step process of transport of air mass from stratosphere to troposphere. Now we should remember that we have removed convection, but still there are some studies that tell that such a characteristic structure might also be due to influenced by the tropical easterly jet or any jet structure as such. But previous studies tell that this sort of reversal is supposed to happen where the jet peak occurs. But in case of tropical easterly jet, we know that this is not so, because this is occurring at 12 to 13 kilometers, while the expected jet peak is much above that. Thus we can tell that this jet is not affecting as such. Similarly, when we study the shear also, we see that at the height of reversal, there is barely any drastic change of shear. So that is also not a player in this. So this 2-step process of transport is what we are getting during the presence of these jets during the summer monsoon. That is, if extant convection does not carry air mass from lower troposphere to that particular height, it is not possible for it to travel straight into the stratosphere. So it is a 2-step process. So whenever convection is present, it is coming into the play. Similarly, this is the hourly variation of whatever I showed as monthly mean, and we see that this reversal height is actually a persistent feature that is observed during this summer monsoon months, and this can be supported, and the downdrafts below it can be supported by the fact that convection over this region, although it is intermittent, yet it is widespread. And although we have removed convection from what we have, it is the convection in the areas located around the region that the gentle subsidence associated with it can cause this possible downdrafts here. So this is a summary of it. Thank you.
Now our next presentation is by Madam Indrani Chattopadhyay. Please put on this monitor. ये monitor off हो गया, इसको on कर दो.
Yeah, so good morning everyone. I'm Indrani Chattopadhyay, a third-year mechanical engineering student from IT Bhubaneswar, and I'm honored to present a research article written by my professor and co-author Dr. Srinivas Ramanujam Kannan and me at the iRAD 2026 conference. So our research article titled Time Series Analysis of Wind Fields over Kolkata during the pre-monsoon season. So our research article titled this investigates the chaotic and deterministic nature of the atmospheric dynamics over a region where the geography plays a fundamental role in the key development of the weather, specifically focusing at the Kolkata radar site. So, to understand about the weather of Kolkata, we have to look to the Chota Nagpur Plateau, which is a very complex terrain, which is a primary indicator of complex terrain. It has a topography which is undulating with prominent gneissic hills, often dome-like in outline. And it has major features like the Prashant Hills and Dalma Hills. As you can see, the highest point is 1,164 meters, and also the lowest step is around 300 meters. So what is so beautiful about the climate here? The region around Kolkata is very unique in its tropical climatology, which receives an annual total rainfall of 1,600 millimeters and also has experienced very high damage risk owing to these Kalbaishakhi or northwesters. This region is also known for its deep convection, thunderstorm and lightning activity. So now we'll talk about the phenomena which cause these events. So the land heats up significantly during the pre-monsoon seasons of March to May, and because of this, the local convection takes place. The heat from the air, it decreases the density of the air and it rises up rapidly. Warm, moist air from the Bay of Bengal meets the cooler, drier air from the plateaus, and this instability fuels rapid updrafts, forming towering cumulonimbus clouds, which are the main hallmarks of these thunderstorms. Next, we'll talk about the jet streams. What are jet streams? These are narrow bands of fast-moving air in the upper layers of the atmosphere. In our region, the subtropical westerly jet stream flows at the high altitudes. If a trough or a dip in the jet stream moves over this region, it causes an upper-level divergence. So it is basically a vacuum which sucks up the rising convective air upwards even faster. So being from West Bengal myself and having seen these destructive thunderstorms firsthand, from my childhood I had a very big curiosity about the dynamics of these thunderstorms. Kalbaishakis or northwesters are localized severe thunderstorm phenomena that occur during the pre-monsoon seasons in eastern India, primarily from March to May, and the clash of these air masses, the warm moist air from the Bay of Bengal, clashing with the northwesterly jet streams are the main trigger for this phenomenon. So our problem statement characterizes this phenomenon by studying the U, V, and W wind components. The U and V wind components track down how much air and moisture moves across the region, and the vertical components are a straight indicator of the convective lifting and the storm intensity. The analysis at the surface level characterizes the intensity of surface heating and convective lifting, and the analysis at the mid-altitude, 700 hPa exactly, characterizes how much there is instability because of the local convection and the high-altitude jet streams. Produced by the European Center for Medium Range Weather Forecast, we have used ERA 5 dataset, which is considered as the global standard for atmospheric data. We have taken the data for 2001 to 2025 basically, which is available at 137 vertical levels. So why time series analysis? So atmospheric dynamics are very complex, which is composed of very complex thermodynamic and fluid mechanical processes. So time series helps us gain insights into the physical evolution of the atmosphere, which a simple linear model might miss. To measure the predictability, we have calculated the Lyapunov exponent. The Lyapunov exponent measures how much simple perturbations evolve over time. A negative exponent indicates a deterministic system. A near zero exponent reflects the near neutral or quasi-periodic behavior, and a positive exponent signifies chaotic dynamics. We have also calculated the time delay to find out the phase space of the system. A small tau captures the short-term correlations like convective turbulence and local heating, and a large tau reflects the mesoscale processes such as diurnal variations or large-scale air movements. We have also calculated the embedding dimension, which is a measure of the complexity of the system. It is the number of independent variables or the degrees of freedom which govern the system. An embedding dimension below 3 indicates a smooth and highly predictable system, whereas a embedding dimension between 3 and 5 reflects a combination of turbulence and mesoscale activity. So our key findings indicate that our horizontal winds are mostly quasi-periodic, while vertical winds oscillate between the deterministic and quasi-periodic states due to diurnal heating. And our recent data shows a shift towards more chaotic and turbulent flows since 2017. Vertical winds near the surface have a short delay, 3 to 4 hours, showing that they are driven by local solar heating. And at mid-level altitude, 700 hPa, the delays are longer, 4 to 10 hours, indicating a mix of local and large-scale atmospheric drivers. The study have consistently shown that an embedding dimension between 3 and 4 for both horizontal and vertical winds. This suggests that the pre-monsoon winds in Kolkata are governed by a moderate level of complexity involving both local convective heating and interactions with high-altitude jet streams. So in our future scope, we identify a massive opportunity for high-resolution radar studies. Unfortunately, we could not perform this analysis because of the absence of continuous radar data observations. But if we have access to such kind of data, we can perform finer scale insights into the data and use this radar-based data as a ground truth to access the fidelity of these reanalysis models and also extend this study all across India to capture the regional variations. So to make this future scope a reality, we are actively seeking for collaborations. If any of the researcher or institution has the UVW components or even data products like hail size, hail distribution or reflectivity, which can strengthen our research, we would be very eager to collaborate. You can see our mail addresses given here where you can get in touch with us. And with this, I end my speech. Thank you. Any questions?
Thank you, Indrani, for a wonderful presentation and keeping it at the right time. Thank you. And next speaker is Arup Borga.
We have a special guest here today with Dr. Kaishap Prakash. He is the person who has that behind the ST radar system in Guwahati University, along with Meenakshi Madam, who has all planning and support from right from the support from Assam government. He has done all the initial thing. So we are very proud to have him among with us. So we just want to felicitate him on our behalf of the organizing committee. I am just requesting Dr. Alaka Medi to felicitate Dr. Kaishap Prakash. Thank you. You can carry on, sir. Sorry for the interruption.
Yes, this is Arup Borgohai from Northeastern Space Application Centers. This is a kind of popularizing our wind profiler installed at Northeastern Space Application Centers. Then this wind profiler we installed in last years that in collaboration with Stract. Actually, Stract developed this wind profiler. It is available in our Northeastern Space Application Centers. Now, see, location of Northeastern Space Application, it is very special. We consider it as a very special wind profiler because of these locations. If you see Northeastern Space Application Center, it is situated in northeastern regions. It is here, and towards the northern part of this towards the north of this site, it is a Brahmaputra Valley. There is a valley and wind. There is always wind circulation is there. There is a katabatic wind and anabatic wind is there. We hope that we will be able to capture this wind with respect to our any weather events. This wind profiler is actually 427.5 megahertz wind profilers. It radiates around 330,000 watt per meter squares, and height range it captures even from 150 to around 1 kilometers. Then with a height resolution of 150, it is programmable, and velocity resolution is around 0.1 meter per second. It is a 12 into 12 by 12, total 144 area of this TR modules, and beam width is around 8.3 degrees. Beam positions, as you know, that zenith, north, east, west, and south, and this pulse width is 0.2, 0.5, 1.2 microsecond. It is also programmable. This is our wind profilers. If you see that we have a RF fencings around this wind profiler also. So this is rule of RF fencings. Everybody know that it is a kind of Faraday enclosures. It is a conductive mesh, and it reduces clutter and unwanted attenuation, because we have a lot of forests and there's unwanted signals are there. Because of that, we install this RF fencings for this wind profiler to improve this data. So this is the block diagrams of this our wind profilers. If you see that we use these time control systems through this rubidium clocks and RF generation around each 420.5 megahertz, and there is a TX RX chains. This antenna arrays, also receivers, RF and digitals. Receivers are there, processings. We have the processing systems. Along with that, it is whole process is coupling process. Overall, we will get this output through this with that wind output. There is a 5 beam setups, 1 vertical beams and 4 oblique beams. This is around plus minus 20 degrees from north, south, and west. And there's actually this is a electronics beam steering process. EBS process is theirs. It gives flexible beam pointings around plus minus 20 degree scannings through 6-bit phase shifters. And after that, we have this combined radial velocity from all beams with respect to U, V, and W. So this is our GUI systems. The WPPU GUI system is developed by Strax, and then with that we can log in all 12 by 12s. This TR system can be monitored. Health also can be monitored. One TR module, if it is down, then quickly we can get information from that. We can replace and we rectify. With respect to what kind of problem is there, we can find out. Mode of operations. To analyze data, we can do online mode of operation also. We can do offline mode of operations also. This is for online. There's we can select these online processings, and with respect to visualize data and other parameters, like a pulse width pulse width, programmable pulse width, beam tilting, everything can be done through this our GUI systems. And to analyze this data, what is the data we archive? For that, we can have offline mode processing. Through that, we can find out this UVW components. These are the data products. There is a zonals, meridional wind profiles, wind speed, wind directions, time and height vectors, wind selections, moment zero data, moment 1 data, moment to data and signal to noise ratio. These are these available data. You can see this raw data. If you see the raw data, this is a process of, these are this, because last year only we installed this, so it is a kind of raw data. So all series of raw data, we are seeing like that, there's a couple of around 30,000, 3,000, 4,000 data are here. From this we can average out these power spectrums. From the power spectrum, further we can get our wind products. These are the kind of wind product, UV, W, and directions products. Then these are another products. And we are obviously after this getting these products UVW, we need to validate this data, because we have a couple of some facilities is there. We have a tethered balloon and meteorological balloon platforms are there. Then we can simultaneously we can launch these balloons. We can use tethered balloons. Obviously, there is a tethered balloon is a control process, but we can use these meteorological balloons. We have these facilities. These facilities can be used to validate our wind profiler data. We are planning for that. This is a validation plant. There's a co-located radio center will be launched within this March. Then from there we can find out some statistics metrics to validate. So this whole process, because it is a kind of advertising that wind profiler has any students and any researcher group can come forward to get this wind data. We can, in collaboration mode, we can do good research on that. Thank you, sir.
Thank you.
What is the resolution? Height resolution, 150 meters. Yeah, it is programmable also. Up to 100 meters you can. Pulse is 0.2 microsecond. 0.2, it is also programmable. Nearby fencing? Yes, possible.
Very good. We have another special tag by we invite Basavi Radhakrishna.
Yeah, good afternoon. So sorry, because this talk is actually planned for tomorrow, but because of my schedule, I'm leaving today, so I'm giving the talk right now. This is the work done by Mr. Anuja Kanase. So she is a master student, and she worked on the GPMV of isolated and non-isolated shallow spreading systems over the oceans. So is there any new things which is already exist? Because many people have done the isolated and non-isolated shallow systems over the oceans using TRMMPR. But what is the new in this is, so when we saw some cases of shallow isolated systems, so shallow isolated systems, the characteristics of the raindrop size distribution is more or less similar to the deep systems when it produces heavy intensity rainfalls. So this is one thing which we observe over the Gadangi region, and whereas it produced almost like a monthly rainfall in exactly 2.5 hours. So in that case, the system's raindrop size distribution is quite different. So GPM can able to produce the raindrop size distribution. So we want to characterize what could be the raindrop size distribution for the isolated and non-isolated shallow systems. So before going to isolated and non-isolated shallow systems, how do we define the isolated and non-isolated shallow systems? If you see, there are two overpasses here. So you could see along this path, the vertical structure of precipitation. So there are certain events where this is the 0 degree isotherm, the echo top heights is less than 0 degree isotherm, which is associated with the deep systems. Whereas here, in this case, you see, there is no system which is deep as crossing the 0 degree isotherm. So the systems, shallow systems which are associated with the deep systems, we are calling it as a non-isolated, and where are completely isolated, these are the systems which are classified as the isolated systems. So here itself, you could see the mass weighted mean diameter, which is the proxy for the drop size. There is a large variations in the drop size distribution between isolated and non-isolated shallow systems. So this motivated us to see what could be the DSD variations during the isolated and non-isolated shallow systems over the global oceans. So when we go deeper into the systems, we have seen certain cases where the shallow, so you see here, it is a shallow systems which are connected with the deep systems. But TRMM is classifying it as a isolated shallow systems, but since it is entangled with the deep systems, so we modified some of these cases to non-isolated shallow systems based on whether it is entangled with a deep system or not, deep systems or not. So this kind of cases are less than 1% in nature. So that also we have taken care in the processes. So coming to the variability of non-isolated shallow systems. So this is the occurrence of shallow systems over the global oceans, which is well developed by the climatology of TRMM. So similar climatology is reproduced here, and these are the regions we have considered. But combining after seeing the DSD variations, so we have combined again, South Oceans is one ocean, North Atlantic and North Pacific, they are possessing more or less similar DSD variations, and North Indian Ocean is completely different from these oceans. So these are the three regions which we focused for further analysis. And if you could see the spatial variability of mass weighted mean diameter, and there is a large variability over the oceans, and with respect to isolated and non-isolated shallow systems, the isolated shallow systems has larger DM when compared to the non-isolated shallow systems, and these differences are at 90% significance level, they are significant. These differences are significant at 90% confidence level. Though this dot shows wherever they are significant, those are the regions where the differences between isolated and non-isolated shallow systems are significant. So when we come across, we know that DSD also varies with rain intensity. So whether the DSD variability, whatever we have seen between isolated and non-isolated shallow systems, is it because of the actual nature of these systems, or it is due to the variation in the rain intensity between these two systems? So to study that, the rain intensity normalized probability distribution functions are plotted for isolated and non-isolated shallow systems over the different oceans, and we could clearly see that the non-isolated shallow systems possess intense rainfall when compared to the isolated shallow systems, but the DM is larger for isolated shallow systems. Though the intensity is more for non-isolated shallow systems, the DM is more for isolated shallow systems. That means that whatever differences we are seeing in the mass weighted mean diameter between isolated and non-isolated shallow systems, this is not by the variations in the rain intensity, and it is the characteristic feature of the isolated and non-isolated shallow systems over the global oceans. So when it comes to the vertical structure of precipitation of isolated and non-isolated shallow systems, the CFATs of reflectivity is plotted with a conditional reflectivity of 15.5 dBz, which is the GPM, the threshold. So we could see the non-isolated shallow systems are deeper in nature when compared to the isolated shallow systems in all the oceans. So what could be the atmospheric drivers where we could see why the non-isolated shallow systems are deeper into the oceans means? So the first is the surface forcing, that is the SST. So SST is quite high when compared to the isolated systems when the existence of non-isolated shallow systems. So the surface forcing itself is driving more, as well as when you see the total column water vapor is also more, and the vertical integral of moisture flux is also, it is in the negative means it is more convergence, and the Kp is also more for non-isolated shallow systems, as well as the sin is less. So all these atmospheric features which triggers the systems can penetrate slightly deeper into the atmosphere for non-isolated shallow systems than the isolated shallow systems over the oceans. So here one more thing is there, that the non-isolated shallow systems are the remnants of the deep systems, where you have a weak echoes which is existing beyond the 0 degree isotherm level. That kind of echoes which are not detected by the GPM also can contribute to the vertical structure. But apart from the drawback of the 15.5 dBz reflectivity, but the atmospheric drivers is also showing that non-isolated shallow systems can penetrate deeper into the when compared to the isolated shallow systems over the global oceans. So when it comes to the vertical structure of isolated non-isolated system of raindrop size distribution, so here we could clearly see that this is the variation. So here the DM is almost like the maximum observable DM is for 3 mm for GPM, that is the threshold. But we could see a slightly more DM for isolated solar systems when compared to the non-isolated solar systems, and large NW for non-isolated solar systems when compared to the isolated solar system at all heights. And when it compares to the what could be the microphysical processes which are occurring, so the dominant is collision coalescence process, which is occurring more than 98% of the time over all the oceans. And where these differences are forming means, we have seen at the cloud top height what could be the mass weighted mean diameter at the cloud top height and what could be the reflectivity. It clearly shows that the differences are originating exactly when the cloud is forming itself, the differences are forming, and which are magnified by the collision coalescence process during the drop growth. So these are the conclusions from this study. Thank you.
Now, any question or anything to discuss? This is for all.
All 7 talks. Any questions you can ask me.
Or anything wants to say?
Like it is very well known, like GPM, the raindrop size distribution is always underestimated. They give very small size. Right. Your studies, my study, a lot of studies are there. So for a non-isolated system, I think it is a deep systems, right? Even though you have considered isolated, but the rain rate and other things, those are high. So do you think that is still further underestimated? That's why you are getting that result, or?
The maximum rain rate which we are observing during these cases is around 30 mm per hour. But GPM can measure up to 60 mm per hour. So I don't think the underestimation, of course, the DM is underestimated when compared to the actual observation.
Yes.
That will happen for both, not only for one system and another system.
No, I agree, but for non-isolated system, the rain rate is not so high.
But whatever images I have shown, that is the case. But when you see overall, I don't know.
That's okay, you tell me.
Overall, it is more for non-isolated solar systems. The intensities are deep, larger. Large occurrence of higher intensities are more for non-isolated solar systems.
Okay.
So that is what I told. This is basically not because of the rain rate variations. This is by the nature. Though it is more, the rain rates are higher occurrence of rain rates are more for non-isolated solar systems. The DM is small.
Okay, thank you.
So that is a characteristic feature.
Yeah. And one more thing, sir. Someone, Indrani Chattopadhyay, she has used the iRAD data. I think better, Prasad sir is also there. You should use the IMDA data. That is the much better as compared to the ERA 5, and then you cross-check your result. And is there any mean you have validated your result?
The problem with CUST radar that we observed was that there wasn't much data to validate with. So we had validated for only 4 or 5 hours. So we could validate the data, that the data was correct and the outputs were coming correct. But the problem is, since we wanted to take yearly data for a long time and continuous data, we could not get the data. So that is what.
So try to validate and please use IMDA data.
Yeah,
I'm not saying that don't use ERA data.
No, sure.
Apart from ERA, you just see the IMDA data also, and then you can find the result.
Okay, thank you.
Thank you.
Thank you for your comments, sir. And actually, if you see the IMDA data, you will get hourly data and real time. You can do that one when especially when studying that long period.
Yeah, that is what.
Any other question for any of the speakers in the session? Then thank you. We conclude this session now. In this session, we have one lead talk by Dr. T. Narayan Rao and 7 presentations. And all 7 presentations covered very well of various specific radars. One is the CUSAT, one is Calcutta, and especially Northeast SAC wind profiler is also recently coming up. And all the people, all the speakers invited young researchers to study their data. So please consider that one. And they introduced the radar sites and they have given the the capabilities. So please take studies using all these data sets. And I think other people also study the respective CUSAT data can be done by Calcutta University people. And like that we can revalidate the results and check the things. With that, I think I conclude. Anything you want to add?
Well, I just want to add that we are highly thankful to all of you for their wonderful presentation. And of course, now actually this world should be a collaborative world, and we should not work in an isolated manner, but rather we should all combine ourselves, and we should know that what other people are doing, and so that we can, what we are doing scientifically should be very good for our knowledge as well as for the society. So thank you very much.
Thank you. With this, we come to the end of our session 1. I would like to extend my heartfelt gratitude towards our chairpersons, Dr. Sanjay sir and Dr. Prasad sir, and all our presenters for their insightful presentations. May I now request everyone to kindly proceed to the dining hall for the lunch, and we will gather here for our second session after the lunch. Thank you.
दिशा 12 तक। learned that ChatGPT works.
chairperson is an Welcome back, everyone. We are soon starting the post-lunch session on day 1. May I request everyone to please settle down, and also our guests waiting outside may please come into the auditorium. We are soon about to start the session. Thank you.
stop wasting time applying for jobs on LinkedIn or Naukri or other online job portals. You know why? Because HR posts only 20% of the jobs on these sites, and most of them are entry-level jobs. But if you're a mid or senior level professional, you need to tap into the hidden 80% of the job market, because this is where you can find a gold mine of opportunities with higher salaries, great work culture.
A very good afternoon and warm welcome to everyone to the second session of the first day of the 8th conference on India Radar Meteorology. So welcome back everyone. Hope you had a hearty meal and we are all set to resume the session on day 1. For this session entitled Modeling, Data Assimilation, AI ML Application in Radar Meteorology, we have as usual a host of papers preceded by a lead talk by Dr. V.S. Prasad, and we have two chairpersons for this session, Professor Saurav Das and Dr. S.S. Kundu. May I request Professor Chandana Sharma ma'am to please escort our speaker and the two chairpersons onto the stage. I have the honor of introducing our chairpersons. Professor Saurav Das is a professor in the Department of Astronomy, Astrophysics and Space Engineering, IIT Indore, and Dr. S.S. Kundu is head Space and Atmospheric Science Division, ANISAC, Shillong. Before we proceed to the session, may I request Dr. Navajit Kumar Das, faculty in the Department of Anthropology, Guwahati University, to felicitate our guests. First, we begin with the honored speaker of this session, Dr. V.S. Prasad. He is felicitated with a gamusa. Thank you so much. Now, may I request Dr. Navajit Das to please felicitate our speakers, Professor Saurav Das from IIT Indore, with a Fulam Gamusa and a memento from Guwahati University. And may I request Dr. Das to please also felicitate Dr. S.S. Kundu with a Fulam Gamusa and a memento. Thank you so much. And now may I request Dr. Navajit Das to please introduce our speaker for the session, Dr. V.S. Prasad.
Dr. V.S. Prasad is a prominent figure in Indian meteorology, serving as a head of the National Center for Medium Range Weather Forecasting under the Ministry of Earth Sciences. He leads effort in advanced numerical weather prediction, focusing on developing next generation forecasting system for high impact weather, integrating supercomputing and AI, and supporting sector like agriculture and disaster management with precise forecast with extensive research in monsoon dynamic and NWP modeling. He played significant role in developing state-of-the-art data assimilation system and operational and ensemble forecasting system in India. Under his leadership, NCMRWF successfully carried out the first ever global reanalysis project in India. His main areas of research are data processing, satellite data retrieval, and data assimilation. Dr. Prasad published more than 100 scientific papers in various national and international journals. He has received many awards such as B.N. Desai Medal, Mosam Biennial Award, MOES Merit Certificate, GSPS Fellowship, and has also been elected as an IMS Fellow. Thank you.
Thank you, Navajit. Now we're all set to begin the session. May I request our chairpersons, Professor Saurav Das and Dr. S.S. Kundu, to please conduct the proceedings of the session. Over to you, sirs.
In the first instance, I thank you organizers and for giving this opportunity, and also introducing data modeling and data simulation in iRAD for the first time. And for the time, thank you for the, introducing that one. And also thank Chase and for kind introduction to that one. And special thanks to Professor Goswami for coming and attending this talk. And he is the leading NWP person in India, and made wonderful contributions in developing IITM into the world leader center, and we are getting the fruits of this now with the great presentation. And actually, what I want to tell this session, my main participation is that in India we have the finest. Government is giving a lot of importance to the NWP. We have the in mission mode projects we are working now. We have the deep ocean mission for the exploring the oceans, and also mission MOSAM, and successfully completed mission monsoon mission also. And presently with mission MOSAM, the government is emphasizing in the developing the observations. Earlier, we had done the theoretical works for the modeling, and now the emphasis on the data observations, and gone with a major emphasis relevant to this one. We are going to enhance our radar network, DW network, from 30 to 4 times. About 126 radar are going to establish all over the country, and such a wonderful occasion for the researchers to work on that one. Similarly, we have the under this project some super computing also, which is other thing which is available for the required for the modeling. It is going and last year September, Prime Minister inaugurated HPC systems of iRAD, ARCA, Arunika. They are the top 500 computing systems, and ARCA, Arunika are acquired by through MOE and CMRWF, and if you see that one, we are in the top. It is not there, okay. We are in the top 200 place who are there. ARCA is about 220, and Arunika 221 position in the top 500, and about 100 iRAD. This much computing system is available for the research, and our MOA systems are for the service, and the iRAD system is for the research. It is available this NSCM, and with that first time we are also getting for weather community the GPU nodes also. We have 18 GPU nodes in the Arunika system and 26 GPU nodes, and with that we are venturing into the not only the numerical modeling, even AML techniques also we are going to do that one. So this was the thing, and with this high computing system available, we are going to go to K-scale modeling as kilometer scale modeling, and our weather models, 6 kilometer weather model developed at IITM indigenously, calling Bharat Forecast System, and similarly in NCMRWF also we developed 6 kilometer model, as well as implemented coupled model along with our partnership countries. NCMRWF partner is a co-partner in the Momentum Partnership with UK Met Office and other leading centers. We are co-partnering in developing that one. So in that we coupled NWP also we developed. And as I said, with AML models also has been placed, and we are testing that one. And earlier under monsoon mission, we developed high resolution reanalysis. Morning we were mentioning that Indian monsoon IMDA data, which is about 12 kilometer resolution, hourly fluxes, and to study the biunal data also available. And that one is one of the most impact data is the most impact factor. After Dr. Rajivan's rainfall data, this IMDA reanalysis is catching up, and now it has more than 250 impact factor is seen in that one, and also more than 10,000 users are registered and using the data, and many papers many papers are coming up, a lot of university students also studying, and it is accepted, and such a data is developed. This data, and with present computing power, we are going to develop, work on the AML things. And AML, we are using also bias corrections and also data assimilation, and that are going to be used, that one. That is the one of that work I want to introduce here. And this is our 6 kilometer model, what we developed in this one, at NCMRW. This is the satellite picture. And this is the with the explicit convective scheme, and earlier the parameter scheme is there. With the 6 kilometer things, we are almost able to generate a picture of the good quality, almost this thing. But still, presently we are working with the data with ensemble techniques, so that we want to convey the stakeholders the uncertainty in the forecast. So we are making the system more robust, so that we can use it operationally with ensembling mode. That work is going on, but the results of this one are found, that one, and also this paper on this one already coming up, and Bharat forecast, is similar thing was done at IITM and also has been made operational. Then next, this is a global coupled NWP system that we are operational from 1st November on, now 21. We are calling Mithuna forecasting system. And it is the first ever coupled model for short range forecasting, short to medium range forecasting. The system is operational from 1st November, as I told that one. It is having the atmospheric, 3 parts of, for atmosphere, we have the 4D ensemble war system, and ocean 3D war, and land ensemble Kalman filter, EK based on the simplified EK system is there. So this system we are this completely operationalized. At present in the world, ECMWF is running the coupled model for the medium to short range forecasting, and UKMet is, and NCMRWF become third system to use the data coupled data assimilation system and coupled data for medium range forecasting. And what I call weakly coupled means the background field is first guess is from the coupled model, but all 3 DAs are separately run, atmospheric DA and ocean DA and land DA separately run, and these data will go to the model for initialization. And in the case of strongly coupled data assimilation, all 3 parts together is simulated, but the science is not so far they developed that way. It can be operationalized, but tests are going. In India also tests are going, and other tests are going everywhere in other places. But strongly data assimilation is presently not in the scale of operational scale. So this much complex system, people can work on the land data or ocean or atmosphere and contribute to the development of this one, the forecast. And totally, we have, with this coupled system, we have the seamless prediction system. We have 330 meters Delhi DM Chem model is there to give the forecast for the fog and visibility for Delhi airport. And for running such a high resolution model for downscaling, we have the 1.5 kilometer regional model. These two we are running particularly for the winter period for the pollution studies or in Delhi and also visibility studies. And regularly we are, there is 4 kilometers and CM model is there. And presently this is the system what is operationalized in the coupled modeling system. We have the 12 kilometer resolution. We are running for it 10-day forecast for 2 hours per 00 UTC and 12 UTC. As mentioned, we have these data assimilation systems here for the land and ocean. And this system, we have the 20 kilometer ensemble system with 44 members. Earlier we were doing 12 kilometers only with less number of ensemble systems, but ensemble members. But we thought that increasing the number of members is required more, and that's why 20 kilometers we are running. And there is another thing, the coupled model for giving the S2S forecast, we are running that at 60 kilometers. In near future, after getting the sufficient hindcast, we are integrating this global group forecasting and ensemble and coupled this STS system all together to single system. And we are calling it seamless and unified system such a way that means all the systems having the same dynamics. And of course, because of the resolution, there may be the change in the physics or things, but the dynamics are the same thing. There is no need to interplay so to the other things. If you run that, people are working at the WRF, other thing they know. They have to do other process for running the model. The major thing here is the contribution, what we do, shown that one, we have developed a strong observation processing system for the thing. We are getting from all 180 countries, we are getting the data to GTS. Similarly, we connected directly to the UMETcast broadcasting system. We are getting all UMETSat data, about more than 500 to 1 TB data is coming from the UMETSat. Similarly, from the ISRO and also NOVA and all 5 satellite countries, we are connected and getting the data together. And that is the same thing. And also for ocean, also we are getting the data from all the countries. And this part was added for the coupled model. And otherwise, earlier we had the ocean data processing system. This is a strong data processing system we developed, we implemented there. And India is the only country having the satellite data program and NWP also. We are working, so with ISRO we are working together and showing the improvement of the data. For example, this megatropic data was gotten in 2014 with Saphir radiances, which are become very popular, and also scatterometers from the OceanSat 3 has been well accepted with the countries. With the recommendations of the NCMRW, which is getting about good improvement with simulation of 180 GHz water vapor channels. Similar microsat 2B was launched for testing that one, and here the fast additive transfer also we developed everything in indigenously. Apart from the international satellites, what I mentioned, now presently the private players, commercial players also entered the data, and we are getting the data from the Spire, radio occultation data, Spire and Plantiq, and this data being operationalized. And other thing that tomorrow, another thing, LEO satellites, they have launched about 18 satellites. The data is available. And what I want to mention here, the satellite data processing and application, morning Professor Chandrasekhar is mentioning the data processing in operational means. Like he simplified very much with washing machine and running the cloths with that hand. Like that, in the operational system, everything has to be defined, has to come to real world time. And for that one, satellite meteorologists and also our ISRO team and MOS team worked together to develop such a good satellite program and other things. My main aim of attending this one is we are coming with a good number of radar data sets which are going to come out. Already about 36 radars are operationally running, but such a robust system of satellite data radar data processing is not available. I request youngsters to work on that one, and a lot of problems are there on radar, and to use it in operational scale, and also to show the various products and also improve that one. And NCMRWF, Dr. Amarjyoti is here. We are working for making a mosaic of all radars that is becoming major improvements are required on that one. Basically, as then we have the S-band radars and C-band radars, X-band radars of different makes, different companies make. In case of US, NextRad, same type of radars are available. And here we have the different company makes and different things for S-band radar, primarily for cyclone detection over the coast, and C-band radars are there over the other places to run the thing. And for the mountain, other regions, X-band radars are there. And if you see the scanning strategies required for that one, X-band radar, we thought that X-band radars will give good insight into the cloudburst and heavy rainfall that are occurring in the Himalayan regions and northeast region. But getting the data and signal, that one became a problem. The scanning strategy also has to be worked out, that one. And we have seen, now we have scanning strategy, it is X-band radar or C-band radar, all are same together, and they are taking 15 to 12 minutes, I think, scanning time. Morning we have seen Professor Chandrasekhar is telling a 2-minute interval strategy. So that strategy we have to work out. And actually, societies like people like in iRAD, we have to work with this scanning strategy entirely, left with the operational people and IMD mainly. The research works has to be carried. In a satellite data thing, we are doing the experiments called observation system simulation experiments. Before satellite launch and after satellite launch, what is the impact, how to increase the impact of the data. We are working through the system called OSSC for before designing, and after also OSC we are doing, and improving a lot. Things are coming up, and there are many researchers also doing that one. In the case of radar, we have seen people are working on the generating some understanding some schemes or all other things, but the operational product, what we require at a single go, we can get the unified product, so that we can use that one. That type of things are not working, and this is the major thing. Our part of present thing is what we would require here. The wind data. We are using the 3 types of data presently in our assembly. We are assimilating VAD winds, we are assimilating radial winds, and radio reflectivity from these data sets. These things has been operational. We are finding a lot of quality issues, quality control issues, and the scan parameters, what we are getting, this volume scan, this is the scanning mechanism which is required. Another major problem is handling the volume of the data. At present, people are working single world radar, and a few, we are seeing that NRL working with MST radar, and other people are working CU, Cochin University running single radar, that one. But when we are going to handle such a 126 radars in future, what is the data volume, what is the actual fields we have to keep? And about the strategy, we have to see the data volume. For example, when we changed the data, other format to IRA buffer and FSL format to IRIS format, we have reduced the required space by 10%, and say this. So the scanning strategy, parameters, and also the volume, what type of data, and how to store the data, without in satellites we have got the level 1B data, where our basic parameters to improving that one. Suppose any new understanding comes, to reprocess the data, we are keeping the level 1B data. If the level 0 data, we have a lot of space, it is occupied, this space is occupying, and also handling such a volume data become problem, so level 1B is the better. In that way, the radar data to handle on a regular basis for research or development work, other development, the radar data volume and what fields and what is the format has to be stored. That should be taken, that should be things. And also, we are at NCMRWF, as I told earlier, we are, of course, this one, for today's thing, we had in the radar reflectivity mosaic product to develop. Professor Chandrasekhar morning is showing that such a wonderful mosaic product that then developed. So how to develop a mosaic product? We have the IIT radars, IMD radars, and Department of Space radars, and all together to make a regular mosaic product, that is more important. Another thing, we are at NCMRW, we are generating a radar satellite mixed product for rainfall, to get the every 15 minutes rainfall. And for that one, the calibration of rainfall of all radars, not only the MOS radars like that, not all radars, that is challenging. And this product showing little bit encouraging results, but still not that much satisfactory. It is a preliminary effect that we are doing. So these products, what we are generating it and similarly being used by all the IMD and other people, IMD and operational also. These products improvement. This is a challenging thing to come up for verification. We are for verification, the model development, the rainfall, and also this thing. And also, another my colleagues are going to present in the next session, downscaling the radar data for every 15 minutes. Using generating a product every 15 minutes rainfall for adjusting the model for model verification, and also a lot of applications are there now, RE other things. So we are my colleague will present that one, that ML rainfall downscaling and what is the results we are getting. And we are using this data with getting the amount of radar data every 10 minutes. We want to use high resolution rapid refresh things. Earlier data simulation has every 6 months window, but with the radar data we want to generate the products every hour using all the data, especially to study the thunderstorms over the Himalayan regions, something, this high resolution rapid refresh. In this, we want to simulate radar reflectivity, the thing, and at present, because of the radar data quality, we are nudging the observations. When we are going to simulate radar data, because of the quality issues, we find other problems. But to avoid that one, we are doing every 15 minutes radar data nudging. And giving the forecast for 18 months, 18 hours. To improve these things, and we required high quality control observations and good for reflectivity things. This also a challenging task. And at present, of course, with the nudging itself, we are able to catch some high resolution with subsynoptic scale rainfall and subsynoptic scale systems has been well captured with this radar nudging itself, and this shows that rainfall the results are not improvement because the audience here are mostly the radar data people, but these challenges the results what I'm showing is to only in qualitative state to study that the radar data giving the impact, very things, and other data we are able to get the synoptic scale things with subsynoptic scale resolution, granularity. We are getting the assimilation of the radar data. So this is the most encouraging things, and I'm skipping this one, and we show this quality things improvement that I want to present, but I am skipping because of the audience here. We improved using the simulation things, the cyclone forecasting things are improved, and I'm skipping these things. And the coupled models also, I want to show that they're responding. Suppose cyclone is forming in the Sri Lankan region, the ports that we are giving the ocean meteorograms also. The ocean response is, you can see, we are getting the ocean response well before cyclone that disturbance arrives, long away. This shows that coupling systems working well. That I want to show that one, and also the improvements I'm skipping. Another important thing is using our reanalysis data sets. Morning people are working on that one were available. These IMDA data sets for 1979 to 2020. Now we are continuing IMDA-like products and also NGFS global reanalysis. Especially these reanalysis for studying the extreme rainfall things are found very useful, and many papers that what I mentioned is coming up. And using this our data sets, we are going to enter into the AML models, and these models also are in place. Actually, they are trained now. They are trained with IRAD data, but initialized with the Mithuna, our own reanalysis, and we are trying to train our data with our reanalysis data sets. And first, what we want to demonstrate it is these things are working in condition, and we are going to replace these background training methods with our reanalysis data sets, and we'll get our own products. And if you see the comparison, if extended the physics-based model is taking 47 minutes for running the to 1.5 hours to run the cyclone. This is a
initialized forecast. Now, these are Pongu weather. What is plotted here? Wind.
Wind and precipitation.
Precipitation is.
No, wind only. Only wind only showing that one. All are not giving the wind. Only Fengu.
Precipitation.
Not precipitation.
Rain on precipitation.
No, the Fengucast is one model. It got the wind precipitation also.
Yeah, but they have not tested.
No.
So, even large scale they cannot do.
No, large scales, general, not precipitation. Wind, other things are temperature, wind.
You are giving the impression that you can do precipitation. I think that will be very dangerous.
Actually, this Fengucast, we have the Pangu weather, we have the precipitation also.
There is precipitation, but they never show the scale of precipitation because they cannot do.
Yes.
Because there is no precipitation data which can be trained on hourly precipitation.
You are correct, sir. Even now, we want to see extreme weather, extreme winds or cyclones, are they capturing or not, recurring cyclones. Those things we are testing. Yes. No, same thing we are telling, sir. Actually, if you go to this our conclusion, we are showing that only this Pangu weather we are able to get some precipitation here. Some precipitation, but no. So actually, we are studying that one. Actually, these are how whether not validated. Skill.
They get the large scale the small scale fishers.
Those things we are still working. Actually, these we started recently only, in the last 1 month or 1.5 months, and we are studying whether they can normal weather it is getting, whether extreme weather or extreme systems or cyclone or anything it is able to capture things that we are studying, and we'll come up with the statement soon.
Yeah, I think precipitation is something that I think the AI models are still it is not even thought about. That is why and they know that they cannot do it. That is why they are not publicizing it. So I think from our side, people like you should not give the impression to the politicians that you can solve the problem, because this is a research problem. First of all, we need training data for that, and there is not enough training data to train precipitation, even on the weather scale. The synoptic scale, there is not enough data, good data to train. And
those things are accepted.
And
another thing also, resolution. 0.25 higher resolution things, whether how they are coming. We are not giving any statement that they are we are under, these are the experimental thing also, and we want to come up with a statement whether they are capable of producing extreme weather or not.
I think you should make that very, very specific. I think that will be useful. Otherwise, it will be very misleading.
No, we're just showing
the research problem that is going on. I think under this national mission now, the AI mission, we had a meeting and we had discussed, and I think nobody can promise prediction of precipitation even in the next few years because there is not enough data. So we should be very careful because this is a challenge. I think globally nobody, in India I think not many people are actually working on this global AI models, And even people who have been working for 10 years in the others, Google, DeepMind and others, they are not able to do because there is not data. So I think when you present this in a way that to the public and the politicians, policymakers, we have to make very, very...
Sir, I made clearly that at present we shown the capability and we are using ERA 5 trained model and we want to replace it with our own trained models, our own things. Okay. And for that one, we want to use our reanalysis thing. And also, we are planning to come up whether...
Actually, you cannot use your reanalysis. I have checked your data. The IMDA, the reanalysis, because those reanalysis data use your hydrostatic model for analysis, hourly analysis.
No.
Hourly analysis.
Sorry, I refer that one. We have the IMDA data is we have the fields, and that is possible. And also our people are working on that one. And actually, how to trade these things we have already studied, and we're working on that one. That's why. Only I defer last statement that IMDA data and other reanalysis data.
No, you are giving an overview of a lot of things you have done. I think there are a lot of good things you have done, but I think we should not give the impression that we can do everything and we can deliver everything to the public. I think that is a very bad message. Okay.
My aim of presenting here is to, I'm telling that the radar data, other things, development requires, things are required, like satellite data. The radar community also should come up with that one, not only leaving to the operational agencies, processing the data things, and also coming up with the mosaic products, how to do that one, and quality control. And these are many issues. What we are doing, I am also showing that one, the reflectivity when we are receiving directly, we are not getting good results. We are nudging the data to compromise on the use of the radar data because of want of quality control.
Okay, thank you.
Thank you. Thank you. Time is over, so I'm stopping here. No, it's okay, it's okay. Main thing is conveyed.
So, thank you, Dr. Prasad. So, any question from the audience? Only 2 questions I can take, if there is any question. If there is no question, you have any question? Okay. Thank you, sir, for a wonderful talk. Okay, now I would invite the participants one by one. So the first one, Shankho Shupro Chakraborty. Okay. Priyanka Srivastav. So you have 8 minutes plus 2 minutes for discussion.
Good afternoon, everyone. So, okay, I think some of the fonts have changed, but okay. So, I'm Priyanka Srivastava, I'm from Aries, and I would be presenting our work where we have used radar data and machine learning to characterize and predict atmospheric structure constant. And this was done with my colleagues at Aries and some of my interns who came from Banasthali and Christ University. So, as an outline, I'll start with the background and importance of the structure constant, briefly describing what our site is, the methodology that we have used to derive the CN square. Finally, we'll come to how the vertical variations come up from radar and compare them with ERA 5. I'll tell you why I use ERA 5 later. Then the temporal variations and their comparison, and finally the We'll evaluate machine learning models against these. So this atmospheric structure refractive index or the structure constant, it is actually used to quantify the intensity of turbulence and the strength, which is strength of it, which is caused because of temperature or humidity or general clean air turbulence. We have already had a very good talk by Dr. T.N. Rao. And we know that this is an important parameter and which relates to the clean air turbulence, so it is important for the aviation safety. It is also important for boundary layer physics. Another application which is less talked of and is more important in our concept is that it can be used for determining the astronomical seeing, because when the light is coming from a star, it gets blurred because of the turbulence. It is much more complicated compared to the flat terrain in the mountainous region because of the gradient and the orographic effect. So our objective is to establish scalable real-time framework for optical turbulence prediction in this complex terrain. This is not a work which can be done in one stage. So at present, we have restricted ourselves to characterizing CN square and then predicting atmospheric seeing or astronomical seeing. So for those of you who would not know our site, we are at Aries. This is a mountaintop site at 1958 meters above mean sea level. And in the background, you can see Haldwani, which is a plain site at 400 meters. This is about 300 kilometers from Delhi, near the IGP region. And IGP, you can see, is like this is carbon monoxide. And you can see that it is a very polluted region. So we are in close proximity to the IGP pollution. Another important characteristic of the site is that in July especially, the ITCZ reaches our site. So it is one important feature where we see these synoptic scale things. And why we were interested in the astronomical seeing was this place is a hub for astronomical observation. We host Asia's largest 3.6 meter optical telescope at the site. So we need air which is like free of turbulence, and of course that is not possible. So we need corrections which come from the knowledge of these structure constants. So at Aries, we are hosting the first ST radar, the wind profiler one, which operates at 206.5 megahertz. It's a 3-element Yagi-Uda antenna with 588 elements. We will have a dedicated presentation by our engineering lead, Dr. Samreshji, on this. So I'll not spend much time here. These are again some of the parameters from the radar. So in my talk, I'll be using ERA 5, so it's like 31 kilometers, roughly 0.25 degree resolution hourly data from 2020 to 2023, other than the radar data of the same period. Then we use the machine learning models like gradient boost and LSTM, which is a recurring neural network. So we want to characterize seeing. The astronomical seeing is connected to the fried parameter, which is in turn connected to the integral of the structure constant. So if you have a radar in place, what you can do is you can use the SNR from radar to get the radar reflectivity, calculate the volume averaged structure constant from there, and get the local structure constant. And in that you would need F, which is your fraction of turbulent volume, and that you can get from your Brunt-Weisseler frequency for troposphere and stratosphere. If you do not have a radar and it is not functional, and if you need it for a long-term basis, what you can do is you can use some model. Here I have used ERA 5 to just demonstrate, but I'll show that if you really need a scalable approach, you will need to replace it. So with ERA 5, what you can do is you can use this equation where L0 is your outer scale of turbulence. I regret that this, I think there's some problem because of the change in system. So the fonts are now correct. But anyways, so this is the outer scale of turbulence for troposphere and stratosphere. And you can have the vertical gradient, which is connected to wind. So here, this outer scale is connected to the wind shear, which is a function of height. And again, a vertical gradient, which is vertical gradient of generalized potential refractive index, which is a function of pressure, temperature, and potential temperature. Okay, once you have it all set, you can derive your Cn square. So this was done by one of our members from Aries, Aditya. And what we found was that 63% of the turbulence source was coming from the lower troposphere, which is also expected. And this was the main source of turbulence degradation. But in the upper troposphere, the convective shift in the monsoon and the upper tropospheric jet at the side affects and degrades the seeing quite a lot. Then we show that if you are very tempted to use ERA 5 for the same purpose, you cannot do it. So if you're planning some telescopic measurements at another Himalayan site and you think that, okay, your models can do it, unfortunately we show that ERA 5 smoothens most of the vertical features due to its coarser resolution, of course, and it fails to represent the high turbulence due to the jet or the monsoon region. So even the synoptic scale features are not well captured. So in terms of the seasonal pattern, so the red ones are poor seeing, which is 0.7 above, and this is 0.7 below. So you have bad seeing here, and ERA 5 again cannot capture the seasonality even. So I'll just rush. So this is like, we did the model evaluation with radar data, and with radar it is giving excellent predicting power of like 0.84. And this is like the actual versus the tested data for 2023. So small to moderate turbulence condition, very good. Higher ones, we need more training data. So this is for 2020 and 21, and this is the testing data is for 22. We did it for ERA 5, and we used LSTM, but it was having overfitting. How we know that? Because training data has a higher R square, but the testing one has a lower one. So XGBoost did relatively better, but still if you compare, obviously radar data is much better. So this was like a preliminary work where we show that we need much higher resolution regional models as set already by our previous speaker with radar data assimilation to get a real scalable fraction. So this is a summary of whatever I said earlier, and that's it. Thank you very much, and I'd like to thank our supporting staff at Aries. And yes, we have postdoc positions, so those of you interested in being at this heaven-like site, you're most welcome. Thank you.
Any questions from audience? One question you can take if may not be there. Okay, we'll see at the end.
Okay, sure.
Okay. Yeah.
Yes,
So when you are talking about prediction, so you are predicting in time, or what is your input and output? I just missed that part.
Okay, so currently we have used two kind of, like I showed LSTM where one of the inputs is time, and in the XGBoost we have used mostly SNR from the radar data.
Okay, so
yes.
you are predicting what?
We are predicting the Cn square once we have the SNR as one of the features in XGBoost. In LSTM, we mostly have like time, temperature gradients, and shear as the features.
If you are using two different type of parameters,
yes.
then you cannot compare the model performance.
Yes, precisely. And the reason behind doing that is to go to a regime where, one, we have observational system forecast, and we can compare it with a model-based forecast using AI. So the advantage would be that if you know that your observation system is working good at one side and your model is able to do well in this scenario, what you can do is you can scale, and you know that your model capability, like the global model capability or your high resolution model capability is at par with the observational system, you can rely on it much more. Okay. So that was the main ideology behind this two approach. So we want to converge using that.
Okay, thank you.
Okay, thank you.
Yeah, please. Okay, so next speaker, Joydev Shaha. Yeah.
So good afternoon all. So my work is, there is a improved simulation of rainfall over Northeast India. So 4-dimensional variational data simulation system of Doppler weather radar data, wind reflectivity and radial velocity. So we are using this process, this procedure in a manner which is called high resolution rapid refresh data simulation approach. I will explain it. So this is the outline of my presentation. So the motivation is there are very high impact convective events involved with different microphysical processes. So we need high resolution mesoscale models which can be configured, very high resolution, also rapid refreshing, like hourly assimilation, like that. So there are Doppler weather radar data available. There are GPM radar data also available. GPM data also available. So we need some we have developed HRRR, that is high resolution rapid refresh data simulation system, with our regional ANCOMAR forecast model, which Prasad sir also already explained. So for that we have set up two numerical approach. That is, one is control without radar reflectivity and radial velocity data, and another is our experiment with the radar radial velocity and reflectivity data. So this is the reflectivity and radial velocity, reflectivity and radial velocity simulation. We are simulating reflectivity and radial velocity only. So in challenges, before going to the simulation, there are many challenges that already many of the speakers have explained. So these are the issues that we are facing before assimilating radar data. And also for that we need to do some quality control, and there are there are some approaches, and there are different approaches for nowcasting, assimilation, or rain rate estimation. So we are using multiplicity scheme. So after quality control, maybe you can see the we have a range like 1, 0 to 1. There are different, you can give different thresholds. So we are giving thresholds like up to 1. So 1 is something which is we call like a good data. So after giving the threshold after quality control, so this much data we have left in our hand. So we can use this data. This is contamination free. So I will use these data in an event of an event of 7 June 2021. This is the model configuration that we have, I think sir already explained. These are model domains. So I'm using regional and NCM model, and we now presently call it Mithuna NCM regional model. So this is the domain of my study, and the left side is this is the actual model domain. This is the domain that I am used in my study. I've used in my study. So for our NCOM RDA system, we have observation pre-processing system. So this would actually take the background from the the forecasts from the previous cycle, and then it will process this will be also fed by the global telecommunication system GTS and plus radar data, radial velocity and reflectivity, and also we will be giving observational data. So this will configure the data into the format, VAROPS format, that will go to the 4D word, and then we will do some atmospheric optimal analysis increment. Analyze increment something that the model have the model analysis that have produced and minus background. So it will incrementally updated over a time, and after that we give the forecast. These are the radars the stations, the data that we are taking in our usually in our operational work we use these stations for radar data stations. So we can't directly assimilate radial velocity or reflectance. So for that we need the operator, because the radial velocity operator, the model has some different UV actual wind field, wind vectors, but the radar we have the motion, so that the radial velocity operator must be projected in the three-dimensional model UV and W into the radar beam, into the radar beam. So it should be projected into the radar beam. So we are taking the UNV, not the vertical wind injection W. And for that we do super observations. So we are not taking the observations directly. I mean, like, we are not mean the observation and taking. So for that we need to do the super obs, that we need to average the innovation, and then we have to take the background, like that is XB. So I am not explaining that much because of scarcity of time. So we also take the reflectivity operator. Both we need to take operator. We can't directly assimilate. And this rapid refresh hourly simulation cycle. So first of all, we need to give we take the, first stage is the cold start. So the system starts with the global forecast, and then it is reconstructed and downscaled into 1.5 kilometer analysis. And then we have, for 19 to 00 UTC, every hour observation is feeded, and for every hour the background is taking from the previous forecast. So it is hourly updated refreshing system. So we are taking the data background from the previous forecast, hourly forecast, and also observation also feeded. And up to that we run 6 cycles, and then at 00 we are giving long forecast for 72 hours. So this is we call the high resolution rapid refresh. This is based on model. There is another high resolution rapid refresh model that this is run in our office, which is based on a WRF based HRR system. So this is the evolution of the convective system in Agartala. So this is the brightness temperature taking from MOSDEC, and this is the situation. This is the convective cloud structures from the Agartala radar. So with we have checked with DWR, GPM, IMD, and SEMAWF merged product. This is the 4 kilometer product of our regional model. This is the control run. Control run is this is HRR system, high resolution rapid refresh, but without feeding the reflectivity and radiance. And HRR is this is the experiment with the radial velocity and reflectivity. So with that we can say this is the truth observation. There are many observations like DWR, GPM, but we are taking the truth of this IMD and SEMAWF, so we can best matches with the HRR system. We can see the closely associated with the IMD and SEMAWF merged product. So for the skill score, if you see the ETS values, equitable threat score, it is relatively high in HRRR, and in all the we have checked with all the thresholds, and it is clearly deduced that the high intensity of the rainfall is well simulated by HRR then in the control experiment, and also in the early stage the equitable threat score is higher in the HRR model. And if you go, away from the time from the forecast, so that you will get the ETS values are quite lesser. But in the early stage, we are getting good skills. And this is the improvement. Reduction in bias. So if you see the bias in HRR, and there is a very good difference. So increased with the forecast time, the bias, and also for long forecast, more uncertainty. HRR is consistently below control, so that our experiment is giving the better forecast. And every forecast hour, HRR has the lower bias. And so after like 18 to 24 hours, the difference reduces. It is closely merged. And if you see another thing is that you will see the peaks. So if you see that HRR is very close to the GPM and also DWR, and the peak is now. You see, you can see that the HRR peak is HRR is giving the early peak, then the GPM and also DWR close, but control is giving it's overestimated and also very like very early peak. So we can see that our experiment is improving the forecast. And if you see the, RMSE values, the total error is very less in HRRR, and this is the volume, displacement and pattern errors. So so this is a total. So if it is like 50, if it is 60 and this is 50, so this is the total of the the division of how this total percentage is defined in HRRR, and this is the total, how the total is leveled in control. So total for the vector displacement, so it is actually measures the directional error, so or orientation mismatch. So HRRR has the better alignment, less angular, so this means the less angular deviation and more accurate motion prediction, lesser displacement from the actual observation. So these are the conclusions that I have already discussed. Thank you so much.
Yeah, thank you. Any question? Yeah, microphone please.
Quality control, quality control criteria, but what have you used for quality control?
See, we have used some multiplicity scheme that I've already shown. There are some filters that we are using, but in case of like contaminations are different, so we don't have like different for different contaminations. We don't have that much of robust quality control scheme that we can detect different contaminations or different clutters. So we are using this multiplicity scheme, and which is equivalent for all kind of clutters and in contaminations. RFI, it is.
Hello. Yeah, I was just wondering that you are assimilating every hourly, right?
Yes.
But in every hour, say DW data, when you talk about, you will have 5 scans in 1 hour, 12 minutes if you go by. So how are you doing? You're taking the last scan for assimilation, or DWR?
You are taking the first scan, but we are taking the first scan, and for if it is hourly, so the satellite observations that we are feeding.
No, I'm talking about DWR. You are assimilating DWR data also, yes, no? In this entire India. So your scan is 12 minutes. I think 3 minutes there is a break probably. So in 1 hour you will have 4 volume scans. Now when you assimilate at a particular hour, prior to that you have 4 volume scans. So how do you assimilate? All 4 you assimilate, or you assimilate only 1, or you take mean something?
No, we are taking integrated.
Huh?
Integrated.
The last one only probably, huh?
Only 1 per hour.
Only 1
so
per hour.
We are not doing any integration of mean and all.
Mean will not be a good idea also to do.
And it will lead to erroneous data. Too much we cannot feed, and that is one of the reason we are doing the super ops, where the thinning of the data is done, and we do quality checks. So based on the quality flags, the data is processed, and only the good quality data is goes for the assimilation.
Right.
Thank you.
Yeah.
So in the DWR wind, what technique you are using for VBP, VAD? Which wind you are taking?
Which one?
You are taking wind, right?
Sir, I will answer. He is actually an assimilation expert.
I am not aware.
So for the winds, we have different methods. One is region-based and phased, and then 3D. Right now, the operational method, whatever we are using, is 3D de-aliasing. I think after some time, one of the other speaker will be presenting in detail how 3D de-aliasing we are doing on radial winds.
Okay.
Thank you.
Thank you. Thank you. So next paper, Mohammad Amjad Ali.
So I am Amjad Ali, working as a project scientist at NCMRWF. And my work is on machine learning based downscaling of GPM iMerge precipitation at 1 kilometer. So we have taken a 10 kilometer resolution data and convert it to 1 kilometer resolution data using the radar over the Arunachal Pradesh. So here is the road map, and we'll go step by step, like why we need this, then our study area, then the methodology, and finally I will share the results and conclusions. So why do we require this high resolution rainfall data? So I will discuss the problem first. So the current satellite product, like 10 kilometer resolution data, is not sufficient. Like for our Arunachal Pradesh, like 2,000 to 500 millimeters of annual rainfall is gain, and the extreme variation is like within a few kilometers, and it has a serious impact like flash flood, landslide, and the agricultural damage, and the hydropower disruptions. And at 10 kilometer resolution, this whole application is simply too coarser. So we required a 1 kilometer data to capture these local variations that occurs the disaster. So this is our study area, and this is our Arunachal Pradesh, Northeast India. So we can see that the terrain and the elevation, which is ranging at 150 meter to 7,000 meter, and making it as a most challenging region in the world for estimation of rainfall. And during the monsoon season, the daily rainfall exceeds to 200 millimeters. And importantly, like this, windward slopes receives 3 to 5 times more rainfall than these leeward slopes. And this orographic enhancement we want to predict. So this is the data source what I have used. The first one is iMerge version 7 satellite version at 10 kilometer resolutions, and the second one is ground truth, which is the radar gauge adjusted, which is basically made by me only, and the third is SRTM digital elevation model, and here we are computing the slopes, aspects, and TPIs, and I'm showing here the 2022-74 data, and the radar data also for same date, and the SRTM data at 1 kilometer. So here I will discuss the fundamental challenge, like why does simply we can't interpolate to 1 kilometer directly. So basically what we are seeing here, this iMerge shows the smooth and average precipitation. We can see that a single 10 kilometer pixel cover both the valleys and ridges. So, but in reality, this windward slopes receives 200 to 400 more rainfall, and the valleys and ridges are completely different, and it's random. So if it doesn't, it's not random. Basically, we can see that it follows, the variability is follow the physics, and this physics we want to capture. So after understanding this, our primary objective is to develop a machine learning framework to downscale iMerge from 10 kilometer to 1 kilometer. And here is the complete methodology for my model. So we are starting with this input data, and this data is processed, and this processed data is ready to compute the features, and now it's ready to feed any machine learning model to learn the features. And here we have used 3 models which is working together to give a better rainfall estimation at 1 kilometer. So here we have engineered this physics informed feature into 4 categories. And basically here we are not capturing and fitting the numerics. Just here we are encoding the physics. And these are the features I have listed down. And now coming to our first approach, which was direct prediction. So we can see that the images and comparison like iMerge at 10 kilometer and the truth and the direct prediction. We can see that our model is able to learn the complex nonlinear terrain relationships very well. And this is my second approach. We can see that here also it is basically preserving the iMerge spatial pattern. So here we want both the terrain effect also and the spatiality also. That's why we have merged our final model, and based on the final model, here is the final model structure. Basically it's predicting the weight into direct prediction plus 1 minus weight of enhancement prediction. So basically it's trusting based on weight, it's trusting which model at particular pixel to trust. And here is the validation strategy. We have kept 30% of unseen data for test data, and the performance metrics are using like RMSE and MAE for error magnitude, and R square for variation explained, and POD and FAR for detection of the rainfall events. And here is our overall performance comparison. We can see that. So here we can see that the bilinear interpolation gives the RMSE of 24.5 mm, and the nearest neighbor give the 26.8 mm, and our hybrid ensemble is giving very low RMSE and high R square value. We can see that the 90% of the improvement in RMSE versus bilinear, and 91% improvement in RMSE versus nearest neighbor. So here is we have also done the spatial distribution error check, basically where our model is struggling and where it is giving its best output. So we can see that where is the low error zone below the 10 mm, we can see there is a high elevation plateau and clear orographic signal if we receiving, and our radar coverage is like very well, then we have a less error zone. If we have a high error zone, then we can see that there is a deep valley with complex wind pattern and the radar coverage gaps is there. So here we can see that the errors are not random, it's correlated with the complex terrain effects, and we can see that our model is learning the meaningful relationship between the terrain effect and the rainfall. So here is the heavy rainfall event detection results. We can see that the POD is 72% and the false alarm ratio is only 2%, and the critical success index is 0.71%, which is perfect for precipitation estimation. And here is we can see that it's able to also detect the heavy rainfall events. And now this is the future importance, and this blue bar is denoting the terrain features, and the green bar is denoting the terrain feature, and the blue is the for iMerge features. Here the top 5 most important features are also shown. And here is the study case for heavy rainfall event. We can see how beautifully the truth data is able to capture by our models. And this is not just for the research perspective, it is also ready for our operational implementation at our NCMR WF. And we have our Arunica system, and where the 1.9 petaflop is basically dedicated for AI research and work. So I am planning for make it operational for our at NCMR WF using this our high computing system. And here I am using the uses of GPU2, which is giving much more faster training, as we have used the XGBoost. So it has a feature to give the fast training. And here we can show that why our hybrid ensemble it beats the individual. We can see this scatter plot, and the values are correlated with our hybrid ensemble. And we have also done this uncertainty analysis, where we can see that the iMerge have a intrinsic error 15% and the radar calibration at 10%. And we have
you have to conclude. You have to conclude. Time is long back over.
Okay. It's almost done. And this is the real comparison with the published paper. and limitation of future work. So basically, I have only trained for monsoon focused and may not be generated for other seasons. And we required a good coverage of the radar. And the future improvement will be like using the deep learning or transfer learning and can be applicable to other regions too. And coming to conclusion, so we have developed a hybrid ensemble machine learning framework, and it's also proven that the 3-component design is also have its own cons and disadvantage. And it's also for Arunachal Pradesh, it's giving a very good results, and it is ready for operational deployment at NCMR-WF. Thank you. If you have any question, please, you can ask.
Yeah, any question? Because from Northeast region, yeah. Okay. One we can take.
I'm sorry, maybe you explained, but can you just tell us the ground truth at this high resolution that you have used?
Yeah, actually, I have taken the gas data at which is at point location, and I have also taken the quality control radar data which is at 1 kilometer. So I have did the rainfall generation, and I have using the ML model, I have adjusted it to make like a real truth, and I have also used climatology for background to give accurate truth data at 1 kilometer for my model purpose.
How did you make the background, sorry?
Yes.
How did you make the background?
With climatology of Arunachal Pradesh past 15 years.
With radar as well as the gauge data?
Yes.
Okay, thank you.
Yeah, I have many questions actually, but I will discuss with you. But one point only I wanted to know, that in your title you have written that it is using radar observations in Arunachal Pradesh. Actually, but I think there is only one radar in Mohanbari which hardly captures 10% of, not even 10% of Arunachal Pradesh. I don't know, how it justifies that?
So actually, I have made the condition if there is a gauge data is available for more than 50 district. So I have give a preference to gauge data more, and with background I have used the climatology to cover the region.
Okay, I have not fully understood the process. I'll talk to you because it's very important. If you have really done it and the kind of statistic that you have shown, if it holds for a long season, then it has a huge potential for this region, for flood and for many other applications. One point more, SRTM data you have shown 1 kilometer resolution. Why 1 kilometer? SRTM is available in 30 meter.
What's that?
SRTM DEM is available in 30 meter also, no?
At which we are running this
No, are you, see,
downstream.
normally DEM resolutions are told in terms of height variations,
Yes,
not in terms of spatial variation.
Actually, when we run this regional model, so we have processed that regional model to that 1 kilometer domain. The same
1
DM.
kilometer, that's a spatial, you are let
Spatial.
long.
Yes,
But
yes,
DEM
yes.
resolutions, when we say, we tell in terms of the height.
Height and all. So, but then here
So
we
1
have
kilometer is
used-
not height, right? It's
no,
only
it's not
spatial.
height.
Then
It's a
it's fine,
spatial.
Yeah, it's spatial.
Okay, thank you, thank you. Yeah, next is Haritha Meka, there. Yeah. Sujata not there?
Neha Rajput.
Good afternoon to everyone, and myself Neha Rajput, working as a project scientist at NCMRWF. And my today's topic for presentation is the impact of 3D unraveling de-aliasing on radar radial velocity, a simulation for intense rainfall prediction over central India. So it is the outline of my presentation, that how it will go. So let's start with introduction. As we all know that radar data is very high, radar measurements are very high in spatial and temporal resolution. And thus it is very important in short or long forecast, as well as in cyclonic case and intense rainfall cases. But every observation has their limit, and some limitations are there. The radar data is also have limitations. As my topic is on radial velocity, so I am talking with about radial velocity. Radial velocity limitation is, it's a Nyquist velocity limitation, and it results in aliasing, velocity aliasing. And if we assimilate aliased data, it will impact in our analysis and forecast. It will give you damaged rainfall forecast. So we have to alias our de-alias radial velocity, because it is very important observation to correct the wind field in convective storms and this. That's why we can't aliased velocity, we can't assimilate. So we have to do de-alias of the radial velocity. And other than radial velocity, we have other challenges also for radar data assimilation. My colleague has already talked with these challenges, because we have a data quality issue, ground clutter and birds attenuation, radar sampling limitations are there, velocity, what I am talking. And then computational constraints are also there in radar data assimilation. So as I'm talking for radial velocity, so these are the methods, some methods to de-alias the radial velocity. Region-based, where are the 2D region-based, 3D and 4D, as per their dimension, this region-based methods are there. Continuity-based, phase unwrapping method is there. Reference-based, where we are taking external input to de-alias our radial velocity with our traditional method. Temporal, where we are using previous radar volumes to de-alias the radial velocity. And hybrid, one or two events, methods we used to de-alias the radial velocity. For the study, we have choose 3D de-aliasing. Why the 3D de-aliasing? In conventional 2D de-aliasing, what they are doing for elevation and ranges, not individual. But in 3D, what it is taking radar data as a volume in all 3 dimensions. So it enforces vertical and horizontal continuity because of its structure, its how it is working, and it reduces the isolated correction error also. That's why we have choose this 3D de-aliasing method, and it has also its own limitations are also there what we have faced. But this is a 3D de-aliasing methodology. What we have means how it works. So it analyzes the radial velocity in full 3D radar volume, what I have told already. It will correct in azimuth, range and elevation, all 3 dimensions, and then it will identify coherent velocity regions. And then final with some quality control and threshold, it will give you as a de-alias radial velocity. So we are doing de-alias radial velocity assimilation, but on which radar data we have used C-band polarimetric radar data located at the Atmospheric Research Testbed of IITM Bhopal. And this is a scanning geometry of this radar. This temporal resolution of this radar is that every scan is coming for us on every 6 minutes. This is what we have. This quality control reflectivity and raw radar velocity and de-alias. It has improved the radial velocity. Now we have done assimilation. So in our experiment we have set 2 experiments. One is control, where the radar data is not going to assimilate only conventional data, so on radio sonde and surface observations are going to assimilate. And in experiment 1, 3D DLS radial velocity with this conventional data is going to assimilate. And 4 hour assimilation cycles are assimilated per day, and analysis and 6 hour forecast we are going to produce. And these are the parameters what we are using in assimilation. And model configuration, for the assimilation we have used NCOM regional model, which has a 4 kilometer temporal spatial resolution. And for the method, assimilation method, we have used a 4D VAR analysis method. And already this my radial velocity operator and other configuration already discussed earlier, so I am not going to discuss more on this. And these are the results. We have done for assimilation for 2 cycles. We have selected 2 cases for 11th September of 2024 and 12th September of 2024. For that, we have assimilated 2 cycles, 6 UTC and 00 UTC. As we see the number of points, for 6 UTC cycle, we have around 3 lakhs, and for 0 UTC, we have 1.5 lakh points are there. So this huge number of total points showing the robust radar coverage data. And number of points assimilated is around 7 to 9,000. And it is which points we have assimilated. We have with 3D DLSing, we have given a radio sondes also as an external input to make our DLSing robust and that quality. And we have assigned using this radio sonde, we have assigned 3 quality flags, good, bad, and moderate. So only for good quality flag data we have assimilated, and we have this much number of points. And RMSE is also improved, and this improvement, reduction in RMSE shows that DLSing methodology, whatever we have, taken, it is working. And wind increments are for the 11th September 2024 at 850 hectopascal. For zonal wind, we can see that there is an increment, positive increment over the study region what we have selected. Why we are seeing this wind increment? Because wind increments, wind is directly governs, improves the, if better wind analysis is there, then it will be moisture transport, it will affect the moisture transport and convergence, and they directly affect our this convective rain. So wind increment also we have to see, and we can see that positive increment is we have for zonal and meridional wind, and same for 12th September also we can see over the study region the increment is there. And in temperature also the positive increment is there around 0.5 to 0.7 degrees Celsius. And this is the 3 hour accumulated rainfall for control and experiment. We can see that in experiment it is a very organized and coherent and near the central India radar domain. And this is the forecast impact. In forecast also the experiment is more aligned, have alignment with iMerge, that is the observation, satellite observation rainfall. And it improves the rainfall, this structure. So this is the summary that we have successfully implemented the 3D DLSing method for the C-band radar over central India. And actually 3D DLSing method we have already operational for IMD, what we are getting in our operational center. We have already operationalized this, and this DLS method we have implemented on NCOM regional method, and this assimilation has a significant improvement in low level winds, zonal as well as meridional. And the rainfall also improved with this experiment. And thank you.
Any questions? No, you have anything? Yeah, thank you.
Okay,
thank you very much. Vaibhav Tyagi. Acha. Bhaskar Saharia. There?
Good afternoon. Myself Bhaskar Jyoti Sohoria, and I am from Department of Information Technology, Guwahati University. I am a research scholar. So I am here to present my survey. The topic is a survey on atmospheric humidity estimation and weather forecasting in the northeast region of India using cascaded and ensemble machine learning approaches. So those are the contents I will describe in my study. That is the introduction part, aim and objective of the study, cascaded and ensemble learnings, different approaches, then ST Radar Center, literature reviews, and the conclusion part. First one is the introduction part. Atmospheric humidity is a key factor influencing cloud formation, rainfall, and overall weather behavior. Accurate estimation of humidity is therefore essential for reliable weather forecasting. However, regions like Northeast India pose significant challenges due to their complex terrain, heavy rainfall, strong monsoon influence, and rapidly changing atmospheric conditions. Some traditional numerical weather prediction models often struggle to capture local and small-scale humidity variation in such regions, mainly because of strong orographic effects and limited observational data. So, recent advances in machine learning and deep learning have provided effective alternatives in conventional forecasting methods. Those data-driven approaches can learn complex and non-linear relationships directly from multi-source datasets such as radar, satellite, and reanalysis data. So coming to the next one, that is the Northeast. So Northeast India is chosen for this study because it repeats one of the most challenging weather forecasting regions in India. It complex because of the complex terrain, strong orographic effects, heavy rainfall, and rapid moisture transport from the Bay of Bengal. Traditional numerical models often fail in this region due to sparse observations and coarse resolution, especially for humidity estimations. So, the northeast region of India with intriguing dynamical and meteorological aspects such as wind structures, cloud morphology, monsoon troughs, tropospheric temperature, boundary layer characteristics, and different short and large scale variabilities. So here in these two images we have shown some complex. In the first image we have shown the complex topography of the northeast, and the second image we have selected sites, means we have selected some sites where we can compare the models, means we can compare the models how they evaluate that particular sites. So this is a figure that how the challenges of weather forecasting in Northeast India is happening. That is, in the figure we can see that the heavy, moist and warm air is coming from Bay of Bengal to the region, to the northeast region. Due to that situation, strong convection and orographic lifting is happening in that region. Due to that, the weather condition is changed, and weather condition changed to frequent storms, variable humidity, and microclimates, due to which the nonlinear and unpredictable is occurred. So, aim and objective of my study. The first aim is to utilize and analyze recent machine learning approaches for humidity, atmospheric humidity estimation, and weather forecasting. The second one is to study on cascaded and ensemble models that evaluates their effectiveness, limitations, and applicability in the northeast region of India. And last, to utilize satellite and reanalyze data in our directions to research for improving regional forecasting accuracy along with the ST radar data. So, the cascaded and the ensemble machine learning approaches. The ensemble machine learning approaches using many models together and taking their combined output so that mistakes of one model are corrected by others. And the cascaded learning means using models step by step where the output of the one model becomes the input of the next one. It is shown in this figure. It is how ensemble and cascaded machine learning approaches is working. So now coming to the next part is the ST Radar Center, Guwahati University. So it is monostatic Doppler wind profiler radar that operates at 212.5 megahertz with a minimum of 4 megahertz bandwidth. And it has 576 antenna components. So for better understanding of the weather and climate, atmospheric radars, a state-of-the-art is very useful tools in recent times, where high-definition wind parameters are important assets for such study. So the STR is such a system that can provide very high quality and parameters from near surface to beyond tropopause. So STR does provide sophisticated and wind profiling technique which has a wide application since understanding the physics and dynamics in development of monsoon, cyclone, worst weather situations, thunderstorms, etc. So now the system description, it is a very high frequency stratospheric tropospheric radar STR. It is a power monostatic phase array radar installed at Guwahati University. The 576 number of Yagi Uda antenna arranged in a circular array. So some major subsystems are, it consists of antenna array and feeder network, transmit, receive modules, RF sections, TR module controller, power supply exciter, digital receiver.
Your time is about to over. You still in introduction only. Go to your results.
Okay, sir. So this is the basic block diagram of STR. So those are the important parameters. This is 5 beam construction, that is for all the directions. This is the power spectra output from the ST radar that are collected from the ST radar for all the directions. And this is a echogram presented for wind components. This is the component one. And this is the bird view of the ST Radar Center. And literature review means I have reviewed some previous work papers related to my study, and some of the important papers are given here along with the objective methods and dataset they are used. Results, sir. I have just survey on the topic, sir. No results till now, sir. So those are some of comparison defined learnings methods. So these are some literature identifications and selections. Some of the approaches, defined approaches. Then perform evaluation from the previous work. The radar and satellite fusion. Those are some regional characteristics of Northeast region. And this is the conclusion part, that is, weather forecasting in Northeast India is particularly challenging due to its complex terrain, strong monsoon influence, sparse observations, and rapidly changing atmospheric conditions. This study shows that machine learning approaches, especially ensemble and cascaded models, perform better than traditional methods by effectively capturing nonlinear atmospheric behavior. The integration of ST radar satellites and reanalyzed data further improve regional humidity estimation and forecasting accuracy. Overall, data-driven and multi-sensor fusions frameworks offer a promising directions for improving reliable and region-specific weather forecasting in Northeast India. So those are some references of related papers.
Okay, thank you. So is there any question for him? Okay, if not, I have some suggestion for you. I understand you are first year, right? A PhD student starting your. So whenever you give next time a presentation, don't just read out. Okay, I am a teacher, so I am just giving you that suggestion. So we can read. Whatever you have written, we can read. If you are reading the same thing, that is actually confuses people. Okay, and the second thing is that you are doing a survey of the paper. How many paper you have read for this?
25.
25 is a very small number. Okay, you have to expand that and be very focused. You cannot talk everything in a single survey paper. Okay, so these two are suggestions. So you just please take care of that in your next future. Best of luck.
Thank you, sir.
Just wanted to know, what is your PhD topic? You're a PhD student, right?
Yes, sir.
What is your PhD topic?
Sir, weather forecasting, humidity estimation using AIML.
Why you're mixing weather forecasting and humidity estimation together?
Sir?
Humidity estimation and forecasting difference, you please read out. I mean, see, and then see whether it is really justified to club these things together. Okay. Estimation, humidity estimation and weather forecasting. You know, weather forecasting itself is a big business. Okay, okay.
Okay, so the last talk of the session, Washima Tasnin.
Yeah, good afternoon to one and all present here. Myself, Washima Tasneen, from Vellore Institute of Technology, Department of Energy and Power Electronics. So, my paper today is regarding machine learning for sustainable climate planning in Northeast India. So, these are the contents of my presentation. So, coming to the introduction, the Northeast India, it is encompassed by the eastern Himalayas, the Patkai range and the fertile Brahmaputra and Barak valleys, and it has a humid tropical climate with hot summers and then heavy monsoons and mild winters. Rainfall is mainly gives sustained forest, but it also leads to the flood. And the winter starts from October to February, which are cooler and drier. Now, based on this, I have thought to analyze the rainfall and flood predictions with some machine learning algorithms. So for that, different parameters are considered. So I will be coming to that. Regarding this topic, I have done a literature survey with, which uses different data sets, and it uses different machine learning models, namely the random forest, the logistic regression, and there the accuracy, precision, recall, and F1 score, those are compared. So these are the reference numbers given. I will not go into details of that. So these are some of the machine learning models which papers are being using. So during the literature survey, I have also come across that from 1984 till 2024, what is the trend of the rainfall occurring in the northeast region and also the flood patterns. So if we see into the flood patterns, so from 1984 to 1995, the major states that were affected with floods, and the main years, 84, there was massive flood, then 88, and then 91, like that, analysis I have come across, and I have put that here in the tabular format. And then with that data, I have gone to the NASA Power website and collected the data from that. And the major parameters which I have considered, I have just mentioned it over here, starting from the temperature, the humidity, the specific humidity, then the temperature, minimum and maximum temperature. So these are around some 14 parameters that I have considered. And the main prediction is like occurrence of the flood. And the different machine learning models that I have considered are these 7: decision tree, random forest, with and without grid search, then SVM, which is support vector machines, with and without grid search, knife base, and then gradient boosting. So these are some machine learning models which I have implemented. And the data set which I have collected, that is pre-processed, removing the outliers or the missing values and all. And then the classification reports and the confusion matrix I have plotted. So in the classification report, there are certain parameters which decides the accuracy or the viability of the model, which model is better. So these are the different parameters: the accuracy, the precision, then the recall, and the F1 score. So the formulas are also I have given here. Accuracy, we know it's the predictions which are correct. Doesn't matter whether they are positive predictions or negative predictions. Like that, the precision, where prediction is the main parameter, or the recall, where the truth is the main base. And then from that precision and recall, we get the F1 score and then the support. And then with those, we can get the confusion matrix. And after applying it, I have just plotted the precision, recall, and F1 score for the different models here in a graphical manner. And then I have given the confusion matrix here. So we can see that in random forest, in the classification model, it is there. We can see that low and moderate, it is predicted 769. It is predicted as low and moderate, but actually they are the severe affected zones. So like that, we can study the confusion matrix. So the confusion matrix for the random forest, the SVM without grid search, these are. Then with grid search, these are the confusion matrix. Then the naive Bayes and the gradient boosting. And then the decision tree model. So here we saw that random forest without grid search gives a better accuracy, but decision tree, actually it's giving a quite a better result, which is hard to be so true, but with the existing model, this is giving as the result. And SVM with grid search is giving the least accuracy and more error. Coming to the conclusion, this is only with the data which I have collected from NASA Power. Now CNN, RN, and those techniques also can be used. In fact, they are used with the radar data, which people have already shown in this conference. I'm quite new to this. This is not my area, but with the knowledge which I gain in some small period, I just thought that I will be able to present this in this conference.
So thank you. Is there any question for her? Okay. So do you have any question? Okay. So again, I have a couple of suggestions. Yes, first is that you are assuming the whole region and taking a single time series, or you are taking grid values?
Yes, sir. Whole region.
Whole region is single time series. Okay. So first suggestion is essentially you can use a gridded data that might improve your result. Second is that you are trying to identify different type of flood. That is what you are trying to classify, right?
No, not different type of flood, but severity of the flood.
Severity, based on severity. So the most severe one, that will be the most important one. So yes, you are putting at the top, basically that is your true values. This is the low flood regions, but that you get many times, but that may not be actually important. The severe one is the more important for you. So this is a class imbalance problem. You have to be very careful to handle that thing.
Yes, sir, just one, are you talking about the table which I showed?
So this confusion matrix,
yes, sir.
that first one is essentially the true value, that is usually your model is taking. but the low one is not that significant.
No, yes, sir. Sir,
Yeah.
while presenting, I said the lower one.
Yes, so you just check. My
ha.
apprehension that is the lowest one because the number is so high that it is taken as the true value, and the model is tuned to predict that thing. But that is practically we are more interested to know when the extreme cases will happen.
Yes, sir.
Okay, so these are
Yes,
two
sir.
suggestions.
Yes, sir.
Yeah,
Yes.
nice
Thank
one.
you, sir. Thank you, sir.
Yeah, I think with this, this session concludes. As we have seen, this session started with an invited talk by Director NCMRWF, Dr. V.S. Prasad, and then we had 10 papers in this session, but 4 others were not present. Therefore, 6 others presented their papers, and we had a good time. We are, of course, a little late, and I thank organizers for this opportunity as well as thank Dr. Das for the opportunity, and I will request Dr. Das to also have his.
Yeah, so this is a wonderful session about the different aspect of the modeling starting from NWP to AI. And we understand that there are a lot of potential scope and need to do more research on this particular domain to assimilate the data. There are lots of observational data. Instruments are coming in India. So there is a good time to jump into this domain. And that's all from my side. Thank you for coming to the session.
Sincere thanks to the chairpersons for their chairing of the session. So this brings us to the close of the session, and we take a small break for about 10 minutes. Tea is being served outside, but I'd request you all to please reconvene here in about 10 minutes time, as we need to restart our final session of the day on time. So see you in 10 minutes. Thank you.
আছে নেকি ক'ব লগা মৰমৰে মইনা চৰাই ঐ বুকুত আজি ৰৈ 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 বাজে ঐ বাঁহী এটি বৰ 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 মিঠা কৈ বুকুত আজি ৰৈ 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 বাজে ঐ বাঁহী এটি বৰ 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 মিঠা কৈ
হাঁহিৰা চলেৰে ঢাকি ৰখা মোৰ দুখৰে গধুৰ মালিকা ভুল কৰিছা কিয় মুকুতা নহয় চকুলোৰ হেমালা গাঁঠিছা জেতুকা পাতৰ দৰে সেউজীয়া সাজ মোৰে ভিতৰিতে জল ৰঙানো
মৰম হৈ ফুলি আছা ফুলিয়ে তুমুহি আছা মৰম হৈ ফুলি আছা ফুলিয়ে তুমুহি আছা মৰমৰে ৰঙা বেলি ঐ বুকুত আজি ৰৈ 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 বাজে ঐ বাঁহী এটি বৰ 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 মিঠা কৈ বুকুত আজি ৰৈ 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 বাজে ঐ বাঁহী এটি বৰ 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 মিঠা কৈ বুজানো বুজাৰে দুমুজাতে মোৰ কাকে দেখি হিয়াখন পৰে জোৰ বুজানো বুজাৰে দুমুজাতে মোৰ কাকে দেখি হিয়াখন পৰে জোৰ আই ঐ শুব নোৱাৰো আই ঐ খাব নোৱাৰো আই ঐ এয়া জানো মাথো মোৰে ভুল
ৰিপ ৰিপ মলয়া নানিবা কপাব নোৱাৰে বুজিবা হৃদয়ৰ গহন বাগিচা কিদৰে অতীত পাহৰো পাৰো বুলিও চোন নোৱাৰো প্ৰণয়ৰ কোমল দলিচা
ভাল লগা ভাল পোৱা এৰাব নোৱাৰা নিচা গুণগুণাই গান গোৱা নহলে কবিতা ৰচা তৰা বচা আকাশতে ঐ নাচে আজি আবেগৰ নীলা ছৈ উজাগৰে যায় 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 ৰাতি বৈ নাচে আজি আবেগৰ নীলা ছৈ উজাগৰে যায় 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 ৰাতি বৈ আকাশতে ফাকুখানে বেলিটিয়ে নৰা চিঙা সুহুৰিয়ে কামিনীয়ে মুখ 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 কাষলৈ খনে খনে নৰি 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 খাতলৈ বুকুতাজি ৰৈ 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 বাজে বাঁহীয়েতি বৰ 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 মিঠাকৈ বুকুতাজি ৰৈ 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 বাজে বাঁহীয়েতি বৰ 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 মিঠাকৈ তোমার হাঁহিতে খরা মুকুতারে গাঁথমালা তার বাবে তোমার কিবা আছে নেকি কব লগা মৰমৰে মইনা চৰায় বুকুতাজি ৰৈ 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 বাজে বাঁহীয়েতি বৰ 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 মিঠাকৈ বুকুতাজি ৰৈ 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 বাজে বাঁহীয়েতি বৰ 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 মিঠাকৈ
হাঁহিৰা চলেৰে ঢাকি ৰখা মোৰ দুখৰে গধুৰ মালিতা ভুল কৰিছা কিয় মুকুতা নহয় চকুলোৰ হেমালা গাঁঠিছা জেতুকা পাতৰে সেউজীয়া সাজ মোৰে ভিতৰিতে জল ৰঙানো
মৰম হৈ ফুলি আছা ফুলিয়ে তুমুহি আছা মৰম হৈ ফুলি আছা ফুলিয়ে তুমুহি আছা মৰমৰে ৰঙা বেলি বুকুতাজি ৰৈ ৰৈ ৰৈ
We are just about to begin the third session of the day. May I request everyone to please assemble in the auditorium and take their seats. Thank you.
हेलो और ये चालू तो होने दो और यहाँ से भी कर सकते हैं आपका विषय इधर से भी कर सकते हैं आई थिंक यू कैन कॉल देयर आर सम अदर आउटसाइड यू जस्ट मेक अनाउंसमेंट
let's start. Yeah. So hello and welcome back to the final session of the day 1 of the 8th conference on India Radar Meteorology. So we have with us Dr. Sachin Deshpande as the lead speaker and also a host of paper presenters. And we have as chairperson Dr. Subrata Das and Dr. Takahashi. May I request Dr. Navajit Kumar Das to please escort our speaker and the chairpersons to the dais. I have the privilege of introducing our chairpersons. Dr. Subrata Kumar Das is a scientist at the Indian Institute of Tropical Meteorology, Pune, and Dr. Nobuhiro Takahashi is a professor at the Center of Orbital and Suborbital Research, Institute of Space, Earth, Environmental Research and Graduate School of Environmental Studies, Nagoya University, Japan. We welcome you, sir. And may I also have the opportunity to request our speaker to please take his place on the dais? Sir, please. So now I request my colleague, Dr. Navajit Kumar Das, to felicitate our speakers and the chairperson. We begin with felicitating Dr. Sachin Deshpande with a Fulam Gamuza and a memento from Guwahati University. May I request Dr. Navajit Kumar Das to please felicitate Dr. Nobuhiro Takahashi, professor from Nagoya University, Japan, with a Fulam Gamusa and a memento. And may I request Navajit to please felicitate Dr. Subrata Kumar Das with a Fulam Gamusa and a memento. Thank you so much. And now may I again request Dr. Navajit Kumar Das to please introduce our speaker, Dr. Sachin Deshpande.
Thank you. Dr. Sachin M. Deshpande is a scientist at the Indian Institute of Tropical Meteorology, Pune. His research focuses on understanding the structure, evolution, and physical processes of convective cloud and their organization using remote sensing observation. He has conducted research on convective storm, mesoscale convective system, heavy rainfall event, process understanding of convective system through joint analysis of remote sensing observations, and high resolution model simulation. He has also contributed to the establishment of atmospheric research test bed in central India and the urban radar network in Mumbai. Thank you.
Thank you, Dr. Das. And now may I request our chairpersons to please take forward the proceedings of this session. Over to you, sirs.
Yeah, thank you. So, welcome to the sessions of microphysical studies and the dual polarization radars. And the lead speaker is Dr. Sachin Deshpande. I just want to know if Amit Kumar is available. Yeah, he's there. Dharmadas Jos from NCESS. Anyone is presenting? No. Jyoti Sharma. And Vivekananda Panda. Vivekananda Panda is there? Okay, so with that, let us invite Dr. Sachin Deshpande, and he will be talking about tracking the structure and evolutions of MCS in the monsoon core zone through satellite radar and lightning synergy.
Yeah. Good evening, everyone. I'm happy to be here for giving this lecture. Thanks to conference organizers and the Guwahati University. I'm going to talk on the MCS, which are the largest form of a deep convection, and how we are going to measure the MCS, track the MCS, characterize the MCS through multi-platform remote sensing using radar, satellite, and lightning data set. Because all these are complementary data sets, how to best use all these convection measuring data set for tracking the convective sails and the MCS. And I would like to thank my co-authors, Manisha, Abhijit, Rupraj, Murli Krishna, Subrata, Amita, Ashruba, and Harshad for their involvement in this work. So this is the outline. I will start with what is MCS and why they are important, what are their implications. The area of this research is in the monsoon core zone, which is the central India. Why it is important for the monsoon prediction and monsoon variability. The synergy between different observational data sets that I would touch upon. Briefly, I will discuss about the methods for identification and tracking these MCS, and because the MCS has a different structure compared to the individual isolated storms. They are composed of different storms like deep convective core, stratiform region, the anvil parts. So we'll discuss about how these different parameters contribute to the MCS life cycle. And the results are covered into three different parts, the spatial temporal characteristics of MCS. Then I will also discuss about what are the 3D structures and the embedded storms, how they are contributing to the formation of MCS, and some microphysical features, because now we are having the dual polarization radar. So how these dual polarization radars, in addition with the lightning, that characterize the microphysical structure. So what is MCS? So deep convection in the atmosphere takes different forms. Sometimes they form as isolated convective storms. Sometimes some of those cells, they grow upscale and form a very organized structure. This is called as MCS. So the picture on the left is the schematic picture given by the house. This is a cross section of a MCS call line. So MCS is a convective cloud population which consists of shallow convective cells, medium convective cells, deep convective cells. So they form ahead of a large stratiform and downdraft area. So they are defined as, so these are the largest form of a deep convective storm. They form when the convection gets aggregated. So aggregation means when they are coming together. So how do they come together? By interacting with the different storms. So basically these storms are the basic elements for the organization of a convection. So that's why it takes a very large area, and that's how this organization has helped the convection to survive for more than several hours. So if you see the convective cell, normal convective cells, they are within few minutes to maximum 1 hour. But these large scale systems, they survive for 10 to 24 hours, and they produce a precipitation, very large precipitation. That's how they are major precipitation contributors. And why they are important? Obvious reason is that they account for more than up to 50% of precipitation in the tropics. Within MCS, there are regions of stratiform convective. The measure of the precipitation from the MCS comes from the stratiform component. Almost up to 40 to 60% precipitation comes from the stratiform component. And due to the stratiform component, the latent heating profile of MCS becomes the top heavy. Okay, compared to the convective clouds, the stratiform component has a heating maxima in the upper troposphere, and that's how it interacts with the circulation. So it makes the more importance on the circulation concept. If you consider this shallow isolated convective cell, they don't impact the upper troposphere. So the circulation impact by the MCS is very large. And majority of, many studies have shown that there is a sudden rise in the tropical precipitation. That has accounted due to the increased MCS frequency. And MCS also has a societal implication because they produce heavy winds, large rainfall, lightning, hail producing storms. So there are many reasons. Apart from that, But the challenge is that all these organized systems are not well represented in the conventional models, all because these are parameterized convection models. They have coarser resolution. So all these organized convective structures are not well represented. Like for example, the CFS model, which is a operational model for monsoon prediction. It is also a climate model, and over the period it has improved, but it has a long-standing problem of a diurnal cycle. The diurnal cycle peaks at very early stage. It has a dry bias over the Indian, central Indian region. Okay, that's a monsoon core zone. So there are many reasons for not well representing the organized convection. And that's why the precipitation over the central India is less as compared to the observed rainfall. So that's why the dry precipitation bias is persistently there in the all operational model, not just the CFS. But there are studies that as the computing power increases, we can run these models at very high resolution, like a convection permitting. So these models allows the convection to simulate realistically. So those models are now show the features of organized precipitation. So over the period, all these high resolution models will become a global models, cloud resolving global models. So we need to simulate all these features. So one of the reasons for not simulating this representation is that because of the the spatial structure, the timing of the convection, and how does the transition from shallow congestus to the deep convection. This transition is not represented in the parameterization models. So now let's discuss about the monsoon core zone and the research testbed that what IITM is developing for the last couple of years. As we see during Indian summer monsoon, the rainfall is characterized by 3 strong convection areas. One is over the Western Ghat, the other one is over the central India, and the one lies in the northeast part. Over the monsoon core zone, we know that this is the region where all the synoptic systems frequently form. And that's why the convection over the central India is very deep, and that it produces widespread rainfall over an extended period of time. So we must characterize these convection feature into different ways. So like for example, what are their spatial structure, diurnal cycle, what are their life cycle evolution, the precipitation characteristics of a MCS system, and how these systems are controlled by the large scale environment. So considering all these importance of monsoon processes, IITM started establishing atmospheric research testbed, which is a highly observational facility. It is a permanent observational facility spread over a 100-acre campus of a different, and we have different co-located measurements characterizing your clouds, convection, precipitation, radiation. So there are lots of measurements, and these data sets are continuously available. We also know that this area, there is an increasing trend of extreme rainfall. So the central India has its own importance. So there are different ways of identifying the convective sails from one scale to other scale, like a mesoscale convective system. So if you consider the sail as a 1 kilometer dimension, so MCS has a 100 kilometer dimension. So we can use the multi-platform remote sensing synergy, like bringing your satellite data, the radar data together, and characterize the cold cloud system. So there are different ways. I will not go into much detail, but using this satellite-based data set, we track the large envelope of a MCS. And once that MCS has passed over a radar domain, we use the ground-based radar data to identify the internal subcomponents of that MCS, whether it is a deep convective core, stratiform component, or non-precipitating anvil clouds. So this multi-platform remote sensing has actually helped us in providing the MCS statistics. So for GIS 2023, we identify more than 90 cases of MCS. These are well sampled MCS cases for which the radar data was also utilized. And then we tried to understand what are the structures of these different components of MCS and how do they vary as a function of MCS life cycle. Because different components evolve at a different stages of MCS, and that's how they contribute to the MCS life cycle. And to understand the electrification inside those storms, we use the lightning location network data from IITM location network. So that's how we brought the radar data, satellite data, and lightning data in a synergic way. So this is just one example. The figure to the left shows how does the MCS tracking works, and the figure to the right shows how does the non-MCS cases. Like for example, these are small size convective cells. These are short-lived, but they are numerous. These are long-lived, but they are less in the numbers, but they have large contribution to the total rainfall. So this is just one example, and you can see the embedded storms, how they are characterized as the MCS forms. You can see the convective areas, precipitating stratiform, the non-precipitating annual clouds also. Okay, so this, from here onwards, these are the composite analysis based on more than 90 cases of MCS observed by the radar. So the main takeaway is that these MCS persisted for several hours, and they travel hundreds of kilometers during their lifetime. And these pictures are the MCS precipitation statistics, like average number of MCS, the precipitation produced by the MCS, and what are the total contribution of MCS to the observed rainfall. Because observed rainfall, if you divide into two parts, the MCS precipitation and non-MCS precipitation. And you see that over this region, it is close to 40 to 60% rainfall is there. That is contributed by the MCS. And if you see the diurnal cycle, because the diurnal cycle is another important parameter for the convection, and you can see that the minimum brightness temperature happens at around 18 hours in the evening. That's the time when the MCS occurrence is also maximizes. So these two peaks. The next, this is the mean diurnal cycle for different components of MCS, the convective core, stratiform, and anvil. So different lines shows what are their hourly variations. So this is the mean hourly variation for all MCS. As you can see, the frequency decreases from midnight to late morning, and it peaks between 16 to 18 hours in the evening. And compared to, if you consider the aerial contribution from different components, compared to other components, the anvil cloud has a large aerial coverage compared to your convective core and stratiform. And their diurnal cycles are also much smaller as compared to the anvil cloud. And then obviously there is a lead lag correlation between the stratiform cloud and your convective precipitation. Then we analyze the distribution of different MCS properties and its components. Okay, because just to know that how does the convective core influences the stratiform life cycle or the presence of anvil cloud. So we can see that 50% of the MCS has a radius less than 350 kilometer, and they achieve cloud top temperature less than 206 Kelvin. And many MCS have broad areas of intense updraft. You can see that. So they can, because this is the one matrix which discusses about the intensity of the convection indirectly. So these are the areas of intense convection at 8 kilometer. So you can see that this peak is there, and that actually characterizes the areas of intense updraft within the MCS. So these are the different metrics that characterizes MCS in a different way. And if you see the distribution of mean precipitation rate for convective and stratiform, they are almost similar, but if you see their the magnitude and 90th percentile, so there is a difference. And compared to their areas, like this bottom panel, this is convective core, stratiform cloud, and anvil cloud. The contribution from the anvil cloud for the total area is much larger than the areas of your convective and stratiform precipitation. Since this is the C-band radar at atmospheric research testbed site is having dual polarization capability, so we tried to explore the polarimetric measurement just to know what are the different polarimetric signatures that they carry for the MCS and their subcomponents. So this is the same animation. And the top figure is this is the snapshot at mature stage of MCS, because this we know this is the track. This is 19-hour longevity MCS. So this is the starting of your MCS track, and this is the end of the track. So these plots belongs to the mature stage when it acquires the largest area. So around that time, if you can clearly notice there is it shows very typical structure of a leading convective line and a trailing stratiform region. And around the same time, if you take a cross section, you can see this is a cross section along AB. So this is a cross section through the stratiform region. You can see the well-defined melting layer and the ice structure also, and it has a very deep. This is a uniform structure. So horizontal expansiveness also is explained in this stratiform. And if you take the cross section, this is the convective line. You can see the areas of intense reflectivity. So these are convective cores, and the corresponding polarimetric measurements are also shown here. Next, we analyze the lifetime evolution, because MCS has a different stages: initiation, mature, dissipation, depending on its convective cloud area, then the precipitation features. We can identify at what stage the MCS is there. So on the x-axis, you can see these are the hours since detection. Okay, and on y-axis there are different variables that characterizes the MCS. So one major feature, what we see that these areas, they show a steady increase from initiation to the mature. Okay, and then after mature, there is a constant decrease. So there is a roughly first half of the MCS life belongs to the upscale growth of a convection. Okay, and once it matures, then it starts dissipating. So this is a composite picture. During mature stage of MCS, the number of convective core peaks and they acquire largest horizontal dimension. So this is again another good matrix that determines the area of a convective core inside the MCS. Okay, so and you can see that there is a sharp increase here in the convective core, and this is the another. These are the number of convective cores versus convective core length. So you on one side you have number of convective cores, the other side the matrix that is the area of that convective core. So that also follows the typical life cycle of an MCS. And since this is a polarimetric radar, we try to explore some polarimetric signature. There are two variables. One is differential reflectivity and other one is KDP. So this is a specific differential phase. And what we did, we took the area covered by the positive differential reflectivity and KDP above the 5 kilometer, because this is the region where the cold cloud formation takes place. So we want to use, we want to know its usability for any, whether it has any prediction value, as because they can represent as a proxies for the convective updraft in the atmosphere and how they are associated with the lightning. And what we observed that the area of most intense convective feature with positive ZDR values increases through the convective initiation to mature stage and often occur during the, so that's the time when the raindrop growth in the strong updraft happens, because ZDR belongs to the oblateness and the size of the raindrops. So what does it further tells that it carries those liquid droplets and the other particles in the cold phase of the atmosphere, because the underlying updrafts are very strong in the MCS. So all these structures are there, and as the MCS mature, larger areas with positive ZDR and KDP values above 5 km indicates it is an increase in the updraft strength and the spatial extent. So if you want to monitor the evolution of updraft and its extent inside a thunder cloud, one can use the ZDR and KDP in a different way. Then, so this is this is nothing but a pictorial representation of MCS. So this is a summary of MCS in a vertical direction. Okay, so we use this is called as a quasi-vertical profile. We use the 10-degree elevation data and plotted in a vertical profile. So it's not an actual RHI cross-section. That's why it is called as a quasi-vertical profile. And it captures a fine vertical structure from with clear signature of melting. Okay, this is a melting layer. It characterized by different variables, very well matured signature. Two important findings here. So we can see that there is a broad ZDR below the melting layer. It indicates the presence of oblate raindrop or what is the melting hydrometers that is coming through the your melting layer. And what happens in the cold region, that's in the stratiform region. So in the ice part of the storm above, the Z decreases with height rapidly. So you can see there is a rapid decrease in the Z reflectivity value. And a prominent increase of KDP. Okay, you can see this is a positive ZDR at 8 km, even ZDR also. So it shows that there is a presence of a dendrite growth layer around 8 km. This signature clearly helps to know where the dendrite growth takes place, because these results corroborate, because in the past they shown that there is a prominent increase of KDP and ZDR happens at around 8 km. So in this case also you can see there is a prominent increase in the KDP and ZDR. And there are reasons for that, why KDP increases at that height, why ZDR increases. KDP increases because there is a high concentration of non-spherical ice particle at that height, and they are horizontally aligned. So whenever there is a horizontally aligned particle, KDP increases. Okay, and then there is a reason for increased ZDR. They happen due to the oblate shape of your dendrite, and whenever they fall, they fall preferentially with a horizontal direction. So that's why your ZDR also increases, because the horizontal dimension increases the ZDR value. And these are different variables. This is obviously from reanalysis. But this picture again emphasizes the use of radar data for understanding the vertical growth and the internal microphysical structure as a function of MCS life cycle. So on x-axis you have the initiation, mature and decay phase. Okay, same data set we use it for in a different way to know further characterizing the updrafts in the atmosphere. So we can use the volume or area occupied by the positive differential phase, differential reflectivity and specific differential phase above the melting layer as a proxy for the convective updraft in the storm. So again same plot, on x-axis you have initiation, mature and decay phase. The top panel shows the occurrences of this ZDR. This is KDP. And what does it shows? And the dashed line, these are the melting layer heights. Okay. So it shows that the KDP volume, which is shown in the second plot, they remain elevated during 9 to 13 hours. Okay, so this is the period. This is the elevated structure. You can see from 9 to 13 hours, there is a sudden rise is there. Okay, so what does it shows? It shows that there is a significant quantities of liquid rain or water-coated ice particle that are lifted above the melting layer by the strong updrafts. That's how it is indicated in this KDP plot. And if you see, and what does it indicate further? It indicates that there is an increased deep convective characteristics of a storm system. Okay, so once the convection gets established, you can use the KDP value. So because it shows that during the mature stage, the convective nature of a MCS is increased because the KDP values has suddenly jumped. At the same time, if you see the differential reflectivity, you can see that the GDR volume above melting layer is seen to have increased before the elevated positive values of KDP become evident. So before, you can see that these GDR values, they started appearing here. I think it's not working. Battery ho gaya, ye lijiye. Yeah, okay. So this finding agrees with the GDR column as an early observational signal of a convective updrafts. So if you want to know what are the convective and the updraft structure at the initiation time, one can use the GDR signal. If you want to use to know the updraft structure during the mature stage, it is well captured by the KDP signal. So both the variables provides the updraft characteristics. GDR provides the information about the initiation time, whereas the KDP provides the updraft characteristic during the mature stage. At the same time, these variables are also well correlated with the lightning data set. So they can be used to know, see, if you see this is the on x-axis, this is the KDP volume above the melting layer. On the y-axis, these are the lightning count. You can see there is a very good correlation because this is associated with the mixed phase process in the deep convective cloud. So these two variables are very well used for understanding the updraft characteristics inside a convective storm, and it has some diagnostic values also. Because if you track the GDR column, that's how now Manisha will tell about the more details in her presentation. She has tracked the convective cells and also the GDR column. So she has make a composite analysis for tracking the GDR columns inside the convective cells. That's how it is actually tracking the proxies of a convective updrafts in the storm by tracking the GDR column. Okay. Once we know the horizontal structure and different components, we try to know what are the vertical structures of different storms, different components of MCS. So what are the vertical structures of a convective core versus stratiform and anvil? So to do that, we made a composite CFAD of reflectivity, differential reflectivity, correlation coefficient, and specific differential phase. And they are divided into different stages of MCS. So this is the convective CFAD for initiation, mature, dissipation for reflectivity. Similarly, the stratiform cloud, how does the vertical structure varies during the MCS life cycle, the anvil part. So these are classified based on the radar data. As the MCS envelope passes over the radar domain, the underlying radar observation actually captures those signals, and based on the objective tracking, we classified those radar pixels into the possible storm types. Okay, yeah. Similar way, these are for other polarimetric variables and the stratiform component. Okay, so in a summary, using this satellite data, ground-based radar data, we made a composite structure and did some evolution-based diagnostics of monsoon MCS through this synergetic use. We identify more than 90 individual MCS cases and their storms by applying objective tracking methodology for satellite and polarimetric radar observations. And the main outcome of this study is that we are providing statistics of MCS in different physical properties. You can be it is a lifetime, the area, the propagation characteristics and its relation with the large scale components. The polarimetric variables are also used for knowing the fingerprints, and this analysis will be like a benchmark or reference for validating the simulation because we are achieving the cloud resolving scales by increasing through our HPC. So large scale models can run at a global cloud resolving models. So how do they represent the observed structures? How do they represent the upscale growth from a convective cloud to the mesoscale? So these results or these data sets will be very useful for validating the operational models from IITM, IMD, NCMA, WF. So these data sets can be very useful. With this, I stop here, and sakalo ke dhanyavad.
Thank you, Dr. Shastin, and keeping on time. Questions?
Okay. Yeah. May I ask
Yes.
questions? Thank you very much for nice talk. Yeah, actually, it's really nice, comprehensive, explanation of the MCS. And talking about you are introducing you have 3 zones on the MCSs over India continent. So did you find any difference in characteristics of MCS, in 3 regions?
Okay. That plot, I showed it for telling the precipitation, surface precipitation. One is over the Western Ghat, then Central India and Northeast India.
Right.
But as for the study shows, the Western Ghat is a very shallow convection. So MCS, they very rarely form. But the region over the Northeast India and the Central India, they are very favorable because the deep convection is supported by the large-scale synoptic systems.
Exactly. Yeah.
But we have not done that. But in the subsequent study by PhD student Manisha, she compared the MCS over the Bay of Bengal and the Central India.
Yeah. So in the beginning, you are introducing the general characteristics of the MCS. They are mainly working on the Pacific Ocean, probably. Steve Nesbitt or Cotton Schumacher has worked. Yes. So that maybe it would be nice to know that which is the difference between the Pacific Ocean and the Indian continent.
Yes. We did some analysis regarding the life cycle of MCS, comparing with the other MCS over the Pacific, Atlantic, and we observed that the MCS are not. They are long-lived only over the oceans. Land MCS over the Indian region are not that long-lived as compared to the Rocky Mountains and then Argentina. They are not that long-lived.
Yeah. So may I ask one more question? Yeah. So talking about the life cycle of the MCS, in your analysis, probably there is 2 peaks of the Diana arcs. Mainly comes from the convective clouds.
Yes.
So it's just a typical over India. I don't think that it is not typical over the Pacific Ocean.
So the second peak is not that prominent as compared to the first peak, but we feel that there are some MCS cases that are propagated over that. So this analysis is based only over the one radar in the Central India.
Yeah, actually, the midnight peak.
Midnight. So
midnight peak maybe.
Yes. Over the US and many other places, the MCS precipitation peaks in the midnight.
Yeah.
In the midnight, but over the Indian region, what we observed that they peak in the late evening to night hours, not exactly in the midnight.
Okay. So could you add more explanation about the orographic effect or Himalayan mountains effect on the
That
MCS?
could be another topic of research, but in this study we have not done that. But definitely the analyzing MCS over different regions by exploring the radar data could be taken up.
Thank you very much.
Yeah, Professor Takasaki, I just want to add, this MCS is not like Pacific and other thing. They have mostly used the TRRM satellite like GPM and TRRM. So here in India during the monsoon, this MCS is embedded with the small scale, storm scale convections we call, and that is contributing a lot. Okay, to the MCS precipitation. So because he is mostly using this radar data and studying this microphysics and this diurnal cycle, because most of these moistures are coming from the Bay of Bengal. That's why he is showing these things.
The main supplies from the synoptic scales.
Yes. So those are the different factors. And regarding the life cycles and other things, those are different. I think we can discuss those offline. Now it's a time for the questions from the audience.
Sir.
Yeah. Amit.
Thank you, sir.
Hi.
Sir, in your presentation, you showed vertical plots, column plots of ZDR and KDP.
KDP, yes.
But you said that you have constructed it using 10-degree elevation scan, sir.
Yes.
So with the elevation, means with range, the actual point or the column, that will be different. Then how a column is
this
created?
QEP, even though it is measured by 10-degree elevation, it is centered over the radar. So these QEPs are centered over the radar because if you take the cone, so it measures the along the range, and that range information is converted into the height.
Okay, but over the centers, there will be cone of silence. No? So
Over the apart from means beyond the cone of silence, the data is considered only.
Okay.
But you can say that if I ask you where is that QEP centered, ideally it should be at radar center.
Yes.
Because the cone starts from the radar center.
So, sir, for how much range, like?
So for this we consider only up to 70 kilometer, 60 70 kilometer.
Okay, 70 kilometers.
Yeah.
Oh, okay. And then, sir, that 70 kilometer data you have brought to
the vertical
center.
And then as a function of MCS life cycle, this data set is binned.
Okay.
For different variables.
Okay.
Because this will give the summary of what happens it's a height time plot.
But sir, if it is like in range 70 kilometers, then it may happen that it may intersect multiple cores.
Yes,
the beam is going so.
Yeah, it should happen because that's how the cloud structure is embedded within the cell. If you see the here one plot. Yeah, for example here, you can. Oh, it's not there. Okay, sorry. So the convective cells are embedded within. So definitely it will encounter. But as once it sees the stratiform cloud, you can see that in QEP plot.
Yes, sir. Yes,
it is very well organized, but not incoherent structure within that MCS.
Okay, sir. Thank you, sir.
Yeah, so Amit, in addition to this, just you consider cone of silence is like this. It's not a matter of like doing this. He's just flapping, and within the 70 kilometer, it's an aerial average. That's why the value may looks reduced. But over the overall features will be look good because this will be as good as your RHI. Not RHI, but as good as your RHI. And the scan strategy is also very important here. So 10-degree elevations he has considered, and if you go up to 60, so you can see up to 12, 14 kilometers. Okay. So, 10.
Yeah, 10 you can do a sensitivity by taking
so
20 degree versus 10
single
degree.
sweep is also okay, multiple sweep is also okay, but if you consider multiple sweeps, your resolution will become much better.
Yeah. Good presentation, Sachin. Just a clarification. In one of your slides, you have shown the increase in KDP above the freezing level.
Yes.
So simultaneously, do you have any aerosol vertical profiles for these observations?
Yeah, we have,
because,
but
because if you have there's a hypothesis of the aerosol invigoration effect, wherein these condensates will be lifted above the freezing level, and the storm can intensify.
Yes,
so such type of aerosol cloud interaction is also possible in such locations.
Profile as such we do right now for this data set we do not have, but now we are bringing the lidars also. Okay. That will give actual. Right now we have only the surface measurements or column integrated.
Okay.
But that's a good idea to incorporate the aerosol and the convection.
Right.
Yeah.
Because Manoj, this one I just want to add. This is not at the surface level. Aerosol invigoration will be very, very less in this case because it is at the higher level, and that is the typical radar signature because he is showing the ZDR column, dendrites and other things. This is due to these ice particles.
he was suggesting if we bring in the aerosol profile information.
That's what definitely radar is needed.
Will they have any correlation?
Yeah. Any other questions? Yeah, let's thank our speaker, Dr. Sachin Deshpande, for his nice talks on MCS, and he brings a very detailed structure of MCS and its microphysical properties with lightning. Due to the time's constraint, I think we could have listened more. Now we invite Dr. Amit Kumar, and he will be talking about integrated multi-sensor analysis of cloudburst event over Himalayas during southwest monsoon 2025 using dual pole X-band radar, geostationary satellite, and in situ ground observations.
चेंज हो गया क्या सुन बाहर निकल गया ना ये चलो चलो इसको खोलना एक बार बताइए चला ओके
I know those persons. So just a quick announcement whether Dharmodas is there. You will present? No, he's not there, right? Yeah. And Jyoti Sharma? And Vivekananda Panda? So yeah, Amit, so you have time. Okay. Thank you.
Namaskar, good evening. Sir, should I start? Yes, okay, sir. So, I will be talking about, like in this southwest monsoon season, there were multiple cloudburst events which were reported by media, saying that multiple cloudburst events have happened and they are increasing over our western Himalayan regions, mainly over Jammu Kashmir, Uttarakhand and Himachal Pradesh. So we tried to see if some of the events we are able to capture using our observation network, both in situ observation network, that is observatories and AWS ARG, and then using our dual pole radar. We have around 10 X-band radars in Western Himalayan region. So if any of the radar has captured any of such events, so I will be talking about this. So the presentation is like I have divided it into 3 parts. The first one is observations, what has happened, what was reported by our district observatory network systems or our departmental observatories, AWS, ARGs. Then what was the background synoptic conditions which led to such events, and then what were the various signatures which we could capture using our radar system, X-band radar systems in Western Himalayan regions. So if you will see that this is taken from latest Rajivan Sir's paper in Current Science in 2025. So there is a increase, the Himalayan states, around 40% of Indian disasters, they have happened in Himalayan states from all over India. And then the Himalayas are heating at the nearly twice the rate of Indian landmass. So what is happening that the trend of both intensity and frequency of extreme weather precipitation events that are also increasing. Like if you will see the media news from mainly from July to August, then you will see that every 3rd or 4th day there were reports that some cloudburst activity has happened in Uttarakhand, something has happened in Manali or Chamba, something has happened in Jammu. So actually what is happening that in Western Himalayan region there is a complex terrain. So if there is sustained rainfall also, then that small amount of rainfall is also capable of producing landslides or rock slides. And whenever a landslide or rock slide happens, then journal media terms it as a cloudburst, that some cloudburst has happened. Even there are illegal constructions in river beds, and whenever water comes in those river beds, then destruction happens, and that is also most of the times termed as cloudburst, that because of cloudburst uphill, the water suddenly came and then destruction has happened. So if I talk about 2025 alone, then around 303 extreme heavy rainfall events, that is as per IMD criteria, if the 24-hour rainfall is more than 204.4 mm, then we say that extremely heavy rainfall has occurred. So in Western Himalayan regions alone, 303 extremely, sorry, not in Western Himalayan, in all over India, 303 extremely heavy rainfall events have happened in JJAS in 2025. So Western Himalayan regions, you will see that interaction happens in lower troposphere and upper troposphere, middle troposphere. So if there is a western disturbance and at the same time there is moisture incursion or moisture flow because of the location of monsoon trough, or there is a circulation in lower troposphere, so the moisture gets confined in Western Himalayan regions, and then because of orographic lifting, it develops into highly mature and deep convective systems which give a very excess amount of rainfall. But because of less number of observatories that we have, it becomes really difficult to officially get that event recorded. And in media also we are not getting any, because multiple times what happens that past year images or past incidents are reported, their visuals and timings are reported as current incidents in media. So media database, that is also not fully, means you cannot trust that fully that something has happened. So the interaction between western disturbances and lower troposphere, that also results into extreme events in Western Himalayan region. And in recent times, the classic case case was the incident that happened in Kedarnath in 2013. So then also there was an interaction between western disturbance and monsoon, and then there was some studies have come up that glacier lake outburst that also happened there, that also intensified because of multiple excessive rainfall that has occurred upstream. So there are multiple factors which may bring catastrophic effect downhill. So if we see the isohetal analysis of 24th of August, so this 24th of August means that the rainfall information in this slide is starting from 8:30 IST of 23rd of August and ending up to 8:30 IST of 24th of August. So this is how the rainfall is recorded and reported in IMD convention and in WMO convention also. So this rainfall analysis of 24 August, ending at 8:30 IST of 24 August, you will see that there was a peak over Sambha region, and then there was another over Katwa region. So in Western Himalaya, that is South Jammu division, you will see that extremely heavy rainfall occurred on 23rd and 24th also. Then if we'll go to 25th of August, then we will see that it has shifted downhill, and now the Chamba Una region of Himachal Pradesh, that also you will see that the peak rainfall that has shifted downwards. And then on 26th of August, you will see that it was concentrated over north of Punjab. And on 27th of August, you will see that the whole Jammu division, extremely heavy rainfall was reported. And over Udhampur, that is it is a Air Force station, there you will see that 629 mm rainfall, 24-hour rainfall, that was reported. Over Vaishno Devi, Katra in Rayasi, there also around 528 mm rainfall was recorded. Over Jammu also, 280, 260 mm rainfall was recorded. Because of all this rainfall, this Tavi river, excess amount of water, very large amount of water that came into this river. And because of that, the Tavi bridge in Jammu, that collapsed. And when it collapsed, the traffic was also ongoing. So, and then the other thing, over Vaishno Devi Yatra Marg, there landslide happened, and because at Ardh Kumari, and because of that some casualty also happened. So in this study, I will be showing this Vaishno Devi case, how this was captured by our radar, and then what were the background synoptic conditions. So if you'll see this analysis, I'm showing from ERA 5 data. So you will see that over North Bay of Bengal, there was a low pressure area, and there was a cyclonic circulation over South Haryana, and the trough was at its normal position. Monsoon trough was at its normal position, and it was going through Shri Ganganagar and going till Head Bay, till this cyclonic circulation. So you will see that this whole, from Bay of Bengal, the winds were entirely southeasterly and easterly, and they were bringing moisture directly to the foothills of Himalayas in Jammu division. Then at 850 HPA also, both these systems were present till mid-tropospheric level. So we'll see that both of these systems were present, and the moisture of inflow was there at 850 HPA also. At 700 HPA, you will see that over Pakistan, the warm, no, sorry, no, not this one, this one. From North Pakistan, the cold air was coming, and from Bay of Bengal, warm moist air was coming. So both the fronts were interacting, and in this ERA 5 data, actually at 700 and 500 HPA, the signatures of western disturbance are not present. But if we will see the actual RSRW plots, then we will see that at 70° east till 28° north, there was a western disturbance was present over North Pakistan, and at 500 HPA. There at 500 HPA. So here we will see that slight signature is there, but it is not well marked at 500 HPA in error-free analysis. And at 200 HPA, if we will see, then we will see that we will see the signatures of the lower periphery of STWJ. This is Tibetan anticyclone. And after this lower trough of STWJ, we will see another high. So actually these conditions prevailed from 24th of August till 26th of August. So it acted like this Tibetan anticyclone, it acted like a blocking high, which was not allowing this trough to move further eastward. So, and because of this, we will see that even the divergence at upper level, that was also very high. It was around the order of 40 to 50 per second, we will see in meteosat imageries. So, this moisture transport, I will told also, and in this image also it is clearly mentioned that the moisture was getting built up in southern Himalayan regions. Then if you will see the low level convergence, then also we will see that because of that scissor present over Punjab and then it's tilting, we will see that on 26th of August, there was convergence that was happening over Jammu division. Then if you will see the vertical velocity, then that also we will see that over Jammu division and North Punjab and Chamba region of Himachal Pradesh on 26th of August, it was quite high. And so at 700 HPA also that orographic uplifting, that was supporting. Then the integrated vapor transport, that also we can see that how it picked up. Earlier it was concentrated over UP and Bihar on 24th of August, and then on 26th of August we will see then it is directly striking the southern periphery of our western Himalayan regions. So if we see the time latitude evolution also, then also we will see that this 30° north is around Jammu division, Jammu's latitude. So we will see that consistent moisture was present and transported in the region. And on longitude also, we will see that at 75° east, the consistent moisture flow that was maintained from starting from 24th to 26th of August. Then this is just the upper level divergence and vertical velocity plots also. So on 26th of August, we will see that till 6 or 9 UTC, the vertical velocity, there was a very high vertical velocity. This vertical velocity of 700 HPA and the divergence is of 200 HPA levels. So that divergence that I was talking about, then you will see that at meteosat, there was very high divergence that was present over the region, but with the evolution of day, it dissipated, it got dissipated. So this divergence also helped in sustaining of low level convergence over the region. Then using MODIS daily data, we will see that liquid water vapor, liquid water cloud water path, that was also maximum on 26th, and corresponding CTP from MODIS, that will also see that it was minimum on that day. Now, if you will come to DWR Jammu, then the elevation of DWR Jammu is 325 meters above mean sea level. So if you will see that because of lower Pir Panjar range, in lower elevations at 0.21 and 2-degree elevations, we will see that our north and east sector, that is blocked. And if we will see the location of Vaishno Devi shrine, then we will see that it is between two hills. This is our DWR Jammu. So the lower 3 elevations, they are blocked. So the at 4.5 degree elevation and 6 degree elevation, they are the lowest elevations which are beam blockage free, which we can get for Vaishno Devi location. So if the height of Vaishno Devi, if we compare, then the 4.5 degree is around 1 kilometer above the Vaishno Devi shrine bone, the vertical height, and the 6 is around 1.5, 1 or 2 kilometers. The central beam is 2 kilometers, the vertical distance. So these two only we have analyzed because these are the only beams that were available with us. So that was Udhampur. So in this, if you will see that this was the actual reflectivity values which we were getting after getting the corrected for attenuation. We will see that over Vaishno Devi, their successive cells, they were approaching Vaishno Devi and they were impacting the weather. So this image is of 6 UTC, this is of 840 UTC, and at around 9 UTC, that is 2:30 PM, as per the media reports, the landslide happened at Ardhkumari. So here also you will see that there were very high reflectivity that was present. Then if you see the KDP plots, then in KDP plots also we will see that because the time resolution, scan resolution is our 8 minutes, so you will see that higher KDP values were present to the south of Vaishno Devi shrine, and then after 10 minutes it was passed. So if the time resolution is less, scan timings is less, then we could have got the observations when it was overhead Vaishno Devi also. Now if we see ZDR values, then in ZDRs also we will see that large number of drops were present because there were high ZDR values which were present. So this signifies that large number of drops were present, but ZDR calibration, I have not performed ZDR calibration in this. So after doing were dominating in the area at the time of incident. Then rain rate, if you will see, then I've used RKDP. So using RKDP, we can see that at 840, we are getting some signatures of very high rain rate. So
I think, yeah.
This is.
Yeah, thank you, Dr. Amit. And this is very nice observations. Let's clap because I understand you have a lot of issues with this radar, but still it is very good that at least you have captured something. You have main issue with the ZDR calibration, but that calibration is more challenging because you have short pulse different calibration, long pulse to different calibration, and that is a consistent offset, I guess, because it is showing continuously 4. So, okay, I will now ask my co-chair. So. Okay, audience? Any questions? Okay, so I'm just asking, like you have said, like KDP rainfall, whether you have any gauge to see, any kind of gauge measurements are there?
So gauge measurements are there, as I was showing in our, with that comparison I have not shown, because on that day the radar was operated, it started its operation at 5:30 UTC, and then because of that severe weather event, all communications, they were cut off. So the data we have in fragments for that day. And gauge, as this is 24-hour accumulation, so then it's very hard to...
No, I didn't expect one-to-one correlation. I just want to see if gauge has
The
some
AWS, so actually in that area, in Vaishno Devi Shrine Bone, we don't have in AWS. We have in AWS in Udhampur, but for Udhampur also, the low-level beams are blocked. Three lowest beams are blocked. So the only observation we will get is from 4.5. But in Udhampur, because the Udhampur altitude is only 600 meters, the difference will
okay.
become
That is
3 to 4 kilometers.
Limitations of these radar deployments and other thing. And maybe in the future, if you want to show this kind of the things, please put one like iMerge or GS map, some kind of the rainfall things. Then
That, sir, we have taken from like both GPM merge data also we have, and INSAT and this GS map IMD merge that data from
GS
ISRO
map,
that
real now, Persian, INSAT, lot of things are there, just to show that radar is capturing. Of course, at least they have to understand this is not clutter, because people will come across that high rainfall means maybe clutter, something. Thank you, Amit.
Okay.
Yeah,
thank you.
Let's thank Amit. And you want to wind up the session?
Yeah, actually, thank you very much all speakers, and it's really nice to hear about from MCS and you characterized by the dual pole polarimetric radar data, and also the severe precipitation events using the polarimetric radar. So that these presentations are demonstrating the importance of the dual pole observations. Thank you very much.
Yeah. Thank you. Thank you. Now it's organized.
Thank you, Speaker, Professor Deshpande, and sincere thanks to the chairpersons for initiating and for sort of responding to such thoughtful deliberations. So this brings us to the close of the day one of the conference. So thank you everyone for joining in and sort of making this first day a fruitful event. So we look forward to 2 more days of engaging discussions and conversation. So we convene here tomorrow at 9:30 a.m. Yes, so this is for everyone's information that there will be an interactive session, a poster presentation at the AT hall, which is just adjacent to this hall. May I request all the participants, our resource persons, to please proceed to AT hall for the poster presentation, and we will meet everyone tomorrow here at 9:30 a.m. Have a wonderful evening ahead. Thank you.